Hi, I'm here to take you through architecting for the Amazon Web Services cloud. I've been using Amazon Web Services for over 7 years. For 4 of those years, I worked at Amazon, initially as a principal solutions architect and later as a principal consultant. I have had the opportunity to work with a wide range of organizations, from early stage startups to global enterprise organizations, and help them adopt the AWS cloud. This course is designed for solution architects who have limited experience with the AWS cloud. It is intended to provide an essential guide to effectively translate general architectural best practices and design requirements onto the AWS platform. During this course, we will cover essential educational resources, business considerations, cloud design patterns, cost optimization, as well as application platform durability, availability, scalability, performance, and security across a wide range of AWS products and services. We will provide architectural best practices and guidance for a number of service families. This will include products from Amazon Compute Services, storage and content delivery, databases, networking, administration and security, as well as some coverage of application services and deployment and management services. In this course, you will gain the foundational knowledge to be able to effectively and securely incorporate the AWS cloud into your organization's technology platform. While this course does not require that you have access to the AWS platform, learning will be significantly increased if you are able to follow along online. In order to create AWS resources, you will need access to either an AWS root account or an identity and access management user that has been granted access to the web-based management console. If you are completely new to the AWS platform, you should be eligible for the AWS free tier and therefore will incur minimal costs as you explore the platform. As we can interact with the AWS platform via the web-based management console or programmatically via one of the command line tools or numerous SDKs, it will be helpful to follow along from a PC or laptop running Microsoft Windows, Linux, or Apple's OS X. Let's get started. In this video, we will be looking at the AWS Economics Center. So let's get started. We will start off with a brief introduction to the AWS Economics Center and highlight some of the key resources and tools it provides. We will then take a look at AWS pricing and the AWS Simply Monthly Cost Calculator. Next, we will take a look at the AWS TCO Calculator and work through a simple example comparing the cost of operating a 3-tier architecture on-premise and the AWS platform. The AWS Economics Center is a section of the AWS website. It is dedicated to educational resources to help us better understand the cost model of the AWS platform and make it easier to compare the TCO of on-premise with AWS. The website is broken down into a number of sections covering customer case studies, customer videos, industry reports, AWS reInvent sessions, as well as subsections of AWS pricing and TCO. The focus of this video will be the AWS pricing and TCO sections of the Economics Center. We can find the Economics Center at aws.amazon.com/economics. As we will look at the AWS pricing section first, let's select the link highlighted by the red box. On the AWS pricing page, we select the link to take us to the AWS Monthly Calculator. The AWS Monthly Calculator is very useful. It helps us to estimate monthly operational costs as well as upfront costs if we choose to reserve capacity for AWS Web Service resources. For example, let's imagine we are interested in estimating the cost of operating a 3-tier architecture consisting of 4 web servers, 2 application servers, and a highly available database server. All we need to do is enter the required resources on the EC2 section of the calculator. The calculator allows us to select from a list of available EC2 instance types and operating systems. We can also choose between on-demand and one of a number of reserved instance consumption types. For the purpose of this simple example, we will leave the consumption type as on-demand for both the web and application servers. We now configure a highly available instance of RDS, specifying the database engine to be MySQL and provision 200 GB of 1000 IOPS PIOPS storage. We can then see a summary of the expected monthly costs by selecting the Estimate of Your Monthly Bill tab. We can go back and modify details if we wish, and the estimate is revised accordingly. let's go back to the Economic Center and this time select the link to the cost savings section of the website. From here, we select the button Calculate Your Savings. And we are taken to the TCO calculator. By default, the basic interface is presented. Let's update this to advanced. We can now enter the details of our resources on site, in this case web, application, and database servers running on the VMware platform. We choose values for operating system, utilization, and the virtualization host. Next, we specify how much storage and networking we have, and then click on Calculate TCO. The TCO results are organized into 3 or 4 sections. The first section is a summary of the 3-year cost breakdown. We then scroll down to the Environment Details section, where we can compare resources side by side. The next section provides a visual comparison of the compute, storage, and network costs, along with subsection breakdowns for each category. If we scroll right to the bottom of the page, we can see an expandable section. Let's click on the Calculations tab. By selecting the tab, we can see how each calculation is performed, and if required, adjust one or a number of assumptions to better match our infrastructure. Let's imagine that when we looked at the calculations, we felt that one or more of the on-premise resource costs was incorrect. The TCO calculator lets us revise them. In this case, we update the cost associated with the virtualization host. This results in a revised cost comparison between on-premise and AWS resources. In this video, we will be looking at the AWS Product and Services website. We will start from the AWS Products homepage and take a look at the AWS product categories. We will then focus on a particular service to highlight the general structure and resources contained within each respective product subsection of the AWS website. This will include pricing, documentation, frequently asked questions, and service level agreements. The AWS homepage is located at aws.amazon.com. The product section, the focus of this video, can be reached by selecting the Products Navigation link highlighted by the red box in the slide. The AWS Products and Services section of the website is located at aws.amazon.com/products. AWS products and services are grouped together into about a dozen different categories, ranging from compute, databases, analytics, to AWS support. While the resources and layout of each isn't identical, for example, AWS support will look quite different to the compute category, they generally follow a similar pattern which is useful to understand. Let us focus on the AWS storage and content delivery. Storage and content delivery covers services such as Amazon S3, Amazon Glacier, Elastic Block Storage, etc. Each service is accompanied with a link, Learn More, to the dedicated product or service homepage. The product or service homepage consists of a product summary section, usually with a helpful overview video, a product details section, pricing, getting started resources, frequently asked questions, and SLAs. The pricing section is useful when we are investigating the cost of a service. But we'll typically find the AWS cost calculator located in the economic section of the website the most valuable resource for estimating the cost of our architectures. The resources section is the place to go to quickly find the necessary technical resources for a product or service. In particular, we will probably visit the documentation section most frequently. Documents are typically broken down into Getting Started Guides, API Reference Guides, Developer Guides, and Console Guides. For services with a strong admin focus, such as the Amazon Virtual Private Cloud Service, there are additional network administrator-focused resources. These documents are actively maintained, so when possible, it's generally advisable to use the online versions to guarantee that we are working from the latest documents. The FAQ section is invaluable. If you have a question for a given product or service, then there's a good chance that it's already covered here, with a verified, accurate answer. We can save ourselves a lot of time by looking here before searching through service documentation or posting a question to the AWS Support forum. Finally, we have the Amazon SLA section. For services with an associated SLA, there will be a detailed summary of the policy, service commitments, and definitions. Obviously, we need to understand the service level agreement of each service we consume and factor it into the expected availability of each of our architectures. In this video, we will be looking at the AWS Architecture Center. We will start from the AWS Architecture section of the AWS website. We'll then look at the Reference Architecture section and Architecture white papers, followed by the subsections covering recorded webinar content, as well as the AWS simple icons. We'll wrap up by looking at the section corresponding to the AWS webinar program. The AWS Architecture section is located at aws.amazon.com/architecture. It is designed to provide us with the necessary guidelines and best practices to build highly scalable and reliable applications on the AWS platform. One of the most valuable sections of the AWS website is the AWS Reference Architectures section. It contains a number of 3D architectures drawn using an isometric projection. Collectively, they cover the most common design patterns. These should be the foundation from which we build our designs and reference architectures. For example, the Web Application Hosting Reference Architecture shows the key building blocks of a web application hosting system on the AWS platform. As shown in the slide, the reference architecture shows how resources should be geographically distributed to increase availability, along with commonly used services such as auto-scaling that helps make such an architecture more scalable and elastic. We'll now look at the Architecture White Paper section. This is where AWS publish and maintain technical white paper documents, often with detailed implementation details. For example, the AWS Disaster Recovery White Paper highlights relevant AWS features and services that we can leverage for business continuity and provides guidance on how to prepare and recover from a disaster event. While white papers and reference architectures are invaluable, recorded webinars are a welcome addition to online learning. The Recorded Webinar section, located at the bottom of the Architecture Center homepage, contains links to previously recorded content. Webinars cover a wide range of topics and experience levels across both commercial and public sectors. While the 3D isometric icons used to create the AWS reference architectures were not available for use by AWS customers when this video was created, the two-dimensional icon set are available for use purposes as described on the AWS website. In addition to being able to download versions for use with common desktop applications, they are also integrated with online drawing tools. And finally, we have the AWS Architecture Webinar Program. Here we can see future webinar schedules as well as recently delivered webinars from locations around the globe. In this video, we will be looking at the AWS Marketplace. We will start off by looking at the AWS Marketplace homepage and provide a brief introduction to the service. We will then look at the desktop application section, followed by the software infrastructure section. Next, we will explore the developer tools and business software sections. And finally, wrap up by looking at selling on the AWS Marketplace. The AWS Marketplace is a section of the AWS website located at aws.amazon.com/marketplace. From the marketplace, customers can search, buy, and sell software and services that run on the Amazon EC2 web service. Software is grouped into a number of categories as indicated by the red box in the slide. Let's take a closer look at the category of applications named Desktop Applications. Desktop Applications is a relatively new category on the AWS Marketplace. It is focused on applications that will run on the Amazon Workspaces, Amazon's managed desktop computing service. Within the Desktop Applications category, applications are further grouped into subcategories. For example, in the Productivity and Collaboration section, we have the ability to select Microsoft Office. Next, we'll take a look at the Software Infrastructure category. The Software Infrastructure category is currently the largest category on the AWS Marketplace. It contains a comprehensive collection of commercial and open source applications. We have the ability to search by product name, operating system, pricing plan, whether it's available under the AWS free tier, its rating, region, etc. In this example, we have searched for all of the available Atlassian products. If we want to launch the Atlassian Stash product on an EC2 instance, we just need to click on the application name. This takes us to a summary screen where we are presented with additional product-related information as well as the EC2 operating system details and corresponding Amazon machine image. In particular, we should take careful note of the pricing section to ensure that we understand the costs associated with running products and services from the AWS Marketplace. If we are happy to proceed, configure and launch the instance, we click on Continue, and are taken to the EC2 section of the AWS Management Console. Let's navigate back to the home page and take a look at the next category, Developer Tools. The Developer Tools section contains both developer and operations-focused tools, so DevOps may be a more appropriate description. This category is further broken down into issues and bug tracking, monitoring, log analysis, source control, and testing. Continuing on through the list, we come to business software. This is the second largest category after infrastructure applications. Business software is subdivided into a number of subcategories, including business intelligence, collaboration, content management, and media, to name but a few. Irrespective of the category, it's common for organizations selling software on AWS Marketplace to provide both a bring-your-own-license version and a version where the license cost is already bundled in. Choosing the wrong one will result in additional unnecessary costs, so choose carefully. The final element of the AWS Marketplace we will look at in this video is how to sell software and services. The AWS Marketplace also provides a sales channel for AWS partners to offer software and services that run on the AWS platform. Before selling software and services via the AWS Marketplace, we need to qualify to be a seller and sign up. AWS provides detailed registration prerequisites, so we should follow the links under the section How to Sell Your Software on the AWS Marketplace, located towards the bottom of the management portal. In this video, we will be looking at the support section of the AWS website, so let's get started. We will start off by exploring the AWS Support homepage and drill down into some of the key subsections. We will then explore the AWS Support Center and Trusted Advisor, both via the AWS Management Console. Next, we will explore the AWS discussion forums and conclude by looking at the AWS Service Health dashboard. Let's start from the AWS homepage located at aws.amazon.com. The support section of the website is located under the More drop-down list. The support section of the AWS website is divided into a number of sections, including customer and partner testimonials, Trusted Advisor, event management, pricing, features, frequently asked questions, and news. Let's take a closer look at some of the most useful subsections for architects. AWS Support is available in a number of different tiers, each with a different SLA and support features. At one end of the spectrum, we have basic support that all AWS customers benefit from at no additional cost. At the other end of the scale, we have enterprise support, which provides the greatest level of support, features, the greatest level of SLA, and access to dedicated AWS support personnel. If we are running AWS in production, or production activities could be impacted by a lack of timely support, then developer level support should be a minimum level that we sign up to, with business level support being a common choice. Basic level support is included as part of our monthly AWS resource costs, but developer, business, and enterprise come at additional cost. Developer level support costs are the easiest to understand, as it's fixed at $49 per month, irrespective of the size of our AWS resources bill. Next, we have business level support. The cost is the greater of $100 and a variable percentage of our banded AWS resource costs. Finally, we have enterprise support, where the cost is the greater value of either $15,000 and a variable percentage of our banded AWS resource costs, albeit at significantly higher and wider bands than that of business support. One thing to note when prepaying for reserve capacity is that there will be an accompanying upfront support cost too. Refer to the Purchasing Support for Reserved Instances section of the pricing page for full details. AWS Trusted Advisor is kind of like an AWS expert that reviews our environment and provides recommendations for improvements. Recommendations are grouped together into one of four categories of cost optimization, performance, security, and fault tolerance. The number of areas covered in each category is dependent upon the current support level we've subscribed to, with only 4 checks being performed for basic and developer level support and over 40 checks for business and enterprise level. The Trusted Advisor dashboard is available via the AWS Management Console. Each section allows us to drill down into the source of the alert or warning notification. Continuing on in the AWS Management Console, we can view our support case dashboard, create new support cases, and review our case history. Support is little different from any other AWS web service in that we can interact with it via either the Management Console or API if we choose to do so. This would, for example, allow us to integrate AWS Support with an existing portal if we so choose to. Moving back to the AWS Support homepage, let's explore the documentation section of the website. AWS provides a user guide for AWS Support, an API reference guide, documentation for Trusted Advisor, and the AWS Support Knowledge Center. The next section of the support website we will look at is the Events Management section. Events Management is a specialized architectural and operational planning service that AWS Support assists customers with. When failure is not an option or an event carries significant risk, then the Event Management service can help us manage that risk. The Knowledge Center contains highlights of the most useful frequently asked questions from each of the AWS web services. This is a useful reference for new customers to the AWS platform, but more experienced users may find it more efficient to go directly to the service in question. In addition to AWS Service Frequently Asked Question highlights, the Support Center also contains an FAQ page for the AWS Support service itself. One of the most valuable sections of the AWS Support website, especially for customers with basic or developer level support, is the AWS Discussion Forum. The AWS Support forums are grouped by AWS service and provide questions and, more importantly, verified responses from experienced technical support engineers. While discussion forums on third-party websites can be a useful source of information, we should consult official AWS channels first for trusted, reliable responses. And finally, we have the AWS Service Health Dashboard. This provides an up-to-date summary for each AWS service in each region, along with service RSS feeds. If we experience elevated service errors or latencies, then we should check the service dashboard to determine the extent of the problem. In this video, we will be looking at the AWS blogs, so let's get started. We will start off by looking at the official and principal AWS blog. Then we will take a look at the application management and development blogs. Next, we will visit the AWS security blog, and then we'll look at the big data and partner network blogs. We will then wrap up by looking at the AWS service blogs. The AWS official blog is principally brought to you by Jeff Barr, Chief Evangelist for AWS. It consists of highlights of the most important AWS announcements. As an architect, time is a scarce resource, so if we only have time to follow one blog, this should be the one. The official AWS blog is located at aws.amazon.com/blogs/AWS. It provides a useful starting point to jump to the growing list of specialty AWS blogs as indicated by the red box in the slide. There are local language translations for Chinese, Portuguese, German, and Japanese. While the look and feel is currently a little different, blog posts highlight the most valuable content for the respective local market. The next category of AWS blog is the AWS Application Management blog. The AWS Application Management blog contains insights from developers, system administrators, and architects. This is a useful resource, in particular if we have a keen interest in DevOps in addition to architecture. Next, we have a number of blogs that focus on using the AWS SDKs. Oddly, Python isn't covered here, but there is a comprehensive Python Developer Center located at aws.amazon.com/Python. Next, we have the AWS Security blog. The AWS Security blog covers both security and compliance on the AWS platform. Security should be the top priority for us as architects, so this blog is highly recommended reading for us all. Now we move on to the AWS Startup blog. The AWS Startup blog is the accompanying blog to the AWS Activate program. It is designed to provide startups with the resources needed to get started on AWS. This is a useful resource not only for startups, but established businesses too, as it may highlight software or platforms deployed on AWS that are coming of age and will make the transition into the established commercial and enterprise spaces in the future. It also contains posts of startup events and startup company success stories. With products such as Amazon Elastic MapReduce and Amazon Machine Learning, it should come as little surprise that AWS has a dedicated big data blog. AWS Big Data blog provides articles showing us how to collect, store, clean, process, and visualize data. The AWS Partner Network is served by a dedicated Partner Network blog. AWS Partner blog consists of customer and partner success stories and reference architectures from around the world. And finally, we have services-focused blogs. Given the extensive number of AWS services, this section of the official blog seems a little underrepresented, but there's no cause for concern. Updates corresponding to the myriad of AWS services are posted under the main AWS blog. As we would expect, service posts contain useful articles on how to use a particular service, new feature, and service-related events. In this video, we will be looking at AWS Events and Webinars, so let's get started. We'll start from the AWS Events and Webinars section of the AWS website. We will then move on to look at the AWS reInvent series, and then take a look at the AWS Global Summit series and Awesome Days. We will then consider AWS user groups and conclude by looking at the AWS Webinar Program. The AWS Events and Webinars section provides a summary of recently conducted and future planned events. Events cover a broad range of topics from AWS product-focused events such as Amazon S3 to events with a public sector or startup focus. AWS reInvent is the largest of AWS's events and usually takes place in October each year. The event spans several days and consists of technical and business tracks. reInvent has the objective of imparting the knowledge and skills to help participants refine their cloud strategy, improve developer productivity, increase application performance, and reduce infrastructure costs. If we cannot make reInvent each year, then the next best thing is to attend one of the Global Summit series run in a number of cities around the world. The Global Summit series is also an annual event and has a similar format to that of reInvent, but it is generally restricted to 1 or 2 days, with the first day restricted to AWS partners. The name Awesome Day is a play on words for a free, one-day training event ideally suited to developers, system administrators, and IT professionals who are eager to learn more about the cloud and also get training on the AWS platform. A number of cities around the world have a healthy user group community, meet to network, discuss ideas, and present and share knowledge on all things AWS. And finally, we have the official AWS Webinar Program. Here we can see future webinar schedules, as well as recently delivered webinars from locations around the globe. The webinar program lives under the architecture section of the AWS website. In this video, we will be looking at AWS agreements, terms, and acceptable usage. We will start by carefully explaining the purpose of this video. We will then take a look at the 2 current customer agreement models. Next, we will look at the acceptable usage policy, and we will wrap up by looking at guidelines for vulnerability and penetration testing on the AWS platform. The purpose of this video is not in any way intended to provide legal advice or guidance. We should always consult with qualified legal counsel for all matters concerning contracts, terms, and conditions. Now that we have the obligatory disclaimer out of the way, let's look at what we are looking at to achieve in this short video. The main objective is simply to create awareness and highlight the choices that we have when consuming AWS products and services. We will look at different consumer options and provide some guidance around which may be appropriate based on the size and degree to which our business is dependent upon the AWS platform. We will also highlight elements of the AWS acceptable usage policy that, while most people would consider reasonable, are possibly things that we may not have seen before, even when consuming services from external providers. When we initially sign up to use AWS, we agree to a set of terms and conditions that govern our access and usage of the AWS service offerings. This agreement is called the AWS Customer Agreement or Click-Through Agreement. The Customer Agreement takes effect when we click the Accept button or checkbox presented with the terms or, if earlier, when we use any of the AWS service offerings. It's often the case that the click-through agreement is performed by a senior technical or business team member, often because they have a corporate credit card, which is required during the sign-up process. The AWS Customer Agreement can be found at the URL presented in the slide. While this should be read before signing up to AWS, it's usually the case that the person signing up will take a cursory look and accept the terms and conditions. What we do from this point onwards depends really on what type of organization we are or we represent. If we are a startup or a small business, we will probably just securely store our AWS root credentials and get on with it getting as much value from the AWS platform as quickly as possible. If we are an established business in the commercial sector, or we are a public sector organization, then we definitely want to share the AWS customer agreement with our legal counsel. The larger our organization, the more likely our legal counsel will want to include some additional terms. The AWS Enterprise Agreement is the vehicle for including these terms. At the time this video was created, guidelines on specific terms typically included in an AWS Enterprise Agreement were not readily available on the AWS website. There are, however, a few examples of organizations that have publicly shared some of their terms via the internet. The Stanford University IT Services Department is one of them. For example, at the time their enterprise agreement was signed, they had negotiated improvements to security, privacy, and audit protection. They had also terms relating to the Family Education and Rights and Privacy Act, some branding and trademark protection, extended payment terms, termination lead times, and data recovery. AWS recommends that customers wishing to enter into an enterprise agreement should contact their local sales representative. As architects, we should leave the legal discussions to those qualified to have them. However, we should read and understand AWS's acceptable usage policy. This can be found at the URL presented in the slide. The acceptable usage policy is succinct and should be mandatory reading for everyone using the platform. The policy is broken down into 6 short subsections, each with clear and easy to understand guidance on what's not acceptable. There should be no surprises to what's in the acceptable use policy, as it's simply common sense. Usage guidelines around penetration testing are implicitly referred to in the policy. However, this is something that we should be explicitly aware of, so let's take a closer look at them. AWS's acceptable use policy describes permitted and prohibited behavior on AWS and includes descriptions of prohibited security violations and network abuse. As penetration testing is frequently indistinguishable from these activities, AWS have established a policy for customers to request permission to conduct penetration testing. As indicated by the acceptable usage policy, penetration testing of AWS services themselves is strictly prohibited. If we want to perform penetration testing on applications and services that we deploy onto the AWS platform, then we need to complete the AWS Vulnerability and Penetration Testing form. The form can be found at the URL presented in the slide. The current penetration testing policy prohibits the use of T1 micro and M1 small instance types in testing. We need to give AWS suitable notice before performing penetration testing, as indicated in the penetration testing section of their website. Currently, this is 24 to 48 hours notice. While we can specify multiple dates and times, a single request will only remain valid for a period of up to 3 months. In this video, we will be looking at AWS resource consumption models. So let's get started. We'll start by introducing the 3 cost models currently offered by AWS and explore why they are useful. Next, we'll briefly look at the AWS Simple Monthly Calculator. In the remainder of the video, we will take a closer look at each of the supported models of On-Demand, Reserve Capacity, and Spot, highlighting design considerations as we go. Today, AWS supports 3 different models for consuming resources. These are On-Demand, Reserve Capacity, and Spot. On-Demand allows us to consume resources as a pure utility service. We pay as we go and have no commitments or contracts. Reserve Capacity is a way to consume resources under a blended OpEx-CapEx model. And the Spot consumption model allows us to consume resources similar to On-Demand, but based on the market price of the resource. More on this in a minute. The 3 consumption models collectively provide flexibility around how we pay for resources and the expected availability of those resources. For example, we can choose to consume AWS services purely on demand. We could also choose to consume some services with no ongoing payments. We could also choose to consume some services with no ongoing monthly payments, with all costs up front. Our reasons for doing this may be to optimize our costs or control OpEx-CapEx costs for one of a number of business reasons. As we will see shortly, Reserve Capacity model provides greater commitments around the availability of resources and not just a means to control OpEx and CapEx. As AWS's pricing model is granular in nature, that is, we are charged for what we use, it can be a little complicated to estimate costs. Thankfully, AWS provide a useful simple monthly calculator to help us. In particular, the cost calculator is incredibly useful for helping us estimate resource costs for resources consumed under the Reserve Capacity model. We cover the simple monthly calculator in more detail in the AWS Economics Center video in this series. Now let's take a closer look at the on-demand payment model. On-demand was the original payment model provided by AWS, and it's one of the tenets of public cloud. When we consume resources on demand, we simply pay as we go with no upfront payments or contracts. On-demand uses a utility pricing model, so we only pay for the resources that we use. If we stop using a resource, then we do not incur any additional costs. We should understand the respective AWS service pricing model to understand what stopping using a resource actually means. For example, a stopped EC2 instance will still incur a cost. On-demand provides a number of benefits. Firstly, the lack of contracts and commitments means that we no longer need to perform capacity planning upfront to choose resources. We can take an educated guess on required resources based on the available data to hand. If we find that we need more compute, memory, or storage, then in the case of EC2, we can stop an instance and choose a more appropriate instance type. On-demand is also a great option if cash flow needs to be closely managed and the business decides that switching CapEx for OpEx is beneficial. It should, however, be noted that on-demand consumption models will be the least cost-effective consumption model for resources with consistent or well-understood high utilization usage patterns. The reserve capacity consumption model allows us to exchange some of the OpEx costs of on-demand, in some cases all of it, for an upfront cost and a reduced monthly payment. AWS provides strong and growing coverage for the reserve capacity model, but it's not currently available for all AWS services. We should refer to the pricing section of each AWS product for the latest supported pricing models. That being said, today support for reserve capacity includes EC2, RDS, EMR, DynamoDB, and CloudFront. By providing a commitment to AWS to consume a given resource, we receive a reduced hourly rate. However, it should be noted that if we incorrectly estimate the utilization of a resource, it's possible that the effective monthly cost amortized over the duration of the reserve contract period will be greater than that of an on-demand instance. We can use the AWS Simple Monthly Calculator to good effect here to help us ensure we choose the right consumption model. However, we still need to understand our usage patterns in order to get accurate pricing. A secondary reason why we may choose to purchase reserve capacity is to obtain greater commitments from AWS to provide resources when we need them. While the public cloud promises infinite capacity and scalability, clearly it's a finite resource. If everyone wants exactly the same resource at the same time, then it's possible there may be resource contention. While uncommon, we may want to seek greater commitment from AWS that those resources will be available when we need them. Reserve capacity provides this. It should be noted that the reserve consumption model currently varies between services. This includes both the duration and utilization consumption components. Let's illustrate this by taking a closer look at the reserve consumption model for EC2 and RDS. The image in the slide shows the billing options for a T1 micro instance. There are 5 billing options, 6 if we include on-demand. The duration of the reserve capacity model includes a 1 and 3-year option. The other dimension to the reserve capacity model for EC2 is the percentage of CapEx. The 1-year payment term provides the greatest number of options with support for all upfront, an all CapEx model, a partial upfront cost, and no upfront cost. While the no upfront cost model may appear to be similar to on-demand, it's not. The effective hourly rate is based on assuming a resource will be consumed 24/7. Therefore, if we only use the resource for 1 hour each day, then the effective hourly rate will be considerably greater. We can make significant cost savings by using reserve capacity, but we need to understand the expected utilization of our environment in order to do so. Similar to EC2, RDS provides options for both the term of the reserve capacity and the utilization. Unlike EC2, RDS uses a slightly different weighting system. It uses heavy, medium, and light utilization. Similar to EC2, the most cost-effective offering will depend on our actual utilization rate. Once again, the AWS Simple Monthly Calculator can help us choose the right consumption model. When we enter into a reserve capacity consumption model, we are committing to consume capacity. If we don't use the resource as much as we expect, or use it at all, then that's going to reduce the operational efficiency of the resource. We should invest time up front, if necessary consuming resources on demand, before we lock in a commitment to reserve capacity. It's often helpful to think of resources in terms of those that are baseline, ones that will consume 24/7. Other resources that will consume frequently but not necessarily 24/7, and resources that we use predictably but infrequently. such as weekly batch workloads or those used in a disaster recovery scenario. The better we understand our usage patterns, the greater the potential cost savings. As a general rule of thumb, consider purchasing baseline resources and a percentage of predictable, frequently used resources as reserve capacity. Infrequently used or unpredictable resource usage is more economically served via on-demand or spot capacity when possible. As reserve capacity is often restricted to a type or geographical location, we need to factor this into our calculations. If we are architecting for availability, then we should spread our reserve capacity evenly between availability zones in a region. However, choosing the correct instance type often takes feedback from running a system in production or at the very least realistic load testing. As we've seen, resources can be reserved for either a 1 or a 3-year period. It's worth considering whether we want to be locked into a given family of resources for 3 years or whether just a 1-year term is sufficient, as this gives us a good blend of operational efficiency with future choice. That being said, if we choose the wrong reserved instance capacity, there are options. We can sell the capacity on the AWS Marketplace. While this will incur costs, assuming that someone else wants to buy our reserved capacity from us for the remaining duration of the contract, this is a very good option. As a final consideration on reserve capacity, we should note that when we choose to make a CapEx payment, there will be an associated upfront support cost as per the support contract we are signed up to. Refer to the support section of the AWS website for more details on this, or use the AWS cost calculator to estimate the upfront support costs. The last consumption model we will cover in this video is Spot. Unlike EC2 capacity, it is available at market rates based on supply and demand. If we want to consume a spot resource, we simply bid for a given resource, and if our price is above the current dynamic market rate, then we are allocated the resource. If, however, the market price goes above our bid price, the resource will be taken away from us without warning. While architecting to accommodate failure is a key design principle, there may still be undesirable consequences of replacing on-demand and reserve capacity with Spot. For example, if we use Spot for all our web or application server tier, and all or a large portion of our Spot instances are terminated, we may not have enough resources to meet demand. Furthermore, unnecessary termination of resources will still require TCP connection to be re-established, even if we manage state externally. This will not be a great user experience if it's a frequent event. However, Spot instances can provide significant cost savings and are an excellent choice when we can accommodate their ephemeral nature. In part, this is achieved by breaking down work tasks into smaller chunks, so termination impacts a smaller proportion of resources. We can also frequently checkpoint state into a persistent external data store to allow partially completed tasks to be picked up by another resource and completed. As the price of Spot resources is dynamic, AWS provides programmatic access to pricing data. This allows us to track the Spot price, make changes to our current bid price, and potentially increase our on-demand or reserve consumption as necessary to meet demand. In this video, we will be looking at the key concepts of cloud computing that we should bear in mind as we architect for a public cloud platform. We will look at 5 key concepts that we should consider as a guide to help us take full advantage of a public cloud platform. While they are not requirements of architecting for the cloud, ignoring them will often lead to a lift and shift architecture that will result in many business, architectural, and cost benefits being unrealized. One of the promises of public cloud is almost limitless access to resources when we need them. While resources are clearly not infinite in supply, they should be considered like any other utility service, such as water or electricity. Considering the AWS platform as a utility service is incredibly powerful and almost eliminates capacity planning. If our application does not scale well on on-premise infrastructure, it's almost certainly not going to scale well on a cloud platform. If anything, deploying our application in a cloud environment may highlight the lack of scalability on the application sooner than we would have seen on-premise, because resources can be added as required without restriction. A public cloud platform provides the foundational building blocks into which we can build global scale applications. We still need to understand how our application will scale, where its scaling bottlenecks are, and ensure that we design for growth within a sensible time frame. It's easy to keep adding resources to an underperforming architecture for ever-decreasing returns. The goal should be linear increases in capacity with increased investment or resources. Ignoring this will lead to a reduction in one of the key drivers for business adoption, namely a reduced total cost of ownership. Consuming a public cloud platform reduces a huge chunk of operational responsibility and makes it the responsibility of the cloud provider. This is not too different from traditional outsourcing models of the past. We still have operational responsibilities, they are now simply different and should require far less effort or heavy lifting than we previously needed to expend. Many of the operational gains can be eroded if we don't plan and develop our new operations over time. By elastic, we just mean architecting to be able to take advantage of adding or removing resources when we need to. Without scalability, elasticity doesn't really make sense, but the two concepts are different. We can have a massively scalable architecture, but if we can't easily modify the resources it consumes, then it is not elastic. One of the properties of a utility service is the ability to consume it when we need to, and stop when we do not. While the cost savings for reducing CapEx are obvious, being inefficient with our use of resources, such as over-provisioning, will increase OpEx and therefore erode our TCO. Designing for elasticity also makes our architecture easier to repair in the event of one or more components failing. For example, if we design our web server tier to be elastic, then in the event that a web server fails, we can simply replace it with little or no impact to service. We used to have to deploy resources for peak load. This was expensive, as most of the time a system is not operating anywhere close to peak capacity. Furthermore, if our capacity planning underestimated peak load, then we now just experienced a loss of service or missed a key performance indicator. Either way, not a great result. By making elasticity one of our core design components, we are far better prepared to accommodate changing operational conditions, either for operational efficiency or to meet unexpected load. Let's consider how the load may vary on an e-commerce website throughout the day. The peak load could be several times higher than that of off-peak. Furthermore, seasonal peak load is often far greater, with values of an order of magnitude greater than off-peak not uncommon. In the diagram, the area represented by the orange diagonal lines corresponds to the cost of statically provisioning to meet peak load. The grey area represents the minimum cost required to meet operational load, and the total area represented by the solid vertical orange bars corresponds to the cost of elastically scaling to meet operational load. We can often save 30 to 40% in our operating costs by building elasticity into our architectures, so elasticity should be an important part of the design planning stage. Any organization that has provided an application or service to an international customer base knows that establishing contracts and deploying and managing resources isn't a simple task. The task becomes even more complicated the further down the stack, such as compute, network, and storage, we need control over. Public cloud providers provide global reach and standardize the deployment and management of resources. In the case of AWS, you can deploy resources in one of their US regions as easily as you can in Asia Pacific or Europe. Removing the barrier for global deployment means that as an architect, we can think about improving our customer experience by deploying resources closer to where our customers are and not being burdened by contractual or environmental barriers. As Mark Andreessen once said, software is taking over the world, and nowhere is that more obvious than cloud computing. Consuming virtual resources as web services means that access can be programmatic. For example, it is just as easy to launch an instance of Amazon EC2 as it is to instantiate any other class object. While we could use the AWS Management Console to manage our resources, we should strive to drive more of our interactions programmatically, as this will pave the way for automation. While most enterprise organizations will have long ago embraced virtualization, virtual administration of anything other than infrastructure-like services may be new and can make teams feel a little uncomfortable with a loss of control or a layer of abstraction. Teams can often feel somewhat disempowered and potentially concerned about job security. As with the adoption of any new technology, some of the greatest challenges lie within change to people and process. Virtual administration and automation should be embraced. This will allow teams to focus on higher level issues and challenges, but be more efficient, look after greater numbers of resources, and offload low-level, undifferentiated heavy lifting, which, for the most, is a distraction from more interesting activities. One attractive property of a public cloud is addressing the OpEx-CapEx balance. It's possible to completely eliminate CapEx when operating in a public cloud. This is particularly valuable during the early stages of adopting a platform or deploying a new application. As usage patterns are better understood, organizations will typically take a balanced OpEx-CapEx approach to minimize costs and obtain greater commitments from cloud providers on the availability of resources. As an architect, we should be acutely aware of when and how to optimize our environment for TCO. I often compare public cloud platforms to other utility resources such as water or electricity. The utility pricing model provides unprecedented visibility into where costs are incurred and also the flexibility to turn on and off services when not required. AWS provides a number of features and tools to help us minimize TCO, including AWS Trusted Advisor, the Economic Center, a TCO and cost calculator, not to mention a selection of resource consumption models and support for resource tagging and billing. Like any other service, public cloud platforms have limitations. This should not be a surprise or reason to dismiss them unnecessarily. As architects, we should invest the time to understand what the limitations are and architect within them when it makes good business sense to do so. We should also actively provide feedback to product teams to ensure that unnecessary limitations are reduced over time. Given that public cloud platforms are a crucible of innovation, new features and improvements are constantly being released. Architectures should not be static, but evolve over time to take advantage of future improvements. One common criticism of public clouds is that specialized or high-end resources are not available. For example, non-x86 instruction set architectures and networking communication standards other than Ethernet. In many circumstances, acceptable performance can be achieved by consuming non-specialized commodity resources at a far lower price point. That's not to say that there isn't a place for specialized hardware, though in our role as an architect, we shouldn't dismiss using a public cloud simply because we cannot find identical resources to what we can deploy on-premise. We should fully explore the different dimensions of the problem we are trying to solve and see whether we can replace complex, high-performance systems with simple, scalable, and often inexpensive cloud resources. In this video, we'll be providing an introduction to the Amazon Virtual Private Cloud, or VPC as it's more commonly known. We will start with a high-level overview of what VPC actually is and why it's useful. We will then consider a summary overview of the components that make up the AWS VPC. We'll then look at each of the components in more detail. This will include VPC subnets, internet gateways, security groups, VPC peering connections, virtual private gateways, and customer gateways. The AWS Virtual Private Cloud provides advanced networking features that allow us to isolate portions of the AWS cloud. Each VPC within an AWS account in a region is defined by a CIDR block that is contiguous and does not overlap with that of another VPC. VPCs can range in size, the largest being a /16-bit subnet mask and the smallest /28-bit subnet mask. Care should be taken when choosing a CIDR block to ensure that we will be able to take full advantage of the available address space. Refer to the VPC Design Patterns video in the series for more information on this, as well as VPC Limits section of the VPC User Guide. If we created our AWS account after the 4th of December 2013, our account only supports EC2 VPC. In this case, AWS creates a default VPC for us in each AWS region. A default VPC is simply a VPC that's ready to use without needing to configure or think about subnets, CIDR blocks, etc. If we created our AWS account before the 18th of March 2013, it supports both EC2 Classic and EC2 VPC in regions that we've used before, and only EC2 VPC in regions that we haven't. If our account was created in between these dates, then support for EC2 Classic is uncertain. It may only support EC2 VPC. The diagram shows the key components of a virtual private cloud. Let's take a closer look at each of these. The first component we will consider is a VPC subnet. A subnet is a range of non-overlapping IP addresses within a VPC and is associated with a single availability zone. Subnets can either be considered public or private, with both providing optional DHCP services for the allocation of dynamic IP addresses. We can launch EC2 resources into a subnet and restrict the flow of traffic between subnets with suitable routing and network access controls. Next, we will look at subnet routing tables. A routing table is associated with one or more subnets. It contains one or more subnet routes that control network routing between resources placed in each subnet. Routes consist of a destination, target, and propagated flag. The destination field represents a CIDR block to match against. The target specified, i.e. a gateway or elastic network interface to use to reach the destination, and a propagation flag determines whether a route should be propagated via a virtual private gateway. We will cover this a little later. Each VPC contains a default route table that's implicitly associated with subnets in the event that they are not explicitly associated with another subnet. Next, we will consider network access controls, or NACLs. A network access control is a container for stateless ingress and egress rules. Network access controls can be associated with one or more VPC subnets. Each network access control rule consists of a number that determines the relative order of the rule it is evaluated, a type, either inbound or outbound, a networking protocol number such as ICMP or IP, and a port range. As NACLs are stateless, port ranges for egress rules are usually broad to accommodate the arbitrarily high ports chosen by client operating systems. Rules also have a source or destination CIDR block as appropriate and a corresponding action of allow or deny for the given rule. We now move on to the Internet Gateway. The Internet Gateway is a horizontally scaled, redundant, and highly available VPC component that allows communication between instances in our VPC and the Internet. Public subnets should have a network route associated with them that specifies the Internet Gateway as the target for a given destination CIDR block. In many cases, this is often the default route. Now let's look at security groups. A security group provides a stateful virtual firewall for EC2 instances. Each security group consists of ingress and egress rules that restrict incoming and outgoing traffic. Unlike their EC2 classic counterparts, VPC security groups can be attached or detached from an instance after it has been launched. One powerful feature of security groups, or more specifically their rules, is their ability to refer to other security groups. This allows us to easily define a rule that allows one or more logical groups of servers, say application servers, to communicate with another logical group of servers, say database servers, by creating a database security group ingress rule that references the application server security group. We now look at elastic IP addresses. An elastic IP address is a static public IP address that can be associated with an EC2 instance in a public subnet or an elastic network interface. Elastic IP addresses can be reused or reassigned to instances within a VPC. They are typically used when an instance needs a fixed known public IP address and cannot either reside behind a load balancer or the decision has been made to manage the potential single point of failure. Next, we consider VPC peering connections. A VPC peering connection allows us to connect together two VPCs in the same AWS region. VPC peering allows for inter-VPC routing using private IP addresses. While the VPC does not need to belong to the same AWS account, they will need to have distinct, non-overlapping CIDR blocks. They are fully managed components of a VPC and therefore highly available and redundant. They are therefore the preferred option when we need to connect VPCs together. While routing between VPCs using private IP addresses is possible, transitive routing between VPCs is currently not possible. We can currently only pair VPCs together, so we need to explicitly pair each VPC that we need to communicate between. Now let's look at the virtual private gateway. The virtual private gateway is used to associate a VPN connection or AWS Direct Connect with a VPC. It consists of two distinct endpoints that, in the case of using a VPN connection, can each support an IPsec tunnel from on-premise to our VPC. In the case of a VPN connection, it may be helpful to think of the virtual private gateway as like a VPN concentrator. To enable instances in our VPC to reach a customer gateway, we must configure our route table to include the routes used by our VPN connection and point them to our virtual private gateway. We can enable route propagation for each routing table to automatically propagate routes from on-premise if desired. Similar to VPC peering connections, virtual private gateways are a fully managed component of the VPC and are therefore highly available and redundant. We now consider a VPN connection. A VPN connection itself is not a new concept or one specific to AWS. However, in the context of a VPC, it refers to the VPC component that associates a virtual private gateway with a customer gateway. It is a key component to allow us to create a secure connection from on-premise infrastructure to AWS. As a virtual private gateway provides two IPsec tunnels in distinct locations, we can utilize both of these in our VPN connection along with the border gateway protocol for dynamic routing. Now let's consider the VPC customer gateway component. Similar to a VPN connection, a customer gateway or router isn't a new term, but it does have a specific meaning in the context of Amazon VPC. On one hand, it refers to the physical or virtual device residing on-premise from which we will initiate a VPN connection. However, it also specifically corresponds to a VPC component that's used to define the type, routing protocol, and fixed public IP address of the physical device. And finally, let's consider VPC endpoints. A VPC endpoint is a relatively new feature of Amazon Virtual Private Cloud. It allows us to access AWS services from inside of our VPC subnet via a private connection. This avoids the need to send data over the public internet, which can be a little challenging to achieve in a highly reliable and scalable way from a private subnet. In general, internet access to resources residing in a private subnet would require the use of a NAT instance or application proxy server. At present, the VPC endpoint feature is a little limited in scope and doesn't provide access to all AWS services. Refer to the URL in the slide for the latest supported services. In this video, we will be looking at VPC Design Patterns. We will start by considering an approach for mapping between AWS accounts, business environments, and VPCs. We will then look at triggers for creating new VPCs and flexible, scalable patterns for VPC subdivision. We will conclude by considering strategies for inter-VPC and EC2 classic to VPC communication. Integration strategies between VPC and on-premise is covered in an accompanying video in this series. So let's start by considering the relationship between AWS accounts and business environments. The most common pattern here is to map environments such as production, staging, and development to distinct AWS accounts and consolidate each account under a master billing account. This provides a pragmatic compromise between security through strong isolation of resources and operational efficiency. Some organizations may choose to create dedicated AWS accounts for select business units to provide even greater levels of separation. For example, a finance or billing department may need greater levels of resource separation than is currently possible today using identity and access management. We can pair together pairs of VPCs that belong to distinct accounts. Therefore, using a relatively small, manageable number of AWS accounts provides for resource separation, whereas VPC peering allows for communication and sharing of services if desired. Typically, each AWS account contains one or more VPCs per region. There is a definite trade-off here between separation of resources and managing the potential blast radius of an environment. For example, consider a production environment that consists of 30 applications. While technically it would be possible to create a VPC for each, this is not operationally efficient and creates additional networking complexity and cost. Therefore, it's common for VPCs to contain a number of applications for a given business environment. For example, a production VPC may contain tens of applications before the operations team creates a new virtual private cloud. So let's imagine that we have created a VPC for our production environment. Should we place all of our production applications into it? If not, what factors influence our decision to create multiple VPCs and what impact will they have on our VPC design? Let's start off with a simple factor of geography. A VPC is restricted to a single AWS region. Therefore, if we need to place resources in a VPC in a different region, then clearly we will need to create a new VPC if one doesn't already exist. We may decide to deliberately restrict the number of applications we place into a VPC. This is to restrict the potential blast radius for an operational, software, or customer event impacting the resources contained within that VPC. This comes down to a decision of managing risk. Another important factor in the maximum size of our VPC is designing within the constraints of the VPC service. While the VPC service is constantly evolving to meet the needs of AWS customers, there are some limitations to bear in mind. In particular, the maximum number of security groups per VPC, currently set to 100, can limit the number of resources we place into a VPC if we don't think carefully about our security architecture. For example, if each application consists of 3 distinct tiers, each protected with a dedicated security group, then after deploying little more than 30 application stacks, we have reached the current service limitation. If each of these security groups only refers to a single security group in the same stack, then we can expect AWS Support to approve a request to increase this limit. If, however, each security group makes reference to a common security group such as a build server, authentication server, or monitoring security group, then it's most likely that a request to increase this limit will be denied. There are ways around this limitation, such as referring to resources by CIDR block instead of security group, or grouping together applications to reuse security groups. This of course has a potential impact on security, and therefore we will need to make a pragmatic compromise between security and manageability. With this in mind, let's imagine that the types of application we intend to place into a VPC, we estimate that we can deploy 50 application stacks before needing to create a new VPC. What size VPC actually makes sense? Remember that a /16 subnet mask provides a range for 65,000 IP addresses. A VPC should have sufficient headroom for future growth, not only for our applications, but also for future changes to AWS Service Limits. Finally, application sensitivity will often require that we create a dedicated VPC instead of placing it into an existing shared VPC. For example, PCI DSS compliant applications are often placed into a distinct VPC to other applications, as it makes them easier to audit and provides the greatest levels of separation within an AWS account. The diagram shows the essential subcomponents of a VPC that factor most strongly into a discussion of VPC subdivision. Let's take a closer look at each of them. Let's start by considering VPC subnets. A subnet is just a contiguous block of network IP addresses that we consume within an AWS resource such as EC2, ELB, or EMR. Placing resources into subnets allows us to logically group together and manage resources in blocks such as controlling their routing or stateless network access controls. We use subnets in AWS in a similar way to how we would use them on-premise, so the same design best practices still apply. Our VPC architecture should have a high degree of symmetry across 2 or more availability zones. This provides for geographical redundancy and is a key element of architecting for availability. As AWS subnets are restricted to an availability zone, our subnet design should possess a high degree of symmetry between availability zones within a region. Subnets can either be public or private. One of the biggest benefits of the VPC over EC2 Classic is being able to protect resources and place them into a private subnet. We should therefore restrict the number of public subnets to a small number. They will typically be restricted to DMZs and public ELBs. Web servers can and should be placed safely in a private subnet. One area that's often overlooked is placing adequate security controls over network subnets. While security groups provide stateful controls, ignoring NACLs means that we have removed a coarse-grained but valuable first line of defense from our architecture. That being said, managing large numbers of subnet NACLs in addition to security groups is an operational burden. There is, however, a pragmatic compromise here. At the very least, we should invest the time to design and manage NACLs for the outermost tiers and the boundary from outer to innermost tiers. This can often reduce operational complexity by an order of magnitude while still allowing us to benefit from increased control in the areas that matter most. Now let's consider best practices for allowing resources in EC2 Classic and VPC to communicate. Communication via the internet is straightforward, assuming that we have the appropriate access configured. The main focus of what we will look at here is how we can enable communication via the private IP addresses, therefore avoiding traffic going over the public internet or at least out to the edge of the AWS network. The first and generally accepted approach is to use EC2 Classic Link. The most significant distinction between EC2 Classic linking and VPC peering is that once EC2 Classic is linked to a VPC, transparent routing is not automatically configured for all EC2 resources in EC2 Classic. We still need to enable linkage on an instance-by-instance basis. Classic Link can only be enabled between VPCs belonging to the same AWS account in the same region. Each EC2 instance in the Classic environment can only be linked to a single VPC at any given time. EC2 Classic is a helpful solution during the transitionary period, migrating resources from EC2 Classic to VPC. It is particularly useful for organizations that already have a significant deployment footprint in the old EC2 Classic environment. In the case where we cannot use EC2 Classic Link, for example when linking between different AWS accounts or different regions, then we may need to consider other options, such as potentially using a software VPN solution or using Direct Connect as a routing link. This is not a common requirement, so we should think carefully before proceeding with such a solution. Now on to the more common requirement for private communication between multiple VPCs. For example, needing to communicate between a shared services VPC and a production or development VPC as shown in the diagram. AWS allows us to peer together pairs of VPCs by defining a VPC peering connection. VPC peering connections can be used for VPCs belonging to the same or different AWS accounts. This provides significant flexibility during the design process when considering our account to VPC mapping strategy. We can still use a software VPN solution to peer together VPCs, but the reasons for doing this are somewhat limited, and it's generally considered an anti-pattern when the VPCs are in the same region. One reason why we may want to use a software solution is for traffic inspection. This obviously introduces a single point of failure and network bottleneck, so this is not a solution that we should fold into our architecture or design without a compelling reason to do so. Furthermore, the introduction of VPC flow logs means that if our primary goal is to inspect logs, then there are more elegant ways to do this. VPC peering connections are currently restricted to one-on-one connections. Therefore, we will need to explicitly create point-to-point VPC peering relationships for each VPC. While we should use security group rules with source and destination targets consisting of other security groups, peering will require a slightly modified approach, as security groups are not recognized across VPCs. We will therefore need to refer to source and destination resources by CIDR blocks, and not by the security groups that they may belong to. Transitive routing is currently not supported. Just because a VPC is individually peered with two other VPCs does not mean that private network traffic will be able to be routed directly between those two other VPCs. This is generally not a design challenge, but can lead to more VPC peering connections to manage than we may ideally desire. The remaining design considerations shouldn't be a surprise. We cannot peer together VPCs with overlapping CIDR blocks. This would only be a potential issue when looking to peer together VPCs belonging to different AWS accounts, and is a good reason for taking a holistic approach to network design within an organization. The last consideration is that VPC peering connections only refer to VPCs in the same region. There are some strong operational and security reasons why we may want to limit coupling of resources between AWS regions. While it's becoming increasingly common for us to take advantage of AWS cross-regional features for data movement and replication, we don't need to peer VPCs in order to take advantage of this. If we must peer between AWS regions, then either a software VPN or a WAN-based routing solution together with AWS Direct Connect would be a way to achieve this. This is not a common design configuration, so we should think very carefully before implementing such a solution. And finally, we come to how to achieve private communication between resources in a VPC and AWS service endpoints. This is an area that AWS has recently been working on, and with the introduction of VPC service endpoints, we now have the ability to provide access to a specific AWS service via a private, fully managed link. Currently, support is limited to a subset of AWS services, but when possible, using this VPC endpoint link provides real benefits over using a NAT or application proxy service. As previously discussed in other videos in this series, designing a redundant, scalable, and elastic application proxy tier introduces operational cost and complexity. In this video, we will be looking at integration strategies between on-premise IT and AWS. We will start by looking at integration strategies that use a software VPN solution, then move on to using hardware VPN solutions with varying degrees of redundancy. Next, we will consider AWS Direct Connect, once again with different levels of redundancy. We will conclude by looking at a hybrid solution using both AWS Direct Connect and a hardware VPN solution. A software VPN is the simplest and cheapest solution to integrate on-premise with AWS. Using one of a number of available software VPN solutions, such as OpenVPN, we can create a VPN gateway or concentrator on an EC2 instance residing in a public subnet. The instance should be on a Bastion host with appropriate security hardening performed. On the client side, we can either install the respective VPN client software and certificates on hosts requiring access to the AWS environment, or set up a site-to-site connection via a suitably configured client-side router. A software VPN is often the solution used by teams requiring access to a small AWS footprint. It is also sometimes used as a temporary solution until a more reliable solution can be implemented. using an SSH jump host or similar can often be a useful alternative. However, as our AWS environment becomes more complex, especially with multiple subnets, having to hop between the jump host makes access a little inefficient, and therefore a software VPN quickly becomes the preferred option. There is also a single point of failure and potentially a performance bottleneck, namely the EC2 VPN gateway. Furthermore, software VPNs can be less reliable than hardware-based solutions. The next option we will look at is a hardware VPN solution. AWS supports a number of hardware VPN solutions. Refer to the VPN Administrator Guide for full details of supported devices. A hardware VPN solution consists of the following AWS VPN components in addition to the physical VPN device. It consists of a customer gateway, a virtual private gateway, and a VPN connection. An AWS VPN connection consists of two IPsec tunnels. While using both tunnels is not required, it clearly provides redundancy in the event that one of the tunnel termination points fails. There is one tunnel termination point per availability zone, thereby eliminating a single point of failure. When using both tunnels, we should configure BGP routing on the client-side router to allow for transparent failover in the event that an IPsec tunnel fails. While a hardware VPN is more expensive and often more complex to set up than a software-based solution, it provides a number of benefits, such as increased availability and often increased stability and reliability. AWS's Virtual Private Gateway is a fully managed and redundant AWS component and doesn't impose the same networking throughput constraints of a software VPN gateway running on an EC2 instance. While the VPN solution of the previous slide is redundant on the AWS side, it's not redundant on the client side. This can be easily fixed to provide greater levels of redundancy. We simply need to create an additional customer gateway and a VPN and associate these with a secondary VPN device potentially located in a secondary location to the first VPN device. Now we have a total of 4 IPsec tunnels and can therefore tolerate failure of either one of the pair of VPNs or virtual private gateway tunnel termination points. This is a good solution for customers with strict SLAs against their on-premise to AWS connectivity. Next, we consider AWS Direct Connect. Unlike a VPN solution, AWS Direct Connect provides a point-to-point connection between a rack in a Direct Connect peering location and AWS. We can either place a router in one of these locations or use one of the AWS partners to provide this service. AWS Direct Connect provides greater consistency of network connectivity than a VPN solution and can provide a more economical connection than transferring data over the public internet. It is therefore a common choice for larger commercial and enterprise customers. However, as it is a point-to-point connection, we should complement a primary link with a secondary link, often with a reduced network capacity. For customers that require increased levels of availability and consistency, then redundant Direct Connect links configured together with BGP provide a resilient connection strategy between on-premise and AWS. However, in the case where the Direct Connect peering locations are the same physical location, this could introduce a single point of failure. Therefore, when possible and when supported in region, we should use distinct Direct Connect peering locations to provide the greatest levels of availability. In the event that distinct Direct Connect peering locations are not available within a region, or we simply want the highest levels of availability, we can combine both Direct Connect links with a redundant, highly available VPN connection. This solution is the most complex and costly of each of the solutions we have considered in this video so far, but provides the greatest levels of availability and throughput with the smallest, most consistent latency. In this video, we will be looking at how to estimate the availability of applications deployed on the AWS platform. We will start by looking at what availability is and how it relates to an SLA. We will then take a look at the availability of AWS Web Services and highlight some key differences between resources and the services that provide them. We will then look at 2 formulas for helping us estimate effective availability and work through a simple example, along with assumptions assumed during the estimation process. We will finish up by summarizing the key design decisions. Let's start off by considering what availability is. While there are a few different formulas for calculating the availability of an individual component, fundamentally, they are all similar. It corresponds to the ratio of the total time a system is capable of functioning correctly and the interval of the time of measure. When architecting for the AWS platform, a common design requirement is to achieve a particular service level availability, or SLA. This is particularly common when the system provides an external-facing service with an associated service contract. Estimating the expected availability of a system is nothing new. Many of us have performed the task a number of times with on-premise systems. However, even organizations that have adopted a highly virtualized environment still consider compute and services as virtual resources and not web services. We are used to reasoning about the availability of servers or disks and not virtual resources resulting from one or more web API calls. While some AWS web services provide durability or annual failure rate figures, in the main, measures of availability are restricted to web services. This can complicate the process of estimating availability. However, with a few simplifications, assumptions, and historical data, we can use techniques for estimating availability and map them to the AWS platform. There is a subtle but important difference between an SLA and availability. The former is a contract based on an estimate of the expected value of the latter. While an SLA should be indicative of the expected availability, the degree to which they are coupled is a business decision. SLAs are often accompanied by service penalty tokens as a means to compensate customers when an SLA is not met. The expected availability is therefore typically higher than that referenced in the SLA, to a level proportional to the confidence of the service provider in being able to meet the SLA. While it's possible to achieve higher levels of availability using one or more services or components, we should take great care, especially when providing an SLA to our customers. We need to clearly understand the dependencies and assumptions, more so if the SLA is a contractual agreement with associated service penalties. The first thing to be mindful of when estimating availability is the distinction between the SLA of a web service and a resource created by that service. For example, the SLA of the Amazon EC2 web service is not a measure of the availability, durability, or failure rate of a single EC2 instance, but rather it refers to all of our EC2 resources. The SLA of each AWS web service is a policy governing the use of the web service under the terms of the AWS Customer Agreement. The terms of the SLA are set out in the Service Commitment section of each web service. The web service SLAs are clearly stated on the AWS website. We should take the time to read them carefully to fully appreciate the scope and in particular the definition of items referred to in the SLA. Depending on the nature of the web service, the nature of availability can be quite different. Furthermore, it is possible for the definition to change over time, of course with suitable notification from AWS. While some web services may be accompanied by durability and annual failure rate guidelines for resources they create, we should build up our own estimates for resources over time to improve our models. With a few assumptions that we will cover shortly, we can estimate the availability of a system consisting of a number of components in series and in parallel by applying a few simple rules. Rule number 1, in series rule, if a system requires that each of its n components be available in order to be classed as available, then the effective availability is the product of the availability of each component. Rule number 2, in parallel rule. If a system requires at least one of its n components to be available in order to be classified as available, then the effective availability is 1 minus the product of the probability of failure of each component. Put another way, the system will fail only if every component fails. Let's take a look at a simple example to help our understanding. In this example, we have a simple three-tier architecture consisting of an AWS Elastic Load Balancer, a pair of web application servers, and a highly available deployment of the AWS Relational Database Service. While the AWS ELB service does not have a published SLA, provided that we configure it to be able to distribute load across multiple availability zones, and given it's a fully managed service, we will estimate the availability to be that of the EC2 service, currently 99.95%. Next, we have a tier of web application servers running on EC2. While the SLA of EC2 is 99.95%, and that may be a sensible starting point to estimate the availability of an EC2 instance, purely from a resources perspective, tests have shown that the availability of each of our application and web servers is dominated by the availability of the application. Therefore, we estimate the availability to be 95%. Finally, we have a highly available deployment of RDS. This is estimated to be 99.95%, as defined in the SLA section of the RDS website. Let's simplify the web application tier by calculating the combined effective availability. As the components are in parallel, we use rule number 2. This provides us with an effective availability of 99.75%. Then, let's reduce the remaining 3 components using our in-series formula or rule number 1. This provides an estimate for the overall system of 99.7%. While this video is about how to estimate availability, it seems appropriate to mention how we can increase it. Firstly, we can make each of the individual components more reliable. We can't alter the availability of the underlying AWS web services, but we can use them in a way that maximizes availability. For example, using RDS in a multi-AZ deployment or distributing resources between availability zones. Therefore, we should always follow best practices when consuming each service. Based on rule number 1, it suggests that systems with fewer components will result in higher availability. At first glance, this appears to be in conflict with a move towards a microservices architecture. It's not. What we typically find is the individual availability of microservices is greater than that of a large monolithic surface. When we consider the product of each individual service's availability, it's still higher than a single complex service. Increasing the number of redundant components in parallel, as per Rule 2, brings clear availability benefits, as we have seen in the example. This is an effective way to build highly reliable systems using unreliable individual components. We have needed to make a number of simplifications to reason about availability. Let's take a look at them. Firstly, in the case of the ELB, we assume that its availability is 99.95%. This is not explicitly stated in the AWS website, but provided it's configured for multi-AZ load balancing, configured to route traffic between availability zones, and given it's a fully managed service, this is a sensible starting point. Over time, we may decide to modify this figure based on our own operating metrics. However, caution should be taken on expecting or relying on it, at least from a contractual perspective, to be any greater. Next, we estimated the availability of the web application server to be dominated by the application web stack, rather than the underlying EC2 resources. We could of course estimate the availability of an individual EC2 instance and combine it with the availability of the application using Rule 1, but we would expect the infrastructure resources to be more reliable than software. We are also making the assumption that the availability of one application web server is independent of the other. This is reasonable given the size of the AWS platform, but we should distribute our resources across multiple availability zones to strengthen this assumption. We are also making an assumption that the availability of an EC2 instance is independent of the instance type. We may find that our metric data suggests that the larger EC2 resources are more reliable than the smallest instances, and therefore our model isn't as accurate when using very small instance types. We are making the assumption that the additional load created by the failure of one or more resources in parallel will not result in the system being unavailable. Related to this, if we assume the remaining resources can provide a reduced level of service for a short period of time while the resources are being replaced, say by autoscaling, then they can be replaced quickly enough not to result in overall failure. The services are assumed to have synchronous dependencies. For a web application providing a single service, this is a reasonable assumption. But as systems become more complex and are able to handle asynchronous calls, we can tolerate temporary failure of an individual component without affecting overall availability. It's easy to get bogged down searching for a way to perfectly model a system. We should start off by taking a simple approach, clearly stating our assumptions, and refine both the model and estimates over time as we collect more and more operational data. We can then revise our models when planning new systems or consider modifying existing SLAs. When architecting for a platform, SLAs should be driven by sensible business reasons. We can create highly resilient architectures on the AWS platform, but as we chase higher and higher availability, costs and complexity will increase. Before designing a system, start by asking whether the SLA makes business sense, and speak with the respective business owner about the cost-complexity equation. We should use AWS Service SLAs as a guide to availability and complement actual availability statistics into our modeling over time. We should invest sufficient time thinking about how systems will be managed and designed for operational flexibility. If we require a 1-hour outage every month in order to patch and upgrade our systems, then this will erode our attempts to maximize availability. The virtues of architecting for scalability have significant implications on availability, especially when components are considered unreliable. Even if we can comfortably run an application on a single EC2 instance, we may choose to use multiple smaller instances in order to increase availability. We need to carefully consider the economic model of over-provisioning in order to reach an estimated availability. Autoscaling is a valuable tool to grow resources in response to changing load. But can it replace resources that fail quickly enough to meet the highest levels of availability? We may need to underutilize resources in order to accommodate large step changes in load resulting from the failure of one or more instances. This, of course, needs to be folded into our SLA and service costs. Architecting for availability should not just be focused at the infrastructure or platform level. The application could be the dominant factor in reliability, so efforts to increase availability should be invested in areas of greatest yield. If an application component has an availability of 70%, it will dominate our system's availability unless we can offset it with a significant number of components in parallel. If we are chasing the very highest levels of availability, the illustrious 5 nines, then while it's possible to achieve this in a single region, trying to substantiate an expected availability would be challenging, even for the simplest of architectures running in the largest of AWS regions. For this reason, if we need to achieve anything greater than 99.95%, it would be prudent to architect across regions. In this video, we will be looking at the importance of geographic distribution of resources in order to achieve increased levels of availability. We will start by looking at what is meant by geographical distribution of resources from the perspective of the AWS platform. We will then look at some common geographical terms used when referring to AWS services and resources. Next, we will highlight how different web services and their resources are geographically related to the terms we've just introduced. We will then consider geographical implementations when choosing consumption models and wrap up by pragmatically looking at distributed resources across multiple regions. The AWS platform currently spans 5 continents. There are a number of reasons why we may choose to take advantage of geographically distributing our AWS resources, including reducing latency of services to our customers, data regulatory requirements, and to increase the availability of applications and systems. This video focuses on the geographical distribution of resources to increase availability. Let's start by considering some AWS definitions often associated with the geographical location. The first is an AWS region. AWS has a number of regions distributed around the globe from which they can provide web services such as EC2. Each region is a separate geographical area that is independent to other regions. Each region consists of 2 or more isolated locations referred to as availability zones. While isolated, availability zones are connected via a low-latency network interconnect. AWS has a number of edge locations distributed across the globe. These locations are currently used to support the AWS CloudFront service, thereby allowing data to be cached at the edge. The last entity that we will mention is AWS Direct Connect locations. These are physical locations allowing us to establish a dedicated network connection from our existing data center to our AWS environment. Each of the AWS web services creates resources that have a particular affinity with one or more of these entities mentioned in the previous slide. If we are to improve the availability of our systems, we need to understand the extent to which they are dependent on location. There are 3 different levels of dependence. First, we have services that are global in nature and allow us to control resources associated with multiple AWS regions. Examples of such services are the AWS Identity and Access Management Service. IAM is said to be global because resources such as IAM roles can be defined centrally but associated with principals residing in any of our AWS regions. The next type of service are ones that have resources that are regional in scope. For example, Amazon S3 buckets and objects belong to a region, while a suitable S3 bucket policy, access control list, or role policy would allow us to access an S3 resource from anywhere in the world. The service and resources are provided by S3 from a given region. While web services can have regional affinity, some resources created by the web service can be associated with a specific availability zone. Amazon EC2 instances and EBS volumes are examples of such. AWS publishes guidance on durability of some resources such as the average failure rate of an EBS volume, but web service SLAs are the best guide to the expected availability of a service. We have already heard that availability zones are isolated locations within a region. Therefore, by distributing our resources between or across availability zones, we will benefit from increased availability at an individual resource level with only a small additional amount of latency to deal with. Deploying resources multi-AZ and running systems in an active-active configuration is the preferred and normal operating position in the cloud, and is the first logical step to improving the availability of an application or system running in a single availability zone. Internet connectivity is typically provided directly by an Internet Gateway device in our VPC. This is a virtual network construct provided by AWS and is redundant within a region. However, resources requiring access from private subnets will either need to reach the Internet via one or more of a NAT or proxy server. Either that, or they will need to be routed via a VPC or direct connect link back to our current data center. We should note that NAT instances are not highly available by default. It isn't a managed service like the Internet Gateway, but it's provided by an EC2 instance that we are responsible for. AWS do provide guidelines for making a NAT instance highly available, but it relies on a two-node cluster, with each node performing health checks on the other node and each node having the permission to modify subnet routing in the event of failure. Two-node clusters can be unreliable in the event of a split-brain scenario. For these reasons, it's common to use a highly available proxy solution for outbound internet access. It also provides for easier scale-out over the NAT solution. Finally, we should consider distribution of or redundancy of the direct connect link. AWS provides multiple locations in each AWS region, allowing us to configure a backup direct connect connection. This will safeguard in the unlikely event that a direct connect location is unavailable. AWS provides a number of resource consumption models. One model is to reserve capacity, thereby allowing us to benefit from a reduced effective hourly consumption rate and greater commitments around AWS resources such as EC2 and RDS. When reserving EC2 instances, we need to specify the AWS availability zone the resources will be in. We are therefore now establishing a level of coupling between resource commitments and of availability zones. While it's possible to later sell or exchange reserved instance capacity, we should be mindful of how reserved capacity is distributed throughout our availability zones in a region. We will typically want to distribute reserved instances evenly through each of the availability zones we use. While availability zones are isolated, they are still connected, and therefore there is the potential for disruption of services within a region to affect resources in more than one availability zone. Given AWS's size and experience operating at scale, these events are rare, but possible nonetheless. As AWS regions are independent from each other, shouldn't we simply use multi-region architectures to increase availability? Architectures spanning multiple regions are becoming more common, but mainly to provide business continuity. While it is possible for applications and systems to run active-active across multiple regions, the increased latency, not to mention the additional cost and operational complexity, provides challenges at the data tier of our architecture, often leading to making data eventually consistent. A number of large internet-based companies such as Netflix have published engineering blog posts on how they've implemented active-active cross-regional systems on the AWS platform. As architects, we should be inspired by their innovation and be ready to incorporate their ideas and designs into our own environments, but only when it provides tangible business benefits. In this video, we will be looking at how we can achieve highly available internet connectivity on the AWS platform. We will start by covering the scope of this video, then look at how we can provide internet-based access to resources utilizing either AWS Direct Connect or an IPsec VPN connection. We will then look at how internet access is provided directly from an Amazon VPC, and then look at two popular approaches for supporting outbound internet connections. We will then conclude by reviewing the key design considerations. It may seem a little strange that we are even considering this topic, how to provide a highly available internet connection on the AWS platform. The AWS platform is accessed via the internet, and AWS go to great lengths to ensure internet connectivity is highly redundant. With the introduction of the Amazon VPC Virtual Private Cloud, we were able to separate resources into different subnets and control access between them using a combination of stateless NACLs and subnet routing. VPC allows us to control access to resources via the internet using a combination of subnet routes, NACLs, and security groups. Internet access is typically provided by way of an Internet Gateway virtual resource. Most of the challenges and architectural complexity comes from providing highly available outbound connections from resources in private subnets. This will be the main focus of this video. While we can potentially connect to our AWS resources directly over the public internet, for example via a Bastion host or a software VPN solution, this is typically used for smaller customers or consumers for which the additional cost of using hardware-based connectivity solutions isn't economical. As the number of applications we deploy or have the intention of deploying on the platform increases, we should explore either one or more redundant IPsec VPN connections, or for the highest levels of consistency and connectivity, AWS Direct Connect. Both AWS Direct Connect and an IPsec VPN connection allow for multiple redundant connections within an AWS region. However, for the greatest levels of availability, we should consider using two distinct direct connect locations within a region to safeguard against failure. Both an IPsec VPN connection and a direct connect connection to our AWS environment are plumbed in via a virtual private gateway, a virtual network construct that we can associate with a VPC. A virtual private gateway is a redundant component. Therefore, provided we ensure our IPsec VPN connection or direct connect connection are redundant, we will have a reliable, highly available link to our VPC from on-premise. Now let's consider internet access from inside of a VPC. As we noted on the previous slide, we can use the direct connect or IPsec VPN connection, assuming that we have suitable routes associated with our VPC subnets, and we can route to the internet from our external connecting location. But what if we need internet access without either of those possible connections? If a resource residing in a public subnet has a public IP address associated with it, it can access the internet via an internet gateway. Similar to the virtual private gateway, this is a virtual network construct associated with a VPC. It's redundant and managed transparently by AWS. All we need to do is attach it to a VPC and use it. If our resources reside in a private subnet, they cannot route directly via an internet gateway. We will either need to route via a network address translation or NAT instance, or an application level proxy, such as the Squid proxy server. As both of these services are provided by EC2 instances, it is our responsibility to make them redundant or risk a potential outage for outbound connections from a private subnet. Before we look at how to implement a NAT or proxy server in a little more detail, it's important to note that currently, with exception to S3, AWS services are not accessible via a private network connection in a VPC. We must provide access to the internet for all API calls. This is sometimes initially overlooked when considering whether we need a NAT or a proxy instance. Over time, this limitation will no doubt disappear as the VPC endpoint feature provides support for more AWS services. Network address translation for resources residing in a private subnet is achieved using an EC2 instance. While we can develop our own NAT instance AMIs, AWS does provide a selection of ready-made AMIs with names similar to Amazon-AMI-VPC-NAT. We can search for the AMI in either the AWS Management Console or CLI tools. Detailed instructions on how to set up a NAT instance can be found in the latest VPC user guide. However, the salient points are these. The NAT instance should reside in a public subnet with appropriate NACLs allowing traffic from each subnet that needs to initiate outbound connections. By default, an EC2 instance only has visibility of traffic addressed directly to it, even if its network interface is placed into promiscuous mode. In order to see packets that should be routed, we need to disable source and destination checks associated with the EC2 instance. This is not an OS property, but rather a property of the EC2 instance and is configured via the AWS Management Console or EC2 API. Once our NAT instance is configured, we can then specify one or more routes associated with private subnets with the instance ID, thereby instructing those resources to send outbound initiated network traffic through the NAT instance. In the case where traffic is part of an existing established connection, for example, a web server residing in a private subnet and an ELB in a public subnet, the traffic will be routed via the ELB and not the NAT. The problem with a NAT instance is that each subnet needing to route through it must have a route containing the NAT instance's ID. Therefore, even if we could tolerate a small outage in the event that the NAT fails, we can't simply use auto-scaling to replace it, as the instance ID will change. We also need to update routing table entries. While this is possible, it is an additional step that we need to take and to manage. AWS provides a useful article describing how to create a highly available NAT solution. It consists of a pair of NAT instances configured in a basic 2-node cluster in an active standby configuration. Each node in the cluster monitors the other node and performs a basic health check. In the event that the standby detects that the primary has failed, it promotes itself to the role of master. For those of us who have experience with 2-node clusters with basic unsupported monitoring scripts, we know that split-brain scenarios where both nodes believe that they are the master can result in operational challenges. The highly available NAT solution will provide greater protection from failure than a single NAT instance, but we should consider whether a NAT instance is actually required. Consider scaling challenges, that is the maximum throughput that a NAT instance can support, and operational challenges around running clusters with simple management scripts. If we need to proxy application-level traffic such as HTTP from private subnets, then deploying one or more proxy servers has a number of benefits over a NAT instance. Let's take a closer look at how we might achieve this. Firstly, we need to configure a suitable proxy server in a public subnet and associate it with a public IP address. The proxy server will then consequently make outbound connections to the internet via the Internet Gateway, similar to how a NAT instance would. However, instead of configuring transparent network routing as we did for the NAT instance, we will place one or more proxy servers behind an internal elastic load balancer and configure hosts to use the ELB as an HTTP proxy. Furthermore, by using an ELB to decouple clients from our proxy server or servers, we can use autoscaling to transparently scale in and scale out our group of proxy servers in response to operational load and proxy failure. As routing is at the application level and the endpoint is an elastic load balancer, we do not need to modify network routes in the event that a resource fails. AWS has developed a detailed and useful tutorial describing exactly how to configure a highly available proxy component. It's located at the URL shown in the slide. The main challenge around architecting highly available internet connectivity is for outbound initiated connections. Provided we are using public elastic load balancers or instances with public IP addresses, either automatically assigned or via a fixed elastic IP address with suitable subnets, routing tables, and access controls, resources will automatically have highly available internet connectivity. As most AWS services are not currently accessible via a VPC endpoint, we should assess whether our resources need API access to AWS services and plan accordingly. When using an IPsec VPN connection or Direct Connect, we need to ask ourselves, is there a compelling reason to direct internet traffic via one or more of these links? Ordinarily, this is no, but factors such as the cost of internet bandwidth and wanting to use existing investments such as firewalls, IDS, IPS, etc. may factor into this decision. Resources residing within public subnets can access the internet via an internet gateway attached to the VPC. This is highly available and fully managed by AWS. This, however, should not be a reason to place resources in public subnets for the same reason that we restrict resources placed in a DMZ on-premise. Before placing any component in a public subnet, even with suitable NACLs and security groups, we should consider the sensitivity of the data or service and resources that it provides. As we have seen, access to the internet for resources residing in a public subnet is usually provided by either a highly available NAT or highly available proxy configuration. While a highly available proxy provides greater resilience to failure, the ability to scale out and meet additional demand, it is restricted to application-level traffic and requires client-level support and configuration. In most cases, we only want to proxy HTTP, HTTPS traffic, and therefore an application proxy is just what we need. However, if we need to proxy traffic transparently to clients or provide support for protocols not supported by the proxy, then we should consider the highly available NAT and acknowledge scaling and availability challenges. In this video, we will be looking at how to design self-healing architectures on the AWS platform. We will start by looking at what we mean by self-healing systems, then consider the extent to which self-healing or automated replacement of resources varies between different AWS services. We will then look at the EC2 autoscaling web service and explore why it's the foundation of self-healing systems on the AWS platform. We will wrap up by considering gray failures and reviewing key design considerations. Let's start by defining what we mean by a self-healing system. Self-healing is the ability of a system to automatically replace one or more of its components in the event that they fail. For example, the ability to detect that a web server behind a load balancer failed a predefined health check and replace it without operational intervention. There are a number of benefits of self-healing systems. The first is that they offload operational tasks, thereby allowing our teams to focus on the other activities. By automating a process, it takes a human out of the reactive side of the equation. This leads to fewer operational errors and faster reaction times. Collectively, this helps us minimize downtime and create highly available systems. The self-healing properties of AWS Web Service resources, not the web services themselves, varies by service. AWS clearly documents what you can expect from the services, but let's take a look at a few services to highlight this. Let's start with Amazon Elastic Compute, EC2. Instances of this service, that is, compute instances, are not self-healing in and of themselves. We can configure external services to replace them if they fail, but this is not an inbuilt property of the service. Next, let's consider Amazon Elastic Load Balancer, ELB. When we consider a conventional load balancer, we probably think of a pair of load balancers in active-active or active failover configuration. An instance of the ELB service conveniently hides almost all of the underlying load balancing components from us. We just see additional IP addresses being associated with the ELB canonical name. If the resource behind one of those IP addresses fails, it is replaced transparently. We don't need to concern ourselves with failover or replacement of resources. Then we have services like the Amazon Relational Database Service, RDS. Here, we have the option to create a self-healing multi-AZ instance. The service is designed to detect failure of a master or primary instance and fail over to the secondary within 1 to 2 minutes. With AWS Lambda, we only need to create our Lambda functions, and the Lambda service will help ensure that the platform executing them remains available and performant. The list goes on. However, one more service that is critically important when developing self-healing systems is EC2 autoscaling. Let's take a closer look at this service. As with all AWS services, EC2 autoscaling is available via the AWS command line interface, via a web-based API, or the AWS Management Console. It allows us to control the scale out or addition of compute resources, or the scale in or removal of those resources, based on a number of scaling policies that we define. The autoscaling service consists of 3 main components, namely a launch configuration, autoscaling groups, and policies. Let's take a closer look at each of these resource types from the perspective of availability and development of self-healing architectures. The first component of autoscaling that we will look at is a launch configuration. This is where we specify the Amazon machine image, region, instance type, etc. Let's take a closer look at elements that have the greatest impact on availability. There are a number of AMIs available on the AWS website. We should use AMIs managed by trusted and reputable organizations, or risk the potential for running unstable operating systems or platforms that may adversely affect availability. There are a huge selection of EC2 instance types that include varying CPU, memory, storage, and I/O profiles. The very smallest instance types have the greatest variability in performance, which may be a contributing factor towards availability, especially if we become overly reliant on CPU bursting or have very little free memory during normal operating conditions. If our applications can benefit from spot market resources, huge operational cost savings can be made. Spot instances are not suitable for all workloads and often require additional effort to manage the state of longer running workloads. When using Spot, we should assume that resources can and usually will be removed at a moment's notice. AWS provides the greatest level of commitment to provide instances when purchased as reserved instances. We should reserve adequate capacity to ensure that we have sufficient resources in times of peak demand, not just as a cost reduction OpEx-CapEx mechanism. The next scaling component of interest is autoscaling groups. Group limits restrict the maximum and minimum number of EC2 instances that can exist within an autoscaling group. While we should place a sensible upper limit to avoid unlimited resource usage, we should have a generous amount of headroom to guard against unexpected spikes in traffic and potential software updates that have unexpected demands on resources. Even if our application is static from a load perspective, autoscaling groups still provide a very useful feature. We can use them to automatically replace failed resources. For example, we could set the minimum level equal to 2 and the maximum level equal to 2. we want to evenly balance resources across multiple availability zones to protect against the unlikely event of a disruption to a service in an AZ. The health check grace period is the time taken for health checks to be performed on an instance after launch. While reducing this value can result in getting resources into service sooner and therefore provide real work, making it too small could result in an instance being deemed as unhealthy and actually extending the time to perform real work. We should tune the grace period as we better understand the bootstrapping performance of our autoscaling group resources. While it's more of a cost allocation consideration, associating meta tags with the autoscaling group resources helps ensure that they are not removed by a janitor service or an admin seeking an orderly and labeled environment. The final component of autoscaling is the autoscaling policy. There are 3 types of scaling policy: manual, scheduled, and trigger-based policies. Used correctly, each of these can help us increase availability. While trigger-based scaling is a common configuration, for the purpose of illustrating self-healing architectures, we don't actually need to define one. We just need autoscaling to ensure that the number of resources stays within a given set of limits. Scaling down too aggressively can potentially result in too few resources or the inability to effectively handle a subsequent quick surge in load. For this reason, we should scale down less aggressively than we scale up. Let's take a look at how to configure a launch configuration and autoscaling group for the AWS Management Console. First, we log in and navigate to the autoscaling section. Located within the EC2 Service tab, we select Create Autoscaling Group. As we currently don't have any launch configuration groups, we first need to create one before we can create an autoscaling group. We choose an Amazon Linux Amazon machine image to base our EC2 instances on, and a T2 micro instance type. We give our launch configuration the name AWS-demo, then select the default storage options. As we will place the autoscaling resources behind a load balancer, we select the security group associated with the load balancer when defining a security group rule. Finally, we review and create the launch configuration. Now we are able to create an autoscaling group. We give it the name AWS Demo, specify the size of the group, in this case 2, and choose the VPC and subnets we want the autoscaling group to create resources in. Then specify the ELB we want to automatically associate resources when created. While we can use metric-based triggers, the focus of this video is self-healing, and therefore we just want our autoscaling group to maintain a fixed number of resources. After a final review, we are now ready to create the group. If we now change to the EC2 dashboard, we can see that 2 EC2 instances are in the process of being initiated. Let's terminate one of the instances to confirm that autoscaling will automatically replace it. As we can see, the instance is now shutting down. And shortly afterwards, we can see that another instance has been launched to take its place. The easiest types of failure to deal with are those when a component has failed completely. That is, an application server is inaccessible from the network or a web server no longer serves content via HTTP. A more challenging type of failure to deal with are partial or grave failures. For example, increased error rates or latency from a web service. Coverage of how to address grave failures is too complex to cover in this short video, but there are a number of great references available online. Not to mention guidance from AWS on handling error retries with exponential backoff. This takes us on to the final point, the so-called thundering herd. As the ability of our system to handle load is impacted, we need to consider traffic shaping to avoid components operating at full capacity, overloading those that are in a gray state. We need to be able to push back on the herd to prevent it causing a complete outage. There are a number of great blog posts on this topic, with the Netflix engineering blog being a good place to start. The effort required to develop a self-healing system can vary from minimal, simply placing a resource within an autoscaling group, or complex, including traffic shedding and shaping techniques. Our approach should be driven by the SLA associated with the service we are architecting. When architecting for the AWS platform, we need to understand the self-healing properties of services we consume. A great number of the services automatically will replace failed resources transparently with no additional effort required on our part. As the operational overhead of making components highly available takes considerable effort, for example, managing our own highly available relational database with a synchronous replica in another region, we should look for opportunities to consume higher order AWS services such as RDS when possible. However, the closer we get to infrastructure as a service like services such as compute and storage, we need to take on more of the responsibility of replacing failed components. Using a combination of autoscaling, CloudWatch, and the ELB is a common design pattern across most highly available architectures. It may take some tuning of our health checks to get self-healing operating effectively, but collectively they are a very powerful combination and will form the backbone of a self-healing architecture. In order to make one or more of our components self-healing, we need to invest time in our operations and orchestration tools. Having the ability to replace a running instance with another will require that either we have a repeatable bootstrap process where we can take a base AMI, launch an instance from it, and configure the instance during the boot process, or have a continuous delivery pipeline where we pre-bake our AMIs and automatically update autoscaling resources to reference the new Amazon machine image. Finally, we should ensure that we have sufficient error handling within our application to handle partial or grave failures. For larger environments, we may consider using traffic shedding or shaping techniques between components to protect against thundering herd scenarios. In this video, we will be looking at decoupling components on the AWS platform. We will start by discussing what decoupling means within the context of AWS, and then look at what most consider the antithesis of decoupling. We will then look at a few examples of how we can make web service architectures less tightly coupled, using a combination of Amazon ELB, Amazon SQS, and Amazon SWF. We will conclude by reviewing the key design considerations when architecting decoupled systems. Loose coupling is not a new design principle. We can trace its origins to service-oriented architecture, or SOA, and object-oriented design. From a software perspective, loose coupling is a design principle that is applied to services in order to ensure that the service contract is not tightly coupled to the service consumers and to the underlying service logic and implementation. When components are decoupled, they are easier to scale and make the overall system more reliable. Loosely coupled systems, while often consisting of additional components to tightly coupled systems, are easier to manage and evolve. Provided that we adhere to various service contracts or interfaces, the function of the service or component can be treated like a black box. Let's illustrate the value of decoupling our architectures by considering a common deployment, one where the web server, application server, and database server reside on the same EC2 instance with a public IP address. If we need to modify any of the application components, it's most likely going to result in an outage. If we need to scale our system, we can only scale up to larger, more powerful instances. It's challenging to architect for scalability or availability, as the unit of scale is an entire system. While our cost model may look attractive, as combining services onto a single host probably means that we will get high utilization, the downside of this monolithic approach outweighs the positives for all but a few cases. This leads us to our first technique for decoupling, using a load balancer. The Amazon ELB can be used to provide public and private load balancing. First, let's introduce an ELB in front of our monolithic system. This allows us to decouple the public hostname from the IP address of the host or host providing the service. This will be important as we decouple each tier and scale out. The next stage of decoupling is to separate out each of the tiers. We now have three distinct tiers: a web tier, application tier, and a database tier. In addition to the public ELB created earlier, we introduce a private ELB between the web and application tiers. This provides significant flexibility as it allows us to scale both the web and application tiers independently. Furthermore, if we have multiple instances at each tier, we can tolerate failure of a resource. Failure can be caused at the virtual resource level, such as an EC2 instance, or potentially with the application. Either way, assuming we have sufficient capacity to support the additional load, service is not impacted. To complete the previous architecture, we now illustrate how additional components can be added at each tier, potentially via autoscaling groups. Building on the last example, let us now consider a different type of coupling, one where two components communicate synchronously. Let's imagine that our application server needs to watermark user-created video content before making it available to download. We will momentarily overlook the Amazon Elastic Transcoding service for the purpose of this example and perform the action ourselves using a watermarking service. The current architecture consists of an application server making an API call to the watermarking service, resulting in watermarking jobs being created and queued on the watermarking host. We even make the watermarking service asynchronous, thereby allowing the client, our application server, to go about its business servicing other requests from the web tier. We have actually incorporated some decoupling best practices here. We have placed a web service behind an ELB, thereby allowing us to scale the service without needing to update DNS records. We can even tolerate failure of resources behind the ELB. Or can we? The problem we have here, and the reason why there is still a strong degree of coupling, is that all watermarking job state is stored in the EC2 worker instances. Apart from losing jobs during scaling down or failure situations, there's no easy way to redistribute the backlog during times of peak work. The solution here is to use a message queue to store job definitions. While we can use a number of messaging solutions, Amazon's Simple Queue Service, SQS, provides a fully managed, highly durable queue. Now, instead of the API request resulting in watermarking jobs being queued on the host, a suitable message is placed on a queue, and a group of workers pull the queue for jobs and complete the task. Once the job is complete, the client is notified. One last AWS service deserves a mention. It is the Amazon Simple Workflow Service, SWF. Amazon SWF allows us to build, manage, and scale multi-step processes that consist of sequential and parallel steps. In the previous example, imagine that the transcoding service actually consisted of 3 to 4 small steps, each dependent on the outcome of the previous step. By placing the decision logic and the action or worker code on the same host, we now have to manage state again, and for long complex processes, this couples a process to the host, which is not ideal. SWF allows us to separate out the decision logic from the action code and ensures that state, the history of each step in the process, is readily accessible from a durable data store. SWF is a highly useful service that has huge potential to be used not only to control processes running on AWS, but also in our own data center. We can consume the SWF service and run decider nodes and worker nodes anywhere, provided that they have access to be able to make API calls to the SWF service. Decoupling architectures isn't simply an exercise in breaking apart our virtual infrastructure building blocks. While we can of course significantly improve our position, unless we work with the software engineers developing the application, then we'll miss out in some areas. Decoupling is driven by multiple needs, not just availability. It often includes the need to scale an architecture, make it elastic, simplify operational management, and create a separate security domain for different tiers of our architecture. Sometimes one of these factors will be more important than others. We should understand what the dominant drivers are and prioritize them during the design process. If we are using off-the-shelf products, our options may be limited. As illustrated earlier in the video, separating our architecture by tiers significantly reduces coupling, provided that we use a load balancer to hide the resources at each level. One area we didn't explicitly cover earlier, but one that's important when scaling out, is handling state. Unless our web application is stateless, then we will need to move state outside of one or more of the tiers and potentially use the stickiness features of the ELB service. The complexity of doing this depends on the nature of the application, but in most cases, this is achievable with minimum effort, especially if we use services such as the Amazon Elastic Cache to store state. Using queues can be a highly effective way to decouple asynchronous components of our architecture. However, like with any AWS service, we need to understand limitations of the service and consider whether we need to develop additional higher-level features with our own application. For example, SQS guarantees messages will be delivered at least once. While duplicating messages is uncommon, it is still possible, and therefore we need to consider whether duplicating processing of jobs can cause unwanted results. In the example of watermarking video content, occasionally duplicating a transcoding job only wastes some compute resources. However, if the job was transactional in nature, such as taking payment for a product or service, we don't want to do that twice. In that case, the SWF service is the better choice, as it guarantees that each step of a workflow will only be performed once. In this video, we will be looking at pilot light architectures from the perspective of cost optimization. So let's get started. We will start by looking at the origin and meaning of the phrase pilot light architecture and why they are useful. Next, we will look at typical or common stages of a pilot light architecture. Then, we look at some key AWS services with features that are very helpful in building pilot-like architectures. We will then conclude with a summary of the key design considerations to bear in mind as we design pilot-like architectures for the AWS platform. The term pilot-like architecture takes its name from the small gas flame that would always be on and ready to ignite a bigger flame as found in old gas heating systems. In terms of AWS, a pilot-like architecture corresponds to an architecture where the normal running state is a small footprint of resources that can be dynamically increased in size at a moment's notice. Similar to a gas pilot light, a pilot-like architecture must be able to rapidly change its state to become a larger system capable of handling production workloads. For this reason, pilot-like architectures are highly cost-effective and are commonly used to achieve business continuity. They are commonly used not only for disaster recovery situations between AWS regions, but also between on-premise and AWS. Let's consider a pilot-like architecture to support cross-region disaster recovery for a simple web application. The architectures consist of a DNS-hosted zone for www.example.com hosted in Route 53, a load balancer provided by AWS Elastic Load Balancing Service, a pair of web application servers running on EC2, and a data tier consisting of a highly available multi-AZ MySQL RDS instance with asynchronous replication to a secondary region. This ensures a recovery point objective in the order of seconds. As the asynchronous read replica is only receiving write traffic from a primary region, we can probably use a smaller instance type. This will reduce the pilot-like architecture costs even further, but potentially complicate operational failover and increase failover times in the event of a disaster. For the purpose of this example, let's assume that the application in the primary region has been impacted. Let's assume it was caused by an unlikely, widespread service disruption to one or more AWS services. After a suitable period during which we wait to see whether the service will be restored, we decide to initiate the failover process. The first stage of failover is to ignite the full application stack in the secondary region by using the small pilot light. In this case, we promote the RDS read replica to a master and spin up 2 web application servers using our Amazon Machine Image template. In a real architecture, ensuring that AMIs or Amazon Machine Images are available involves considerable effort, but we shall leave discussions of continuous delivery pipelines aside for brevity. In parallel, we launch a new Amazon Elastic Load Balancer instance and register the web application servers with it. Once our resources have fired up and are ready to receive traffic, we initiate the cut across process by updating the DNS record to point to the new Elastic Load Balancing instance. Finally, we initiate replication to the original primary region once service is restored, or we replicate to a third region. Only once the replication process is complete are we able to handle another DR event. There are a number of AWS services that significantly simplify the design of a pilot-like architecture, saving us time and operational effort. Firstly, as we have seen, RDS provides a useful cross-replication feature. However, at present, support is limited to a subset of supported database engines, so we should always check the service documentation to ensure that the database engine we want to use is supported. DynamoDB, Amazon's NoSQL database solution, can be configured to send table updates to an Amazon Kinesis stream. Updates can then be read from the stream in another region and placed into a secondary DynamoDB table. This allows us to replicate a NoSQL data tier in near real time across regions. If we are looking at a pilot-like architecture to assist in replication from on-premise to AWS, then the AWS Storage Gateway will allow us to transparently cache data located on-premise and synchronize it to S3, ready to be rehydrated during a failover scenario. Other notable features include an AMI copy feature that allows us to easily copy AMIs between regions and takes care of choosing sensible kernel, RAM disk, and other required metadata. S3 also has a useful feature to allow us to copy objects between buckets located in different regions. As S3 is the persistent durable data store for most architectures, this useful feature makes bulk movement of data very simple. This list is not exhaustive, as the focus of the screencast is cost optimization. To ensure that you minimize operations and design costs, we recommend that you check the data replication features of each service included in your architecture to ensure you don't waste time and money building something that AWS has already thought of. While the primary driver for using a pilot-like architecture is to reduce operating costs, There are a number of factors we need to consider when designing such an architecture. A pilot-light architecture is usually part of a disaster recovery or business continuity plan. In the event of a disaster, operations need to support the business by deploying a replica production environment, often in a different geographical location. The first thing to understand is what constitutes a disaster. The old world view of a disaster would be the failure of a primary data center requiring services to be failed across to a secondary or disaster recovery data center. When considering a public cloud, architectures typically are geographically distributed between two or more availability zones, running in an active-active configuration. The new definition of disaster is typically considered as failure within a primary AWS region. Understand what the business requires for business continuity, and do not architect an overly complex multi-region solution that uses pilot-light architectures or other architectures for that matter, unless it makes good business sense to do so. As we are architecting for cost, it's important to realize that cost is not simply operational cost. AWS's resource consumption models for on-demand, reserved, and spot allow us to make significant cost savings. Pilot lights are a great candidate to benefit from reserved instances. The small, always-on footprint of a pilot light architecture can use heavy utilization reserved instances, whereas the capacity needed when resources are ignited can use light reserved instances in order to guarantee capacity while minimizing OpEx. This, of course, will require a small CapEx investment. The recovery time objective, RTO, that is how quickly we can restore a service in the event of a disaster, plays a significant role in the size and complexity of a pilot-light architecture. For example, consider the case where the RTO is 4 hours, and we know that the application can be deployed from scratch with no pilot light in a secondary AWS region in 1 hour, providing that the secondary region has a suitable Amazon machine image and deployment tools in place. In this case, our pilot light is simply the deployment tools, and no actual additional resources are required. However, pilot light architectures are typically used when SLAs are in the order of a few hours, and there is a data tier that needs to be closely in sync with the source. This takes us on to recovery point objective, RPO. That is, the maximum age of data we can afford to lose in the event of a disaster. It's common that the RPO is significantly smaller than RTO, often by more than an order of magnitude. This leads us to having to run at least a small data tier component in a secondary region in order to receive updates asynchronously from the primary. The degree to which operations have been automated can have a significant impact on the size of a pilot-light architecture. Inefficient IT operations can significantly erode the costs associated with a pilot-light architecture. Even worse, if during a disaster we need to rely on complex operational runbooks before failover and ignition, there could be a break in business continuity. Invest the time ensuring that operations is both reliable and an efficient process. In addition to RPO and RTOs, we often need to incorporate application key performance indicators, KPIs. These might be folded into the RTO. For example, for large systems with significant required resources, it may be necessary for the pilot light to consist of a small number of resources at each tier. For example, web and application servers in addition to the database in order to serve some traffic almost immediately in the event of a disaster. In this video, we will be looking at platform as a service from the perspective of cost optimization. We will start with a brief introduction to what platform as a service is and why it's important from the perspective of cost optimization. We will then take a look at the cost equation when consuming a PaaS. We will conclude by considering the key design considerations when consuming a PaaS. Before we look at platform as a service from the perspective of cost optimization, let's start by reminding ourselves what is meant by a PaaS. Platform as a service, or PaaS, is a category of cloud computing service that provides a platform allowing customers to develop, run, and manage web applications without the complexity of building and maintaining the infrastructure typically associated with developing and launching an application. It's a common mistake when developing a cost equation for PaaS to focus purely on the per-hour service costs. Therefore, let's take a look at the cost in the broader TCO sense. Let's start by looking at how a PaaS typically increases costs over developing, running, and managing the service ourselves. The first and obvious cost is the increased uplift from consuming a PaaS above and beyond the underlying resources. For example, if we consider the Amazon Relational Database Service, RDS, then we will pay several tens of % more to consume the database service than deploying EC2 and Elastic Block Storage resources. There will typically be some operational integration costs, with the majority of the cost incurred when the PaaS is first adopted. For example, if we previously deployed and managed our own MySQL database on EC2, our management tools will need to be reconfigured to accommodate the PaaS. Let's look at the other side of the cost equation, areas that will reduce our overall cost. Unfortunately, this side of the equation is a little bit more difficult to quantify, which in part explains why it often gets ignored or less value is placed upon it. The operational cost savings from adopting a PaaS can be significant by freeing up our database administrators from the minutiae of maintaining and patching low-level performance tuning, backup, high availability and disaster recovery management and testing. This allows them to focus on higher-level activities and administer a greater number of databases, thereby providing a significant cost reduction to the business. In the case where development teams are responsible for managing databases, as is common with smaller teams, often managing a database is a distraction and reduces the development speed. Removing this burden ensures developers are redeployed to areas of greatest yield. Consuming a PaaS often makes it easy to consume third-party software by the hour, as is the case for Amazon RDS with the Oracle database. When software is not available on demand, we are forced to often pay for a subscription that we may not be able to fully utilize. The data tier of an architecture is the most valuable tier. Its availability, security, and durability should be of greatest priority. It's not a trivial task to create a highly available system with automated failover, backup, and recovery. Failure to get this right can lead to the loss of customer data or unavailability of a service, thereby potentially impeding growth, acquiring new customers, or maintaining existing ones. Consider Amazon Elastic MapReduce, EMR. Managing a large, stable, performant Hadoop or Spark cluster poses a number of challenges. AWS have deployed millions of clusters since the service was launched. That's a huge amount of operational learning going back into the platform. Finally, opportunity costs are difficult to measure, but having the ability to quickly try out ideas is incredibly valuable to a business. Consuming a PaaS, even if it's just for a pilot program, removes barriers and allows us to try new ideas out more quickly. During the design phase, we need to evaluate what features and supported configurations we need our PaaS to provide. For example, in the case of a database PaaS, do we need a multi-master configuration? Should it provide asynchronous replication to a different region? What database engines are supported? And is there feature parity? For example, asynchronous read replication is not currently supported for all database engines available in RDS. As with any web service, we need to clearly understand the SLA of the service. This is particularly important for a PaaS, even more so if the PaaS is a database service. Is the service in beta or is it generally available? If it's the former, then we need to weigh up the risk of using the service in production. As architects, we should consider the additional degree to which we are coupled to a third party and estimate the complexity of migrating to another service provider or bringing the service back in-house and providing the service ourselves at a future date. Another variation of this consideration is if we intend to consume services from multiple cloud providers. How will we accommodate the difference? What are the cost implications in doing so? There is a shared responsibility model when consuming a web service. The line of responsibility moves depending on the service in question. For example, consider Elastic Beanstalk. AWS are responsible for the Elastic Beanstalk service and maintaining a selection of AMIs that we may use to deploy our applications onto. But we are responsible for the security of the EC2 instances once launched and running. Don't be tempted to invest significant effort abstracting away the nuances of a PaaS. It's unlikely you will recoup these costs if you migrate away from it later. Just be mindful of the degree to which we are coupled to the service. We also need to be mindful of integration with AWS product maintenance windows and backups. For example, if we consider Amazon RDS, during creation of an RDS resource, we need to specify a 30-minute daily backup window and a 30-minute weekly maintenance window that occasionally gets used by AWS to perform important updates to the service and its resources. In the case of a backup, and depending on the configuration of your RDS instance, any application accessing the database may experience a pause of read-write access to the database. During the backup window, storage I/O may be suspended while your data is being backed up, and you may experience elevated latency. This I/O suspension typically lasts for the duration of the snapshot. This period of I/O suspension is shorter for a multi-AZ database deployment since the backup is taken from the standby. but latency can occur during the backup process. Our application should be able to cope with connection errors, potentially with exponential backoff. Furthermore, given the potential for increased latency and potential I/O suspension, usual backup best practices apply, such as scheduling for off-peak. In this video, we will be looking at serverless architectures from the perspective of cost optimization. We will start by considering what is meant by a serverless architecture and why they are beneficial from the perspective of cost optimization. We will then look at the cost equation of incorporating serverless architectures into our designs. We will then look at design considerations from the perspective of cost optimization, and finish up by looking at AWS Cognito and how it can help make a significant proportion of a mobile application serverless. A serverless architecture is a category of architecture with no compute, storage, or application platform resources to directly manage or back-end code to write. Clients interact with one or more fully managed web services, typically via a RESTful interface over HTTP. The cost equation of a serverless architecture is similar to the cost equation of a platform as a service. Additional costs now come from consuming one or more web services that free us from the burden of managing servers. For example, instead of running a cluster of MongoDB servers on EC2, we may now choose to consume the DynamoDB service. These high-level web services typically cost us more to consume than if we were to consume the underlying infrastructure resources. There is also an operational integration cost, often loaded towards when we initially adopt a service. On the other side of the equation, the main cost savings are development costs. For example, consider the case where we need to design and build an architecture to manage user profiles across multiple devices. This could require significant development effort to create and maintain. However, if we can remove the entire component of our architecture by consuming a web service and developing client-side code to interact with the service, then we have just removed almost all of the effort. The operational cost savings from adopting a serverless architecture are typically greater than that of a PaaS, as we don't need to manage any compute, storage, or platform services. This allows our DevOps teams to be more productive and spend their time on improving the product or service the serverless architecture is supporting. Web services consumed by serverless architectures typically benefit from higher levels of availability and performance than we could do ourselves for the same cost. This is a consequence of scale and development resources available to continuously improve the web service. A good example of this is Amazon S3. The durability, storage capacity, and performance would simply not be possible for a similar price if we attempted to build a version of the service ourselves, unless our platform was of a similar scale. Now let's take a look at some of the design considerations we need to bear in mind as we architect for a cost optimization. The design considerations of a serverless architecture are similar to that of consuming a PaaS in our application architecture. However, now the degree of coupling to one or more web services is far greater. As architects, we should consider the additional degree to which we are coupled to a third party and estimate the complexity of migrating to another service provider or bringing the service back in-house and providing the service ourselves at a later date. Another variation of this consideration is if we intend to consume services from multiple cloud providers. How will we accommodate the difference? What are the cost implications of doing so? We are also more sensitive to supported features from web services consumed as part of our serverless architecture. For example, if we want to run the Apache web service on an EC2 instance, we have more control over the available features provided by the web service than, say, hosting a static website on S3. However, unless our access patterns are particularly unusual for a web server, such as lots of very small requests, then S3 will almost certainly be the correct choice, assuming its simple but powerful feature set is sufficient for our purpose. Use web services for the purpose that they were designed for, and actively provide feedback to product teams to help steer the future direction of a service to better meet our needs. As with any architecture, we need to clearly understand the SLAs of each service component. Do all the services have an SLA? Does one particular service have a significantly lower SLA than another service? What are the implications on our architectures and designs? One AWS service that's making it easier to develop serverless architectures is AWS Cognito. AWS Cognito allows us to offload the management and synchronization of user profiles across multiple devices. It's a serverless architecture component as we don't need to configure or manage any backend infrastructure or write any backend code. We only need to develop the client-side code using one or more of the mobile SDKs or JavaScript SDKs. AWS Cognito can also provide support for public login providers such as Google, Facebook, or Amazon via OAuth. It is also integrated with AWS Lambda, allowing us to incorporate event-driven architectural components into our serverless architecture. Anyone who has developed a mobile application for multiple platforms knows that managing user profiles and keeping scores and records in sync between devices requires significant development and infrastructure resources. Distracting developers from creating the next great game by having them develop back-end code or infrastructure can be the difference between a top 10 hit and the game company not being around next year. By using AWS Cognito to manage user data synchronization and using AWS Cognito Events as triggers to execute Lambda functions, say to validate user data before instantiating data synchronization operations, we can remove a significant upfront development cost and ongoing operational cost and burden. In this video, we will be looking at event-driven architectures from the perspective of platform cost optimization. We will begin by taking a look at what an event-driven architecture is, or more specifically, the properties of an event-driven architecture. We will then take a look at cost benefits of incorporating event-driven services into our architecture, followed by a review of some of the design considerations we need to bear in mind. Finally, we will look at an example of an event-driven architecture using AWS Lambda and consider how we may use its service to monitor an S3 bucket for new objects and then process them. So what is an event-driven architecture? An event-driven architecture performs work in response to an event. Examples of events include a message being placed in a queue, an update being made to a database table, or an object being placed into a data stream or data storage service. While we could argue that a user accessing a web service is also an event, that's a special category of an event that we will not include in this discussion today. An event-driven architecture should incur costs that are proportional to the number of events. Furthermore, a purely event-driven architecture should incur zero operating costs in the absence of events. Finally, an event-driven architecture should respond to events in near real time. Otherwise, we could argue that the architecture is closer to a micro-batch architecture in which events are grouped together and carried out in batch. The most significant benefit of an event-driven architecture is we pay for what we use, and by use, I mean doing work in response to an event. If there are no events, there should be little or no cost. If we compare this to running a web service on EC2, the compute resource incurs cost by the hour when in the running state, whether it performs work or not. Event-driven architectures generally have precise cost models as the total cost is the product of the number of events and the resources consumed to perform the work to complete them. If we understand the distribution of the resources consumed to perform work, we can accurately predict operating costs. In the same way, the platform as a service allows us to outsource some of the platform and infrastructure undifferentiated heavy lifting, then in this case, when our event-driven architectures consumes a third-party service, which incidentally is the only way to achieve zero costs, zero events, then we are able to divert resources into areas of greatest yield. When we consume an event-based service, operational overheads are reduced as we have just outsourced potentially a complex component of our architecture. This is especially the case when considering services that need to provide high levels of availability. If we want our architecture to incorporate an event-based service, then we are now creating a dependency on that service. As architects, we need to consider the additional degree to which we are coupled to a third party and estimate the complexity of migrating to another service provider or bringing the service back in-house and providing the service ourselves at a later date or time. Another variation of this consideration is if we intend to consume the service from multiple cloud providers. How will we accommodate the difference? What is the cost implications of doing so? As we consume high levels of service from infrastructure as a service, platform as a service, to software as a service, we become increasingly dependent upon the features and roadmap of a given product or service. For example, some event-driven services such as AWS Lambda currently support a limited set of programming frameworks and languages. We need to ask ourselves, what is the effort or cost of potentially rewriting parts or application to consume the service, and what is the corresponding time to recover that cost? In many cases, costs are recouped quickly, but sometimes the cost or feasibility doesn't make sense, and therefore we may wish to delay consuming such a service until it provides the features that we require. Another consideration is how many resources such as compute, memory, ephemeral storage, etc. do we have access to when consuming the event-based service. When consuming any service, event-driven or otherwise, we should be mindful of whether there is a point, or more specifically a scale, at which it becomes more cost-effective to perform the service ourselves. This is not a consideration for most organizations, and the decision to provide such a service in-house is often driven more by wanting greater control over the service direction and features than by operational economics. That being said, it is a consideration for a small percentage of potential consumers. AWS Lambda is an event-driven compute service. It automatically manages and scales resources in order to meet the demands of external events. It is a pure event-driven service in that the current pricing model results in zero cost in response to zero events. Furthermore, costs are a factor of the number of events and the resources consumed by each worker thread in response to an event. AWS Lambda currently provides support for a number of events including new messages in an Amazon Kinesis stream, changes to an S3 object, or updates to a DynamoDB table. As AWS has a track record of rapid innovation, we should always consult the latest service documentation to understand what the service is capable of. To illustrate how AWS Lambda may simplify an architecture and make it more cost-efficient, let's take a look at a simple use case. In this example, we're going to see how a basic document watermarking service may be simplified by consuming AWS Lambda. There are two components to the web service, namely a front-end service that allows customers to upload documents to an S3 bucket, and a back-end service that performs the watermarking action. The front-end web service uploads documents to S3. The S3 bucket is configured to create an event notification when a new object is created. This event is placed into an Amazon SQS queue. The document watermarking service then pulls the queue looking for new work tasks represented by events or messages. When an event, that is a message, is available on the queue, the watermarking service downloads the message, extracts the URL to the document on S3, downloads the document from S3, and performs the watermarking action. Provided that our document watermarking function is written in one of the languages supported by AWS Lambda, we can significantly simplify and reduce the operational cost of our architecture. We can replace the watermarking web service and SQS queue with an AWS Lambda function, and configure S3 to publish object creation events directly to AWS Lambda. In this video, we will be looking at environment-based scaling from the perspective of cost optimization. We will start by considering what environment-based scaling is and why it's attractive from the perspective of cost optimization. We will then consider the cost benefits of elastically scaling our application architectures in response to changing environmental conditions. Next, we will highlight a select number of AWS services and their features that will prove helpful in designing responsive architectures. And we will conclude by taking a closer look at the AWS Autoscaling service. Environment-based scaling refers to the automatic provisioning and termination of compute resources in response to changing environmental conditions. Changing environmental conditions could be additional users making requests to a web service, or it could be a failure of a node in a cluster causing increased load to be shared amongst the remaining cluster nodes. In this video, we're going to specifically focus on AWS web services that allow us to scale resources based on rules and triggers that we specify, and not services that automatically provide scaling, such as AWS Lambda. To illustrate the cost benefits of environmental-based scaling, let's consider a graph showing the operational load on an application against time. If we provision for peak load, the area represented by the orange diagonal lines represents unused resources and wasted money due to over-provisioning. Ideally, we want to provision just enough resources to meet demands on the system, adding or removing resources as the actual load changes over time. We continue to add more and more resources as the system load increases. But then, either due to an operational error or an incorrect provisioning strategy, or maybe an unexpected step change in load, we don't have enough resources to meet the demands of the system. This will result in an impact to service that will almost certainly translate into a lost opportunity to provide a service to our customers. This can clearly have a number of cost implications. We can address the potential under-provisioning of resources by first looking to automate provisioning of those resources, using a reliable service that's integrated with a monitoring service and not over-optimize the provisioning of resources to minimize cost. If we try to match supply with demand too closely, we may not be able to scale quickly enough to cope with unexpected load. We always need to balance the potential cost to the business for a loss of service versus operational cost savings of environmentally based scaling that scale up too slowly or scale down too aggressively. This is a common reason why scale down operations, that is, the removal of resources, is typically slower than scaling up. By designing our architecture to take advantage of environmental-based scaling, we can reduce our over-provisioning of resources often by 30 to 40%, or even more if we take into consideration seasonal variation in load. Two AWS services that immediately come to mind when we think about configurable environmental-based scaling are EC2 autoscaling and Amazon Elastic Beanstalk. As the autoscaling features of each of these are closely related, we will focus our attention on the EC2 autoscaling service and take a closer look at what it allows us to do. As with all AWS services, it's available via the AWS command line interface, via a web API, or the AWS Management Console. The autoscaling service is restricted to EC2 compute resources, and the autoscaling service allows us to control the scale out or adding of resources and the scale in or removal of those resources, based on a number of scaling policies that we can define. The autoscaling service consists of three main components, namely a launch configuration, autoscaling groups, and scaling policies. Let's take a closer look at each one of these resource types from the perspective of cost optimization. The first component of autoscaling that we will look at is launch configuration. This is where we specify the Amazon machine image, region, instance type, etc. Let's take a closer look at each one of these elements and see how we can optimize for cost. We need to understand the cost implications of using Amazon machine images from the AWS Marketplace. The Marketplace provides a large selection of third-party AMIs, many of which are free, but some come with additional per-hour costs in addition to the EC2 resource costs. Choose an AMI that's appropriate for the task in hand. There is some variation in resource costs between AWS regions. If latency and regulatory authorities allow you to store data and run your virtual infrastructure in one of a number of regions, choose the region where the operational costs are least. There is a huge selection of EC2 instance types that include varying CPU, memory, storage, and I/O profiles. We can significantly reduce costs if we choose the correct EC2 instance type. Monitoring over time and referring to AWS Trusted Advisor is a good approach to choosing the right EC2 instance type. We have the option of using dedicated or multi-tenanted EC2 instances. Dedicated instances run on single-tenant hardware but come at a significant additional cost to their multi-tenant counterpart. Unless restricted by a regulatory body that we must run on dedicated hardware, we should choose the default option of multi-tenancy. If our application can benefit from spot market resources, huge operational cost savings can be made. Spot isn't suitable for all workloads and often requires additional effort to manage the state of longer-running workloads. However, there are a great many use cases for it, including financial modeling and scientific computing, to name but two. As our EC2 usage becomes a little more predictable, we can use a mixture of on-demand and reserved EC2 instances to meet our needs. If we know that our application always requires a foundational baseline of compute, then we can purchase reserved capacity and use on-demand for the variable component. We can take this further by blending together different reserved capacity utilization types such as light, medium, and heavy. The cost calculator located within the AWS Economics Center is a useful tool to help decide what purchase options make the most sense. The next autoscaling component of interest is autoscaling groups. Group limits restrict the maximum and minimum number of EC2 instances that can exist within an autoscaling group, or we should place a sensible upper limit to avoid unlimited resource usage. We should have a generous amount of headroom to guard against unexpected spikes in traffic and potential software updates that have unexpected demands on resources. Cost optimization should not come at the cost of losing our customers due to a service being unavailable or overloaded. Reserved instances are purchased on an availability zone basis. Choosing the wrong availability zone when defining an autoscaling group will incur additional costs for on-demand if no reserved capacity is available in the availability zone defined. The health check grace period is the time taken for health checks to be performed on an instance after launch. While reducing this value can result in getting resources into service sooner and therefore providing real work, making it too small can result in instances being deemed unhealthy and actually extending the time to perform real work. While it's more of a cost allocation consideration, associating meta tags with autoscaling group resources will help make costs more visible and make monitoring and tuning of resources over time easier. The final component of autoscaling is the autoscaling policy. There are three types of scaling policy: manual, scheduled, and trigger-based scaling. We will focus on trigger-based scaling. The first thing to consider is the unit of change. That is, how many EC2 resources to add or remove when a trigger event happens. This depends on the size of our autoscaling group and how quickly usage can change. Starting with 1 for each initially and tuning these values over time to meet demands on systems allows us to closely manage costs. When defining scaling triggers, we can choose from a number of metrics, statistics, and durations. For example, we could define a scale-out trigger when the average CPU is over 80% for a period of 3 consecutive 5-minute periods. If the scale-out trigger is too sensitive, we may waste resources by deploying them unnecessarily. Furthermore, if our scale-in trigger fires too quickly after we have scaled out, then our total capacity will oscillate, and as a result, we may only get a few minutes service from the resource when paying for a full 1-hour period. Setting appropriate triggers is particularly important when our cluster is small. For example, consider the case of scaling up at 80% and scaling down at 40%. If we have a single instance, when we add a second instance in response to a scale-up trigger firing, the average CPU now becomes 40%, as the load is now shared across 2 hosts. This consequently can then result in a scaled-down event. Scaling too aggressively can result in either a poor customer experience or inefficient operating practices. A common mistake when first working with autoscaling groups is to manually terminate resources in order to reduce operating costs. However, be aware that if as a result of the termination, an autoscaling group limit is passed, or a metric-based trigger event results from the increased load, then a new instance will be launched, and partial instance hours will have been wasted unnecessarily. In this video, we will be looking at how we can use Amazon CloudWatch for performance monitoring. We will start off with a brief introduction to the Amazon CloudWatch service, with a particular focus on monitoring AWS resource metrics. We will then take a look at the CloudWatch graphs available for EC2 metrics by the Management Console. The remainder of this video will focus on interpreting CloudWatch metrics and highlighting some common pitfalls when viewing storage I/O throughput metrics. While we will briefly introduce Amazon CloudWatch and describe its key features, this short video is not intended to be an introduction to the AWS CloudWatch service or a getting started guide. We will focus solely on some useful best practices and common pitfalls to avoid when using it for performance monitoring. Amazon CloudWatch is a monitoring service for AWS service resources. With CloudWatch, we are able to collect and track resource metrics, store and monitor log files, as well as configure alarms. With CloudWatch, we can monitor not only point-in-time metrics of interest, but also statistical measures such as how a metric varies over time or across a group of resources. This is particularly valuable when considering the collective performance of resources within a group, such as, for example, an auto-scaling group. CloudWatch provides monitoring support for a large number of AWS services, with some support resource metrics being recorded 1-minute intervals. For example, CloudWatch supports 2 levels of monitoring resolution for Amazon EC2. The default is a 5-minute resolution, whereas the detailed resolution is every minute. The default level of monitoring comes at no additional cost above and beyond that of EC2, but if we need detailed monitoring, it currently incurs a small additional monthly charge. We can enable or disable detailed monitoring within an EC2 instance at any time. Therefore, we can increase the resolution during detailed performance profiling and disable it during normal operation. However, the decision to enable detailed monitoring may not only be a performance tuning or optimization consideration. It may be driven by other factors such as operational automation when combined with the EC2 autoscaling service. CloudWatch metrics are available for a period of up to 2 weeks. If we need to store metrics for a longer period than that, data will need to be extracted and stored into a durable low-cost storage service such as S3. For most performance tuning exercises, 2 weeks worth of data will probably be sufficient. But for applications that have monthly variations in performance, we may need to collect data for a longer period of time. We can extract historical CloudWatch data using the getMetricsStatistics API call. If we want to use CloudWatch to monitor metrics not exposed by an AWS service, then we can define custom metrics and push the recorded values to CloudWatch using the putMetricData API call. For example, for EC2, the amount of freeable memory is not an available CloudWatch metric. This is because an instance is allocated the amount of memory according to its instance type at launch. As the actual amount of memory used by the operating system isn't visible from the hypervisor, then CloudWatch cannot report it by default. Contrast this with a service such as RDS, which, being a managed database service, CloudWatch does have access to the operating system, as that's AWS's responsibility to manage. AWS provide a collection of example custom CloudWatch scripts to help us see inside of EC2 instances. They report memory, swap, then disk space utilization. AWS's example scripts can be found at the URL in the slide. CloudWatch is a useful service, but we can still use our favorite host-level agents to monitor resource, operating system, and application performance. What makes the most sense really depends upon the size of our environment, the level of insight we need, in particular our application services and resources, and the degree to which we already have an established monitoring platform. The CloudWatch service is constantly evolving to provide greater insight into existing services, as well as incorporating new AWS services and products. The complete list of CloudWatch metrics can be found at the URL in the slide. The first experience that new users of the AWS platform have using AWS CloudWatch is typically via the AWS Management Console. In addition to accessing raw historical CloudWatch metrics or statistics from the last 2 weeks, we can also visualize data via simple interactive graphs. As data can be as little as 1 minute old, this is a great way to investigate issues in near real time and visually explore historical behavior. For example, the screenshot presents a CloudWatch graph for CPU utilization on a T2 micro instance during load testing. While we are only using CloudWatch monitoring with a 5-minute resolution in this example, we can clearly see variation in load against time. While interpreting CloudWatch graphs is generally highly intuitive, there are a few pitfalls for new users that can lead to unexpected results. If we are performance benchmarking or investigating performance issues, then being able to accurately interpret CloudWatch metrics is clearly necessary. Let's take a look at a few areas that can cause confusion to new users of CloudWatch. For the purpose of this example, we run a set of I/O tests on an EC2 instance. The duration of the test was approximately 45 minutes, and statistics collected by the operating system showed that network write throughput was approximately 35 MB per second. After logging into the AWS Management Console and navigating to the EC2 section, we select the EC2 instance used during the testing and select the Monitoring tab. As we can see from the CPU utilization graph, we have an elevated utilization between 2345 and 030. This spike in CPU results from the I/O testing. However, if we look at the write throughput during this period, we see no network I/O traffic. This is actually an expected result. The monitoring summary section only displays the I/O to local ephemeral volumes. As our EC2 instance has an EBS-backed root volume and our I/O test uses that root volume, then there's no I/O to ephemeral storage. The first lesson to take away from this video is to ensure that the CloudWatch metric refers to the resource we think it does. While it was obvious during this simple test, if there had have been I/O to the ephemeral volume during the test, we could have mistaken it for our test I/O. If we want to actually see the network I/O recorded during the simple test, we need to find the EBS volume corresponding to the root volume. We can do this by clicking on the block device name in the management console. In this case, the volume is vol 09E11CE1. By clicking on the volume link, we are taken directly to the volume details in the management console. The summary graph shows a sustained I/O of little over 35,000 kibibytes per second, or about 34.5 mebibytes per second. This is consistent with the I/O reported by the operating system during the test. Let's take a closer look at the write bandwidth performance by clicking on the graph. We are presented with a more detailed view of the write performance during the testing window. Once again, the I/O write bandwidth appears to be consistent with that reported by the operating system. Everything is intuitively what we would expect so far. Now let's take a closer look at each of the 3 drop-down menus of statistics, time range, and period. Time range is simply the width of the window of data we are looking at. In this case, it's from 2345 to 045. Period is the range over which we are performing the statistical operation. In this case, it's summing up the I/O metrics over a 5-minute interval. As we increase the interval, it has the effect of smoothing out the graph as we lose resolution. Now let's take a look at the other statistical options. We have average, minimum, maximum, and sample count. It's very important to consult the AWS CloudFormation documentation at the URL presented in the slide to understand which statistics are meaningful for a given resource. For example, maximum and minimum are not relevant for volume write bandwidth. This is the second lesson we should take away from this video. Let's take a look at average. This is where things may start to be a little surprising. The y-axis for the graph is still set to write bandwidth in kibibytes per second, but the average appears to be 0.426. So what's going on? The figures for write bandwidth appear to be an average measure of throughput per fraction of a second, and not as the legend suggests. This makes a little more sense if we now look at the sample count. During a period of 5 minutes or 300 seconds, we collected 278 samples per second, each with an average throughput of 0.426 kibibytes per sample per second. If we want to calculate the throughput per second, we need to take the product of the average throughput in kibibytes per second, the number of samples per second, and the number of seconds per period. This gives us a value of 0.426 kibibytes, multiplied by 278 multiplied by 300, which comes to 34.7 megabytes per second. While I find the sum statistics very useful for quickly determining I/O, working backwards from average and sample counts is a little cumbersome and can easily lead to errors if we frequently change between sample periods. There is another way to view CloudWatch metrics for an EBS volume. Instead of viewing the metrics via the monitoring section of the EBS section of the management console, we can view them directly from the CloudWatch service. Let's do this and compare the results. Let's select the full list of available metrics and then the write throughput bandwidth. The CloudWatch graph looks very different to the one we saw when we accessed the data directly from EC2. The sum value now for a period of 5 minutes is close to 11.2 billion bytes. However, one subtle difference between the two graphs is the unit on the y-axis. We are measuring in bytes, not bytes per second. The period is not the second, but the interval specified by the drop-down list. If we divide the sum by the number of seconds in the period, in this case 300, then we'll get a value of 35.5 megabytes. This is consistent with our operating system performance statistics and the results we saw earlier. This makes perfect sense. If we change the metric to average instead of sum, we see the average write throughput during the sample interval. Therefore, logically, if we take the product of the throughput per sample, the total number of samples during the 5-minute period, and divide by the number of seconds in the sample period, in this case 300, then we should get back to our throughput figure of around 35.5. As we can see, we have just over 85,000 data samples during the 5-minute period. Therefore, the total throughput during our monitoring period is 11.2 billion bytes, which as we saw earlier, equates to 35.5 megabytes per second. Therefore, the EBS metrics presented via the CloudWatch section of the AWS website are consistent with what we recorded via the operating system. While we need to perform some calculations to get meaningful per second throughput figures, how we do so is intuitive and logical. The third lesson we should take away is, if we just want to quickly see what the I/O to a storage volume is, viewing the sum statistics for throughput per second on the EBS volume monitoring page is the simplest approach. It doesn't require any calculation on our part. If we decide to view the metrics from the CloudWatch section of the management console, we will however need to perform some calculation on the statistics before they are meaningful. The fourth lesson we should take away from this video is that the average statistic for network I/O is not necessarily intuitive with what we may expect, so we should always take care when using it in our calculations. In this video, we will be looking at performance optimization of a selection of Amazon Compute services. We'll start by covering the extent of compute services provided by AWS and highlight the scope of this video. We will then look at Amazon Elastic Compute Cloud or EC2. This will include the different instance families and types, instances optimized for storage I/O, and instances optimized for general network I/O. We'll then move on to consider the differences between paravirtual and hardware-assisted virtual machine types before wrapping up EC2 by looking at placement groups. Finally, we will look at performance optimization guidelines for AWS Lambda. AWS provides a number of cloud-based computing services. These include EC2, AWS Lambda, the Amazon EC2 Container Service, and a number of supporting services such as autoscaling, VPC, and the Elastic Load Balancing Service, ELB. The focus of this video will be EC2 and AWS Lambda, but many of the recommendations are equally applicable to the EC2 container cluster resources. While we will only briefly mention AWS CloudWatch in this video, CloudWatch should form the foundation of performance monitoring and subsequent optimization for the Amazon cloud-based computing services. EC2 resources consist of two broad categories or families: the current generation of resources and those of the previous generation. The current generation of resources typically provide better performance than the previous generation of resources. While the previous generation are still fully supported by AWS, they do encourage us to upgrade to use the latest generation. Instance types are grouped together into one of 5 different groups. The first group is called general purpose. As the name suggests, these are instances that are optimized for general workloads, ones that are balanced in their use of CPU, memory, and storage. This class is further broken down into 3 subclasses: T2, M3, and M4 instance types. T2 instances provide moderate baseline performance and the capability to burst to significantly higher performance as required by our workload. T2 instances are well suited for general purpose workloads such as web servers, developer environments, and small databases. M3 instance types provide a balance of compute, memory, and network resources with local SSD-based instance storage. They are a good choice for small and mid-sized databases, data processing tasks that require additional memory, caching, and for running back-end application services. The M4 instance types are the latest generation of general-purpose instances. This family provides a balance of compute, memory, and network resources. They are EBS optimized by default and have more memory and virtual CPUs than the M3 instance family. Next, we have compute optimized instances. As the name suggests, they are optimized for compute-intensive workloads and have a lower price-to-compute ratio than the general instance family. Compute resources currently range from 2 virtual CPUs right through to 36 virtual CPUs. This family of EC2 instance comes in 2 subcategories, C3 and C4. C4 are the newer instance types with support for enhanced networking and dedicated EBS throughput. Next, we have memory-optimized instance types. They have a lower price-to-memory ratio than general instance types. Memory range from just over 15 GB of RAM right up to 244 GB of RAM. These instance types are ideally suited for relational and NoSQL databases. They are also suited for in-memory analytics and memory cache, such as Memcache and Redis. Moving on, we have storage-optimized instance types. There are currently 2 subcategories within this space. These include I2 and D2. The I2 instance class are optimized to deliver tens of thousands of random access IOPS. This makes them an ideal choice for databases and online transaction processing. Read IOPS currently range from 35,000 to a staggering 365,000 IOPS. And finally, we come to AWS's GPU family of instances. These instances contain between 1 and 4 NVIDIA GPUs, each with over 1,500 CUDA cores and 4 GB of memory. These instances contain between 1 and 4 NVIDIA GPUs, each with over 1,500 CUDA cores and 4 GB of video memory. These instances can deliver blistering performance when workloads make use of the available GPUs. They are a great choice for rendering, 3D application streaming, machine learning, and video encoding. When AWS introduced provision IOPS, the performance bottleneck moved from storage IOPS through to storage throughput. Throughput contention resulted because EC2 instances use the same network interface for application network traffic and access to network storage. There was clearly a need to increase the effective throughput from instances with the highest throughput requirements. This was met with the introduction of EBS optimized instance types. These are instance types with dedicated I/O capacity to EBS volumes, thereby reducing network contention. Currently, EBS optimized instances provide between 500 and 4,000 megabits per second of dedicated network I/O. However, care should be taken to ensure we match instances with sensible EBS storage volume performance to avoid wasting resources or achieving suboptimal performance. EBS optimization for a given instance is optionally enabled. This can either be done when the instance is launched or by stopping and restarting the instance. It should be noted that enabling this option incurs an additional hourly cost. Refer to the EC2 pricing page for details. As we explore the available Amazon machine images, we will probably notice that some provide support for paravirtualization and some for hardware-assisted virtualization. AMIs that use paravirtualization use the PV boot loader. This chain loads the kernel listed in the EC2 instance operating system. Paravirtual guests are able to take advantage of older host hardware that may not provide support for hardware-assisted virtualization. Unlike paravirtual guests, hardware-assisted virtual guests are able to take advantage of modern hardware with server hardware extensions. They are supported by all current generation instance types and benefit from optimized network and storage drivers. This avoids the overhead of having to emulate network and disk hardware. This wasn't always the case, so if we initially investigated and dismissed them, In all probability, our earlier reasons for dismissal are no longer valid. Hardware-assisted AMI should be our preferred default option for optimal performance. A subset of EC2 instance types support enhanced networking. These instance types are able to take advantage of single-root I/O virtualization, a method of device virtualization that provides higher I/O performance and lower CPU utilization compared to traditional implementations. As this is a hardware extension in the host, we can only take advantage of it when using hardware-assisted virtual machines. Another great reason for ensuring we consume AMIs of this type. Single-root I/O virtualization allows the guest to handle greater numbers of network packets per second with low latency and less variance in performance. It is possible for both Linux and Microsoft Windows instances to take advantage of SR-IOV, but enabling it in the guest operating system is different for each. In the case of Linux, we need to ensure that the IXGB EVF kernel module is loaded, whereas in Windows, they require installation of an optimized Intel network driver. Placement groups are a way to logically group together EC2 instances within an availability zone. This allows for increased network performance and reduced latency. Instances in the same placement group are connected via a 10 gigabit per second full bisection network interconnect that provides very low latency. However, we still need to choose EC2 instance types with sufficient resources to take full advantage of placement groups. For example, an instance that does not support 10 gig network speeds will not magically be able to do so when placed into a placement group. It should be noted that placement groups are supported across peered virtual private clouds or VPCs, but while we will still be able to benefit from a reduced latency, we will not be able to take full advantage of the 10 gigabits per second network interconnect. Given their performance profile, placement groups are commonly used for HPC workloads where networking becomes the dominant limiting factor as we scale out the HPC cluster. Let's take a look at AWS Lambda from the perspective of performance. AWS Lambda is a fully managed, event-driven compute platform into which we can deploy our code. Application code executed by the Lambda platform is referred to as a Lambda function. The great news is that AWS looks after the underlying platform and ensures that it is performant. There are, however, a few things that we can do to optimize our Lambda functions. Firstly, it's common for Lambda functions to interact with other AWS services, such as S3 and DynamoDB. When possible, we should ensure that the Lambda functions reside within the same region as the resources that they're interacting with, so as to avoid unnecessary latency. Each time a Lambda function runs, it consumes memory and CPU time. While efficient development practices should apply whether we are using Lambda or not, increased run times or bloated resource usage can impact performance and ultimately lead to increased running costs. In particular, one area that AWS specifically encourages to optimize is the Lambda function startup code. This is the overhead that we have to bear each time a function is run. One way to reduce startup overhead is to use standard library versions when at all possible. And finally, AWS CloudWatch is invaluable for performance tuning and analysis of EC2 resources. It also provides support for AWS Lambda and allows us to monitor the number of times a Lambda function is invoked, the duration of the Lambda function execution, as well as the number of throttles and event errors, which, if excessive, can actually impact our perceived performance. In this video, we will be looking at Amazon storage and content delivery services from the perspective of performance. We will start with a brief introduction to the family of Amazon storage and content delivery services and highlight the focus of this video. We will then look at EC2 instance local storage, followed by Amazon's Elastic Block Storage service. We will then wrap up by considering the Amazon Simple Storage service. AWS provides a number of cloud-based storage and content delivery services. These include Amazon S3, Amazon Glacier, Amazon EBS, EC2 Local Storage, Amazon Elastic File System, the Import-Export Service, AWS Storage Gateway, and Amazon CloudFront. The focus of this video will be EC2 Local Storage, Amazon EBS, and Amazon S3. In particular, the Amazon Elastic File System was omitted from this video as it had preview status at the time this video was created. The majority of EC2 instances have one or more local storage volumes that reside on the host hardware. Some instance types use solid-state drives to deliver very high random I/O performance. This is a good option when we need storage with very low latency. Details of the amount and type of storage associated with each instance type can be found at the URL presented in the slide. As local storage is ephemeral in nature, that is, the data does not persist through an instant stop and restart action, it is sometimes overlooked. However, if the lack of persistence can be managed, for example, data can be easily repopulated in the event that the host will be replaced or the storage is used for temporary scratch data, then we can achieve lower cost performance compared to Amazon Elastic Block Storage for a given range of operations. When using local storage, we eliminate network latency and therefore we can often increase performance. Solid-state drives operate differently to traditional devices with rotating disks. While we can achieve very high numbers of IOPS, there can be a progressive degradation of write performance. One way we can help reduce this impact is to issue the trim command. Trimming enables the SSD to handle garbage collection overhead, which would otherwise slow down future write operations to data blocks. Trim can either be issued as an admin command or, when supported by the operating system, perform the action upon mounting a file system residing on an SSD. Next, let's take a look at Amazon Elastic Block Storage. There are 3 different storage types available, each with a different performance to price characteristic as described in the URL in the slide. Let's start with the magnetic EBS volumes. These are the least performant EBS volume type. We can typically achieve 40 to 90 megabytes per second at an average of 100 IOPS. While the IOPS performance can burst in excess of this, we should not rely on this for extended periods of time. These volumes are ideally suited to OS boot volumes and infrequently accessed storage with low performance requirements. These provide a significant increase in throughput and IOPS performance over magnetic volumes. They provide throughputs of 160 megabytes per second for volumes greater than 214 gigabytes and as much as 10,000 IOPS. AWS recommends using this EBS type for system boot volumes, virtual desktops, small to medium-sized database servers, and dev test. However, it should be noted that volume performance is different when volumes are less than 170 gigabytes in size. Throughput is limited to 128 megabytes per second. For volumes smaller than a terabyte in size, they gain I/O credits each second equal to 3 times the size of the volume. For example, a 100 gigabyte volume would accumulate 300 I/O credits per second. I/O credits are capped at 5.4 million and are only accumulated for volumes smaller than 1 terabyte. The last EBS type we will look at is provisioned IOPS. Provisioned IOPS allows us to control the number of IOPS we require from the storage while requiring that the ratio of IOPS to storage in gigabytes is greater than or equal to 30. For example, if we require 3000 IOPS, we will need to provision at least 100 gigabytes of storage. As they provide the highest, most consistent performance, they are best suited for relational and NoSQL databases. In order to maximize the performance of storage, we should match the storage type to the correct EC2 instance type. Refer to the Compute Focus Performance video in this series for further details. The first time we access a block in a newly created EBS volume, there is a loss in performance of between 5 and 50% of the expected IOPS of the volume. Therefore, if we need storage to perform at peak capacity, we should always zero out the volume when possible. In the event that the volume is created from an EBS snapshot, the only option is to read every block. Zeroing out the storage is probably most critical when conducting performance benchmarking. If we forget to do this, our results may be different from what we expect. EBS snapshots are a way for us to make a copy of the contents of an EBS volume. Creating a snapshot may slightly degrade the performance of the volume during the snapshotting process. The duration of the snapshot process can be reduced by snapshotting more frequently. For most consumers of the Amazon S3 service, the biggest thing we need to consider to improve performance is reducing latency between resources interacting with it. It's often the case that the consumers of an S3 resource, for example a client web browser, will be located in a different location to the resource that creates the content, such as an EC2 instance. In this case, we can use a content delivery network such as Amazon CloudFront to optimize delivery to consumers. Amazon S3 supports multi-part uploads. Multi-part uploads allow us to upload parts of an object in parallel and get S3 to assemble them once they arrive. For downloads, we can use range queries to get different parts of the object, then assemble them at the destination. If we routinely exceed 100 reads, lists, or delete operations a second, or more than 300 get operations per second, we should follow AWS's recommendation of object key naming. The greater the amount of randomness at the start of the key name, the greater degree to which objects will be distributed across the back-end S3 storage platform. One approach of increasing performance is to use a mod 16 operation on the object name. A single character prefix will give us 16 times the IOPS compared to objects with no randomness in their key. A 4-character hash key could theoretically support over 1 million IOPS. Refer to the URL in the slide for a detailed explanation of how this works. It's possible to see performance improvements between a host OS and S3 by increasing the TCP scaling window. The last performance area we might consider tweaking in the operating system is the TCP select acknowledge value. This increases the number of TCP packets sent before acknowledging them. In this video, we will be looking at Amazon Database Services from the perspective of performance. We will start with a brief introduction to the family of Amazon Database Services and highlight the focus of this video. We will then look at performance considerations for the Amazon Relational Database Service, RDS, and conclude by looking at Amazon DynamoDB. AWS provides a number of cloud-based database services. These include Amazon Relational Database, RDS, Amazon DynamoDB, Amazon SimpleDB, Amazon Elastic Cache, and Amazon Redshift. The focus of this video will be Amazon Relational Database and Amazon DynamoDB. Performance tuning of databases is complex. It typically covers optimization in a number of different areas. For a given set of available resources, different database engines make more effective use of RAM and compute. Choosing a database engine and tuning the engine will be limited in scope. We will briefly cover Amazon's Aurora database engine and highlight the maximum IOPS performance we can achieve using each database engine supported. We will principally focus on performance tuning elements that are specific to the AWS platform. Scaling out the database is also a common technique for increasing performance. We covered this in another video in the series, specifically focused on scalability, so our focus will be on a single RDS instance. When creating an RDS instance, we have control of the RDS instance type, storage, and database engine. Performance bottlenecks on databases move between CPU, memory, storage IOPS, and throughput. As RDS provides a large selection of instance types and storage options, it's often the case that we simply want to optimize resources for a given workload to reduce cost. Finding out which of these is the effective bottleneck is made easier by Amazon CloudWatch. A general approach to performance optimization is either to run a set of benchmarks or simply monitor actual production traffic for a sensible period of time. If we are using production workload data and we expect load to vary during a 24-hour period, then we should at least look at a day's worth of CloudWatch data. Better still, consider a week's worth of data to ensure there are no unexpected weekly variations. Before looking at Amazon CloudWatch metrics, we need to know what we expect the upper limits of our read and write IOPS, read and write throughput, and memory are. CPU is measured by a utilization figure, so 100% is the effective upper limit. For smaller databases running on the T2 class of instance type, the CPU bursting properties of the resource can add an additional dimension of complexity. But let's focus on instance types with predictable fixed compute resources for this analysis. With the theoretical maximums for I/O, memory, and compute at hand, we should then methodically go through each recorded metric and compare them. Provided the I/O performance of an RDS instance type is well matched with attached storage, performance bottlenecks will be easy to spot. Often, we just need to increase the IOPS of our storage or choose an instance type with more CPU. However, in the case where CloudWatch shows the effective IOPS or throughput are less than we expect, there's a good chance that we are saturating the available network throughput on the RDS instance. In accompanying videos in this series, we discuss performance optimization of EBS storage and EC2 instance types. In particular, the high I/O performance and low variation in latency makes provision IOPS the preferred storage type for the greatest performance when matched with storage optimized instance types. Refer to each of the videos for guidance on optimizing each of these resources. The guidance holds equally well when matching RDS instance types with storage. There is a subtle difference between provision IOPS for RDS resources and general purpose EC2 resources. The effective theoretical maximum throughput for each is a product of the engine's page size, the supported storage size, and maximum storage to IOPS ratio. For MySQL and Postgres, the maximum theoretical IOPS is 30,000, whereas Oracle is currently 16,000 and Microsoft SQL Server 10,000. To wrap up the section on RDS, we consider Aurora, the latest database engine supported by Amazon RDS. Aurora is a high-performance SQL-compatible database that Amazon describes as having the performance and availability of a commercial database. Aurora has been optimized for the RDS platform, resulting in increased I/O throughput with less variance in performance. Testing Aurora using Sysbench has shown a 5 times performance increase over MySQL version 5.6 on similar virtual resources. If our application supports the MySQL database and we need to maximize database performance, then Amazon Aurora for RDS should be considered. Amazon DynamoDB is a fully managed, high-performance, low-latency NoSQL database with support for strongly consistent reads. While DynamoDB allows us to dial in our IOPS for read and write operations, cost will usually be a strong factor in the design process. Therefore, the focus of this section of the video is on how we can make efficient use of the available read and write IOPS. When we create a DynamoDB table, we specify the read and write IOPS. These determine the number of 4K read and 1K write operations we can perform each second. Therefore, if the expected object size is 8 kilobytes and we need capacity to read 100 objects per second, then we need to provision 200 read IOPS. When strong consistency for reads is not required, it is possible to make read operations eventually consistent. This effectively doubles our read capacity on a table. Optimizing a NoSQL database to make effective use of primary and secondary indexes requires considerable design planning based on specific application use cases. It may also require several iterations of performance tuning based on actual usage metrics recorded by CloudWatch. AWS provides detailed coverage of this specifically for DynamoDB at the URL in the slide. That being said, let's take a close look at some of the key considerations that impact index performance. When we create a DynamoDB table, we must choose a primary index with optional range key. The primary key uniquely identifies an item in a DynamoDB table. For example, the user ID could be used as a primary key for a table that contains user attributes or credentials. If, however, we wanted to store user activity, then we'll need to create multiple items for each user, one for each activity event. In this case, we will need to create a compound primary key consisting of the user ID and a date-time attribute range. DynamoDB partitions data across its back-end storage system. For DynamoDB tables with less than 10 gigabytes of data per table and read and write requirements less than 3,000 and 1,000 IOPS respectively, we don't need to give too much thought to the primary key and how uniform data access is. If, however, we need to scale past these limits, we will need to ensure that hotspots are avoided to allow us to scale efficiently. For example, for a table with multiple partitions, if we use mobile device ID as our primary key, and we find that the majority of interactions are from 5% of the devices, then even if the device ID is a well-distributed hash, most of the reads and writes will hit the same DynamoDB partition. If we choose a sensible primary and secondary key, we might find that our customers fall into 2 or 3 groups, each with different access patterns. For example, let's imagine that 5% of our records in our database correspond to enterprise customer records, with over 100 times the I/O requirements of that of other customers. Will we over-provision our single DynamoDB table to accommodate requirements for only 5% of users? In this situation, we should consider whether it makes economic sense to create 2 tables, each with different read and write IOP configuration. Sometimes we may want to perform a query against an item other than the table's primary key. Performing a scan operation on every item in a table is obviously a highly inefficient way to read data. Thankfully, DynamoDB supports one or more secondary indexes. Secondary indexes allow us to perform a query or scan operation on data using alternative attributes to the primary key. It does this by maintaining a secondary data structure that contains a subset of attributes from a table, along with the alternative key to support query operations. It's not necessary to store or project all attributes into the secondary index. If we perform a query but some of the attributes we requested are not projected into the secondary index, DynamoDB will fetch them from the source DynamoDB table. This will, however, require the entire item being read from the table, which will add additional latency and I/O operations, not to mention effectively reducing the size of a query below the 1 megabyte maximum. This is an area we should look at closely when it comes to optimizing secondary indexes for performance. Using secondary indexes for infrequently queried attributes can contribute to increased storage and I/O costs. In particular, tables that receive frequent updates to the I/O operations required to maintain secondary indexes can be significant. If we expect a higher ratio of writes to reads and plan to use secondary indexes, we should consider reducing the size of an item written to the index by projecting fewer attributes. However, given that writes to a DynamoDB table are in 1K blocks, reducing the size of objects below 1K will not improve performance, as that's the minimum we can consume. We can and should increase and decrease the read and write IOP performance of a DynamoDB table to accommodate IO profiles that vary significantly over time. However, for short-lived spikes in IO, Dynamo provides a useful IO bursting feature. When we are not fully utilizing a partition's throughput, DynamoDB reserves a portion of the unused capacity for later bursts or throughput usage. DynamoDB currently reserves up to 5 minutes of unused read and write capacity. We should use this additional capacity to cope with unexpected sharp spikes in demand rather than peak demand. We should be careful to avoid over-optimizing for efficiency at the expense of availability and performance. We don't always have control over I/O, but when we do, for example for batch workloads, we should look for opportunities to spread I/O over a longer period of time, thereby reducing the overall I/O requirements on individual DynamoDB tables. Now that we have covered some of the basic performance considerations for indexes, let's take a closer look at how data is distributed on the underlying DynamoDB storage platform. The effective available IOPS for a DynamoDB table is dependent on the product of the number of partitions and the throughput per partition. As DynamoDB primarily distributes data within a table based on its primary key when possible, we should choose a primary key that's evenly distributed. This is not just a consideration for the format of the primary key, but our read and write operations too. If 95% of our I/O hits 5% of our items, then access will not be uniform. While DynamoDB handles partitioning automatically for us, there are some performance limitations that we need to be aware of to avoid unnecessary operating costs. DynamoDB partitions are limited to 10 GB in size. Furthermore, a single partition can only support up to 3,000 read IOPS and 1,000 write IOPS. The number of partitions is controlled by which of these limits is hit first. For example, imagine we have 15 GB of data and require 4,000 read capacity units and 1,000 write capacity units. Then our I/O requirements will mean we need 3 partitions, whereas the storage requirements only require that we need 2 partitions. In this video, we will be looking at AWS Service Limits. We will start by explaining what AWS Service Limits are, their types, and potential impact on our use of the AWS platform. We'll then highlight some of the key limits that we should be particularly mindful of and explain how we can track our usage against them. Next, we'll cover how we can request an increase to a service limit and conclude by covering the key design considerations. The default limit for each AWS service is documented under the general section of the AWS documentation website as shown by the URL in the slide. As stated in the documentation, service limits are limited by AWS account per region unless otherwise stated. The documentation also states that only those limits that can be changed are listed on this page. While this is generally correct, we should always cross-reference this with information from the respective AWS service documentation, as there are some examples where this isn't quite the case. The S3 bucket limit is one such example. Default AWS service limits are generally either soft limits, that is, they can be increased, or hard limits, and cannot currently be increased. This doesn't necessarily mean that they can never be increased, but we should cautiously assume that they will not during the design process. The third type of limit can be considered a fuzzy limit. Whether it can be increased or not really depends on how we use the service. We'll look a little more closely at this later. Thankfully, most limits can be increased, and those that cannot can be designed around without significant additional effort on our part. Most potential problems arise during operations rather than the design process, so provided that we take some basic steps, we should be easily able to avoid service limits impacting us too greatly, both during the design and operational stages. AWS throttling applies to each AWS service on an account level basis, and not on an IAM user level. While AWS currently does not publish limits for API throttling, each service API returns a suitable error message if we exceed the rate. In the case of EC2, the error code is request limit exceeded. We should check for this error code and use exponential backoff to avoid further throttling. If there is a legitimate reason for a given request rate, then we should request an increase via the AWS Support team. The next service limit to be aware of is the 100 buckets per account limit. This is a cumulative limit across all AWS regions. Therefore, if we have 50 buckets in US West 1 and 50 buckets in US West 2, then we have reached our limit. At the time this video was recorded, this was a hard limit and could not be increased. The remaining limit highlights relate to Amazon VPC. The first we'll consider is the number of security groups per VPC. The current default limit is 100. This is a fuzzy limit, as it may be increased depending on how we reference other AWS security groups. For this reason, a request to increase this service limit may be denied by AWS Support in order to protect the network performance of our EC2 resources and those of other customers. The last two limits we will highlight are the number of rules per security group and the number of security groups per network interface. The current default limit of rules per security group is 50, and the number of groups per network interface is 5. While we can increase the number of rules per security group, the product of the two numbers cannot exceed 250. So given that there are AWS service limitations, it's important that we know what they are and what our usage currently is. While this is mainly an operational concern, it can impact architecting for the AWS platform too. Thankfully, AWS Trusted Advisor simplifies this task. AWS Trusted Advisor is available via the AWS Management Console. Under the section Service Limits, we can see each of our service limits, what our current usage is, as well as a color-coded status message indicating whether we should raise a support request to increase a limit if possible. For customers with business or enterprise support, they can programmatically interact with Trusted Advisor and track their limit usage. This significantly simplifies operational planning at scale. While we can use one of a number of programming language libraries and SDKs to interact with Trusted Advisor, the command line tool or PowerShell tools provide a simple but effective way to extract the information we require. Refer to the URL in the slide for more details on interacting with Trusted Advisor programmatically. Requesting an increase to a service limit is quite straightforward. We just need to create a new support case in the Support Center section of the AWS Management Console. We choose Service Limit Increase as the reason for creating the support case and select the service we are interested in. After entering the relevant service information, the case is lodged and is attended to as per the SLA of our current support contract. Service limitations can impact both operations as well as the design process. With suitable tracking and capacity planning, there is little reason why this should impact operations. From an architecture perspective, provided that we are aware of the limitations, we can design around them. For example, the VPC service limitation can be addressed by thinking carefully about at what scale a given VPC will hit a service limit. In particular, how many applications can we deploy before hitting the maximum security groups per VPC limit? If commonly referenced resources reside in a peered VPC, then we'll need to refer to those by CIDR block anyway, so a request to increase the limit should be approved by AWS. If our frequently referenced resources reside within the same VPC, then we either need to place them in a subnet and reference them by CIDR block, or potentially create a new VPC when we have reached this upper limit. Another approach is to share security groups between applications, thereby flattening or joining some of the security domains. This of course impacts our security posture, so it's best suited to platform or container deployments where multiple applications or services reside on the platform. The Amazon S3 bucket limitation is a little easier to solve. If we require more than 100 S3 buckets, then we can create additional AWS accounts and use bucket policies that make reference to one or more principals to restrict access. This is in contrast to the alternative approach of using IAM policies to restrict access to buckets and their objects. In this video, we will be looking at Amazon Compute Services from the perspective of scalability. We will start with a brief introduction to the family of Amazon Compute Services and highlight the focus of this video. We will then summarize scale-up operations for Amazon EC2 and conclude by looking at how the EC2 autoscaling service can automatically help us scale out resources. AWS provide a number of cloud-based computing services. They include Amazon Elastic Compute Cloud EC2, AWS Lambda, and the Amazon EC2 Container Service. There are also a number of supporting services such as the EC2 Autoscaling Service, Amazon Virtual Private Cloud, and the Elastic Load Balancing Service ELB. The main focus of this video will be options for scaling EC2 resources with a particular emphasis on scaling out using the EC2 Autoscaling Service. When we think of scaling, two options typically come to mind: scaling up and scaling out. Scaling up is simply just increasing compute, memory, or storage resources for an EC2 instance. The EC2 service provides a number of scale-up options. Instance resources range from one virtual CPU, 1 GB of memory, and low network and storage profiles for a T2 micro, right through to 40 virtual CPUs, a quarter of a terabyte of memory, and 10 gigabit network connectivity for the very largest instance types. A number of EC2 instances are also optimized for network I/O, having dedicated bandwidth for storage instead of sharing the available bandwidth with application traffic. We cover scale-up operations for EC2 in detail in the Amazon Compute Services performance video in this series. At some point, most systems need to scale past a single node. In some cases, this is driven by a performance bottleneck. In some cases, it's required to protect against failure. In other cases, we might get a better return on our investment by using smaller components that we can incrementally increase or decrease in size in response to changing operating conditions. That being said, scale up is generally a simple operation. We simply choose a different EC2 instance type. Scaling out, however, is more complex, with the degree of complexity being heavily dependent upon the application or service we are considering. For example, if the original resource is a worker node and a service that just checks in with a central job management service, picks up a job, completes the task, then repeats, scaling out is relatively simple. We just need to increase the number of workers and ensure that jobs are allocated to only one node at any given time. If, however, we consider scaling out a web service of some sort, then we will need to decouple the client from what is now one or more hosts providing the service, not to mention managing state. Amazon's Elastic Load Balancing Service, ELB, combined with Elastic Cache and auto-scaling can help with decoupling, managing state, and scaling compute resources respectively. Let's take a closer look at the Amazon EC2 auto-scaling service. The auto-scaling service is currently restricted to EC2 compute resources. It allows us to control the scale out and scale in of EC2 compute resources based on an auto-scaling policy that we define. The auto-scaling service consists of three main components, namely launch configurations, auto-scaling groups, and policies. Let's take a closer look at each of these. The first component of auto-scaling that we will look at is the launch configuration. This is where we specify the specific properties of EC2 instances that will be launched. A launch configuration allows us to specify the Amazon machine image or virtual machine template we want to use. We can also specify an IAM role, an identity and access management role, thereby giving each instance permission to interact with AWS services on behalf of a given account. There are also parameters to control the tenancy and consumption models, as well as parameters to automatically associate resources with security groups and a virtual private cloud via the VPC linkage feature. This will make a little more sense as we walk through a simple example. Let's take a look at how to create a launch configuration via the AWS Management Console. First, we log in and navigate to the auto-scaling section located within the EC2 Services tab. We select Create Launch Configuration, and then we choose an Amazon Linux AMI to base our EC2 instances on. We select T2 Micro EC2 instance type and give the launch configuration the name AWS Demo. For the purpose of this example, we can leave the storage options as default. Next, we need to define the security group that instances will be associated with upon launch. In this example, we're going to choose to create a new group. As we will place the auto-scaling group resources behind a load balancer, we select the security group associated with the ELB as the source of incoming web traffic. Finally, we review and create the launch configuration. The next auto-scaling component of interest is the auto-scaling group. Auto-scaling groups allow us to specify a number of options, including the size, location, association, and health check properties of resources defined by the launch configuration. Let's take a closer look at some of the more common options. The first option naturally leads on from the previous slide. As we have defined a launch configuration, we need some way to associate it with an auto-scaling group. Group limits restrict the maximum and minimum number of EC2 instances that can exist within an auto-scaling group. Even if our application is static from a load perspective, auto-scaling groups still provide a very useful feature. We can use them to automatically replace failed resources. For example, we could set a minimum equal to 2 and a maximum equal to 2. This will always ensure that we have 2 instances running. The next property is the VPC and subnet identifier. This allows us to place resources in specific private network segments and availability zones. We can also associate resources in an auto-scaling group automatically with an Elastic Load Balancer. This option provides the necessary glue to allow us to decouple a load balancer from a web application while still allowing each to scale independently. Next, we have the health check type and grace period. The grace period is the time taken for the health checks to be performed on an instance after it has been launched. The health check type can either be based on the result of an EC2 status check, that is the instance accessible via the network, or a health check performed by a load balancer, such as an HTTP GET of a given resource. Let's take a look at how to create an autoscaling group. Navigate to the autoscaling section, located within the EC2 Services tab. Then select Create Autoscaling Group. We give it the group name AWS Demo and specify the starting group size to be 2 instances. We then choose the VPC and subnets we want to associate with the autoscaling group. Scrolling down to the Advanced section, we specify the elastic load balancer we want to automatically associate resources with. We also configure the health check to be performed by the load balancer and set the health check grace period to be 300 seconds. For the time being, let's keep the number of resources in the autoscaling group equal to its initial default size. After a final review, we are now ready to create the group. If we now change to the EC2 dashboard, we can see that the 2 EC2 instances are in the process of being initiated. The final component of autoscaling is the autoscaling policy. The first property of the autoscaling policy is the autoscaling group. We then have the adjustment type. This specifies whether we want to change the number of resources in the group to a specific value, increase it by a fixed amount, or percentage. We also have control over the scaling adjustment. This is the unit of resources that's associated with the adjustment type. For example, if adjustment type is set to change in capacity and scaling adjustment is set to +1, then a single resource will be added when the policy is triggered. We then have the cooldown parameter. This is the minimum amount of time between successive scaling activities. Finally, we have a lifecycle hook. This is a separate object that makes reference to an autoscaling policy. It's an event such as a CloudWatch alarm that we want to use to trigger the scaling of policy. Let's go back to our existing autoscaling group definition. This time we're going to change the scaling policy from keep this group at its initial size to use a scaling policy. We're going to select the scaling policy of between 1 and 2 instances and create an alarm-based lifecycle hook. When the alarm is raised, it will have the effect of adding an EC2 resource to the autoscaling group. The alarm will be triggered when the average CPU utilization across our autoscaling group gets to 75% for one 5-minute period. All that's left to do is review the autoscaling group changes, and our revised event-driven autoscaling will take effect. In this video, we will be looking at Amazon storage and content delivery services from the perspective of scalability. We will start with a brief introduction to the Amazon storage and content delivery services and highlight the focus of this video. We will then look at scalability considerations when using Amazon Simple Storage Service, S3, Amazon Glacier, Elastic Block Storage, and the AWS Storage Gateway. While the need to scale a resource is often driven by a need to increase performance, this isn't always the case. Sometimes we just need to access larger resources, such as storage volumes, object sizes, or more storage containers. This will be the subtle focus of this video. AWS provides a number of cloud-based storage and content delivery services. They include Amazon S3, Amazon Glacier, Amazon Elastic Block Storage, EC2 Local Storage, Amazon Elastic File System, the Import-Export Service, Storage Gateway, and Amazon CloudFront. During this video, we will look at the main scaling considerations when using Amazon Simple Storage Service, S3, Amazon Glacier, Elastic Block Storage, and the AWS Storage Gateway. Amazon Elastic Block Store, EBS, provides persistent block-level storage volumes that may be attached to EC2 instances. The introduction of general-purpose and provision IOPS EBS volumes has all but eliminated scaling limitations of the original EBS service. Using these volume types, we can create volumes of up to 16 tebibytes in size. This is the maximum file system size for commonly used file systems such as ext4 and far larger than basic NTFS volumes. If we don't need the additional performance of general purpose and provision IOP volumes, then magnetic storage has an upper limit of 1 tebibyte. If we need to go past this limit, then we have 2 choices. Either we attach multiple volumes to the host and use software RAID to create a meta device, or we pay for the more expensive storage in exchange for simplified operations. Software RAID was a common and often necessary approach to achieving higher IOPS for database servers when the EBS service was first launched. Today, this is generally not necessary, as a single EBS volume supports up to 20,000 IOPS. Sometimes we might want to attach a large number of volumes to an instance to increase its storage capacity. Assuming that the required performance is possible, we can attach up to 40 volumes to a Linux EC2 host. Anything more than this is supported on a best efforts basis by AWS. For Windows instances, this limit is a little lower and depends on the storage paravirtualization driver we are using. Using the AWS or Citrix driver allows us to scale to 26 volumes, whereas the Red Hat driver allows us to scale to 17. Once again, if we attempt to scale past these limits, then support from AWS will be on a best efforts basis. Amazon's Simple Storage Service S3 is a highly scalable object data store. Storage is divided into containers called buckets. The number of objects stored in an S3 bucket currently has no upper limit. We can keep adding objects and the bucket expands to accommodate each object automatically. However, there are some scale limits that we need to be aware of. Firstly, there is a service limit of 100 buckets per AWS root account. We cover this in the service limits video in this series, so refer to that video for suggestions on how to architect around this limitation. The next scalability limit we will look at is the maximum object size we can store in an S3 bucket. Currently, a single object can be between 1 byte and 5 terabytes in size. If we need to store objects that are greater than 5 terabytes in size, then we will need to slice the object up and store it in chunks, taking care to store the grouping and ordering of chunks in an inventory record of some sort. We could use DynamoDB to record this data. While an individual object can be up to 5 terabytes in size, individual HTTP put operations are limited to objects up to 5 gigabytes in size. Therefore, we will need to perform multiple put operations to upload large objects. AWS recommends that we use its multi-part upload API call for objects greater than 100 megabytes in size. This provides a number of performance-related benefits in addition to helping overcome this upper limit. Now let's look at Amazon Glacier. Amazon Glacier is a data archiving and online backup service. Data, represented as one or more archives, is stored in a Glacier vault. Similar to S3, there is no upper bound on the amount of data that we can store in the service. However, there is a limit on the maximum size of any single archive. This is currently 40 terabytes in size. This is 8 times as large as the maximum size of an S3 object and almost 3 times as large as the maximum size of an EBS volume. If we need to archive images that are greater than 40 terabytes in size, we should either consider making the object to be archived smaller, for example by reducing the number of files in the archive, or chopping the archive up into multiple pieces, similar to what we did with S3. Once again, we have a limitation on the maximum size of an object we can archive with a single put operation. It is a little smaller than S3 at 4 gigabytes. Multi-part upload best practices once again apply for objects greater than 100 megabytes in size. The AWS Storage Gateway provides an on-premise performance-optimized gateway to cloud storage. It has 3 main configurations. We can use it as a cached gateway. In this configuration, only the most frequently accessed data is stored on-premise and less frequently accessed data is stored on S3. Data is transparently moved between on-premise cache and S3 to optimize performance and storage use. It effectively allows us to scale our on-premise storage by leveraging inexpensive cloud-based storage. We can also use Storage Gateway to back up our on-site data volumes. In this configuration, the Storage Gateway will make point-in-time snapshots and asynchronously back them up to S3. The third configuration is to use it as a virtual tape library. In this scenario, it integrates with local backup software and either archives to S3 or Amazon Glacier. The current limitations for the Gateway cached configuration are individual storage volumes can be up to 32 terabytes in size, with the maximum size of a cache storage volume being a sensible 16 terabytes. Collectively, a single gateway can have up to 20 volumes and a maximum of 150 terabytes of storage. The equivalent limits for a gateway storage volume configuration are 16 terabytes for the storage volumes and 192 terabytes for the total storage gateway. When we are using the storage gateway as a virtual tape library, individual virtual tapes are limited to 2.5 terabytes in size, with a total tape library size of 150 tebibytes. Tape libraries and tapes can be expensive capital investments. The storage gateway allows us to effectively scale our existing on-premise investment over time and reduce its footprint. If we require more storage than a single gateway provides, we will need to scale out and use multiple storage gateways. In this video, we will be looking at Amazon Database Services from the perspective of scalability. We will start with a brief introduction to the family of Amazon Database Services and highlight the focus of this video. We will then look at scaling considerations for the Amazon Relational Database Service, RDS, Amazon DynamoDB, Elastic Cache, and conclude with Amazon Redshift. AWS provides a number of cloud-based database services. This includes the Amazon Relational Database Service, RDS, Amazon DynamoDB, Amazon SimpleDB, Amazon Elastic Cache, and Amazon Redshift. During this video, we will have a short segment on each of these services except for Amazon SimpleDB. Amazon Relational Database Service, RDS, is a managed database platform that supports MySQL, Postgres, Microsoft SQL Server, Oracle, and Amazon's Aurora database engine. When creating an RDS instance, we are able to choose from one of around a dozen instance types from the current generation of resources. Each instance type has a different amount of compute, memory, and network resources. Currently, these range from 1 virtual CPU and 1 GB of RAM for a DB2 micro instance, and up to 32 virtual CPUs, 244 GB of RAM, and 10 gigabits per second I/O for the largest instance type. However, sometimes even the very largest instance type may not provide enough resources. One common approach to scaling on-premise is to use multi-master or active-active clusters to continue to scale out past one node. On the AWS platform, in part due to restrictions around multicast and broadcast traffic, when we exhaust available resources on a single host, we need to take a slightly different approach. What we do to accommodate scaling depends on where the bottleneck is. If the bottleneck is I/O related and we're using the MySQL database engine, then we may consider using Amazon's Aurora database engine instead. Benchmarks have shown that throughput can be up to 5 times that of MySQL version 5.6 on similar virtual resources. Each of the available database engines supports different numbers of storage IOPS. This is a result of the combination of the database's page size, the maximum storage size, and storage to IOPS ratio. If our application supports multiple database engines, then choosing an engine that supports greater IOPS may avoid scaling past a single instance. Conventional approaches to offloading from a database can also be used. For example, we can make use of an in-memory cache to respond to frequently requested but relatively static read requests. Another approach to scale out read requests is by creating one or more read replicas. At the time this video was created, read replicas were supported for MySQL, Postgres, and Aurora database engines on the RDS service. Postgres and MySQL support up to 5 read replicas, but Amazon's Aurora database engine supports up to 15 read replicas. If the bottleneck is read-related, then the general approach is to shard data across multiple databases using traditional application sharding approaches. There are a number of publicly accessible articles and best practices for sharding across multiple database servers. Therefore, for brevity, we will not cover this during this short video. Amazon DynamoDB is a fully managed, high-performance, low-latency NoSQL database with support for strong, consistent reads. While DynamoDB has some performance limitations per partition and default limits, to all practical purposes, the service can scale to support whatever scale we need. There are a number of areas we can optimize for performance before simply scaling our read and write capacity units. These are covered in detail in another video in this series. We will assume that our use of the existing read and write capacity of each DynamoDB table has already been optimized. DynamoDB has generous default limits for the number of read and write capacity units. Resources in the US East region are set to 40,000 reads and writes per DynamoDB table, and 80,000 reads per account. This can be increased by AWS using the usual support channels. We don't need to over-provision a DynamoDB table at the time of creation. We can use the update table API call to increase or decrease the read or write capacity of the table during operation. While we can increase the capacity on a given table as often as we like, decreasing provisioning throughput is currently limited to 4 times per UTC calendar day. Furthermore, during the scaling operation, the table operates with the original capacity. When architecting using the DynamoDB service, we can take advantage of scaling our data tier in accordance with changing operating conditions. However, scaling should be less aggressive than when using EC2 autoscaling. Elastic Cache is Amazon's managed in-memory cache service. It currently supports two of the most commonly used in-memory database engines, namely Memcached and Redis. Elastic Cache supports a number of scaling features. The first is a number of different node instance types. Currently, this varies from one virtual CPU and half a gigabyte of memory for the smallest instance type, right through to 32 virtual CPUs and 237 gigabytes of memory for the largest instance type. In addition to scaling up, as we would expect, Elastic Cache has support for scaling out. The Memcached database engine on Elastic Cache has support for up to 20 Elastic Cache nodes. Data, however, needs to be sharded across each of these nodes by clients interacting with the service. There are a number of publicly accessible articles and best practices for sharding across multiple in-memory database servers. Therefore, for brevity, we will not cover this during this short video. The Redis variant of the Elastic Cache service has some useful scale-out features. We can scale out to support up to 5 replication groups that support reads against the primary cache cluster. From a design perspective, we should note, however, that the data synchronization between master and replicas is asynchronous. Therefore, if we require strongly consistent reads, our reads should be directed towards the primary cache cluster. Amazon Redshift is a fully managed petabyte-scale data warehousing service. It uses a columnar database to store data. This naturally gives it strong scale-out properties and allows for I/O and compute to be distributed in parallel across multiple nodes. Amazon Redshift supports a small number of node instance types that are well suited to data warehousing workloads. Currently, the largest instance type available has 36 virtual CPUs, 244 gigabytes of memory, and 16 terabytes of local storage with a data I/O profile of 4 gigabytes per second. While the compute and storage capacity of a single node is significant, given Redshift is a data warehousing service, hundreds of terabytes or even petabyte scale databases are not uncommon. Redshift supports clusters with multiple nodes. The range for a given cluster is determined by the node instance type as described at the URL in this slide. Currently, a cluster using the largest instance type supports a range from 2 to 128 nodes, thereby allowing us to scale up to 2 petabytes in size. From a design perspective, scaling operations can be done dynamically by adding additional nodes to the cluster. However, during a scaling operation, the original cluster will only be able to accept read requests. In this video, we will be looking at strategies to increase data durability, which in turn will allow us to achieve stricter recovery point objectives. We will first take a close look at what we mean by recovery point objective. We will then suggest a level-based approach to help us reason about it in a cloud environment. We will then look at cases where data is stored in Amazon S3, EC2, EBS, RDS, and DynamoDB, and provide guidelines for estimating the RPO as well as recommendations for increasing it for each level. A recovery point objective, RPO, is one of the key design requirements for business continuity. It specifies the maximum targeted period of data that the business can afford to lose for a given system during a major event. A major incident does not need to be as severe as a disaster recovery scenario. It could be the failure of storage on a critical component of a system, such as a database server. It's helpful to think of incidents at 3 different levels. The first is the failure or loss of data for a storage component of a single node, such as the failure of a local ephemeral volume attached to an EC2 instance. The second level to consider is failure and loss of data at the level of an availability zone, for example, the loss of data in an EBS volume. The next level would be failure and loss of storage at a regional level. This allows us to think about the expected RPO for one of 3 different types of incident. A number of Amazon's web services and their resources have associated durability or annual failure rates. For example, objects stored in S3 have a durability of 11 nines, whereas an EBS volume has an annual failure rate of between 0.1 and 0.2%. While it would be helpful for us to be able to translate between these measures of failure and calculate confidence intervals for achieving a given recovery point objective, we would need to make some assumptions about the statistical distribution of failure. If we assume failure rates follow a Poisson distribution, we can estimate a value for lambda and from there the probability of having 0 failures in a given time period along with confidence intervals. We will not have time for such a thorough statistical analysis of failure during this short video, or consider whether our assumptions about the distribution of failure is even valid. Thankfully, we can avoid getting too bogged down in this level of detail by making a few assumptions based on published data and common sense. Given that RPO specifically refers to protecting recent data, we will primarily focus on a select number of Amazon storage and database services. We can extend the techniques used in this video for other services too. That is left as an exercise for the viewer. Amazon S3 distributes multiple copies of objects across a region. Therefore, we only need to concern ourselves with RPO and failure at level 3. At 11 nines of durability, Amazon's S3 is the current gold standard for data durability. 11 nines of durability means that if we have 10,000 objects stored in S3, then we can expect to lose one of these objects every 10 million years. The expected failure rate does not appear to be dependent upon how old an object is. However, if our system contains 10 to the power of 15 objects, then we can expect to lose one object approximately every hour. In this case, if we replicate objects once an hour from one S3 bucket to another bucket in a different region, then assuming the loss of an object is independent between regions, we reduce the frequency of losing an object from 1 in 10 to the power of 15 to 1 in 10 to the power of 30. When we consider that an object is a snapshot of a volume or an archive containing many files, then these numbers are truly staggering. If we truly believe that these figures are achievable by the S3 service, then it's clear that the biggest risk to data loss will be from us as users, either due to user error, a security vulnerability, or application software updates corrupting our data. We should use S3's versioning capability to help protect against this. As a final measure for achieving RPO, we should back up data to Amazon Glacier. As S3 and Glacier provide the highest levels of data durability on the AWS cloud, we will use them as the upper limit of what's possible and measure the RPO of a solution design by the amount of data that can possibly be lost before it is safely stored in S3. The majority of EC2 instances come with one or more ephemeral volumes. Data only persists while the instance is running. A stop and restart operation will result in all data being lost. Data residing on local ephemeral storage is only marginally more persistent than data in memory. We should not use it to store data that can impact our RPO unless we synchronize the data to a secondary location. Going back to our 3 levels of RPO, without replicating data from the host, the expected failure rate of loss of data will be that of the EC2 instance. This is definitely not a good solution if the data is deemed to be important by the business. The effective RPO here is the maximum age of data stored on the volume. Replicating data in real time from one instance to another in a different availability zone will reduce the RPO to the replication lag between availability zones. However, we are still only protecting against multiple nodes failing. Using an EBS volume instead of an ephemeral volume is a more sensible option, as we will increase our expected annual failure rate to 0.1 or 0.2%. We have now decoupled the failure of an instance from that of its storage, albeit within a single availability zone. This corresponds to the second level of RPO that we introduced earlier. While traditionally we would create RAID arrays to reduce the effective failure rate on physical hardware, EBS volumes are already RAIDed, so it's generally not recommended. To achieve the third level of RPO, we need to back up data to S3 or Glacier. While we can do this from a local ephemeral volume, it's far easier to use EBS's snapshot feature. A snapshot frequency of 1 hour will result in an RPO of 1 hour and protect against the loss of all data in one or more availability zones, depending of course on the size of the AWS region. Now let's take a look at higher level storage services such as RDS. RDS uses EBS volumes to store data, so there's no level 1 configuration. If the database server fails, the EBS volumes will be reattached to another compute resource in the same availability zone. However, to protect against data loss in an availability zone, we should run instances in a highly available multi-AZ configuration. We have now reduced the RPO to the effective replication lag, which for synchronous updates is 0 seconds. This still doesn't provide protection against the storage associated with both instances failing or being corrupted at the same time. If we want to achieve an RPO for level 3, then we will need to schedule regular backups to S3. It's impractical to back up a database more frequently than a few times a day. Generally, it's a once-a-day operation. For highly available configurations, RDS provides a useful feature allowing us to recover the primary node from a period of up to 5 minutes ago. If a 24-hour RPO isn't sufficient in the event of the failure of multiple availability zones at the same time, then we need to consider asynchronous replication of data to a secondary region. RDS currently provides support for cross-region replication for some of its database engines. We can therefore achieve an RPO for a regional failure in the order of seconds, as determined by the inter-region replication lag. Now on to DynamoDB. Similar to S3, DynamoDB distributes data across a number of AWS facilities within a region. Therefore, our failure level has a minimum value of 3. Unlike an RDS instance, it's common to back up DynamoDB tables more frequently than once a day. We could, for example, reduce our RPO to 4 hours by using the Elastic Data Pipeline service to back up 6 times a day. We can probably reduce the RPO even further, but at some point, depending on the size of our tables, application load, and provisioned read and write units, we'll reach a point where it just isn't economically practical. If we want to reduce the RPO even further at level 3, then we can use the DynamoDB Streams Kinesis adapter to replicate updates to a DynamoDB table in another region. In doing so, we can take our RPO for level 3 down to a matter of seconds. In this video, we will be looking at compliance on the AWS platform. We will start by highlighting the scope of this video, explain what compliance is and why it's important. We will then take a look at some of the key areas covered in the AWS Risk and Compliance White Paper. Next, we will summarize the current state of the AWS assurance programs, highlighting a few programs of particular interest, and conclude by reviewing the key design considerations. It is both challenging and potentially dangerous to cover compliance in a short video, as this is not a topic that we should simply skim over. It warrants comprehensive coverage, which the AWS compliance team have achieved. Therefore, the main focus of this video is to summarize the key sources of information and resources we need in order to dive deeper on what is one of the most important areas when adopting the AWS platform. Let's take a moment to remind ourselves what compliance actually means. Compliance is conforming to an act, standard, control, policy, program, or regulation, examples of which include the US Health Insurance Portability and Accountability Act, the Payment Card Industry, PCI, Data Security Standard, DSS, and the Service Organization Controls 1, or SOC 1. Compliance is important because it helps us ensure a company meets its legal obligations, often to protect the health, safety, and welfare of others. Organizations operating in highly regulated industries can be heavily fined and receive negative press if they are found to be non-compliant. As architects, we need to appreciate the standards, policies, specifications, and laws that our organization must adhere to. The geographical region, industry, governing regulatory bodies, and sensitivity of the data will of course greatly influence this. AWS has developed a comprehensive selection of white papers, one of which is the AWS Risk and Compliance White Paper, available via the Compliance section of the AWS website. This document is a valuable asset to help us efficiently integrate AWS Web Services into our existing control frameworks. Building on what we already know about deploying applications on AWS, the document covers how the AWS shared responsibility model extends to include IT controls and emphasizes the importance of understanding where the control boundaries lie as we consume different AWS services in different AWS regions. It then goes on to provide guidance on how we should use the AWS certifications and third-party attestations to perform our control evaluations and verification procedures. As many adopters of the AWS platform may not have previously engaged with outsourcers, but still have audit and compliance requirements, the white paper provides a useful chapter on how to evaluate and integrate AWS controls, thereby ensuring that all controls are accounted for and verified as operationally efficient. The Risk and Compliance section of the document provides guidance on how we can incorporate AWS controls into our governance framework, with a particular focus on risk management, information security, and AWS's control environment. The last section of the white paper is extensive and accounts for the bulk of the white paper. It provides an in-depth coverage of AWS reports, certifications, and an extensive list of third-party attestations. In particular, the white paper goes into great detail on the web services covered under each certification, something that we need to be fully aware of if we are to architect our applications for the AWS platform. The compliance section of the AWS website contains detailed information for each of the assurance programs and their scope. The next two slides are a summary of the current state of the assurance program, so always refer to the AWS website for the latest information. That being said, let us now look at a few of the key programs that we haven't yet mentioned. International Traffic in Arms Regulations, ITAR, control the export and import of defense-related articles and services on the United States munitions list. These regulations implement the provisions of the Arms Export Control Act. The AWS GovCloud US environment has been audited by an independent third party to validate that proper controls are in place to support customer export compliance programs for this requirement. One of the more common and widely adhered to standards is that of the International Organization for Standards ISO 27001. ISO 27001 is a widely adopted global security standard that outlines the requirements for information security management systems. AWS has established a formal program to maintain this certification. This certification reinforces AWS's commitment to maintaining transparency into their security controls and practices. There are no shortcuts when it comes to compliance. Organizations operating in highly regulated industries can be heavily fined and receive negative press if they are found not to be compliant. Our policy and controls will often be defined by dedicated policy and government teams within an organization. We need to take great care to ensure that these controls are implemented. Therefore, we need to become familiar with the compliance section of the AWS website. In particular, we need to take the time to read and incorporate the guidelines set forth in the Risk and Compliance White Paper into our designs. If our organization operates in a highly regulated space, such as healthcare or finance, then as architects we will need to be acutely aware of the key compliance requirements that we need to achieve. However, such organizations will no doubt have dedicated policy and compliance teams. Engaging with the policy and compliance teams early on in the adoption or investigation into the AWS platform will reduce the time to adoption and also ensure that we accurately understand compliance requirements. We should always start from the position of what was the architecture actually being used for. This may seem obvious, especially if we are architecting an application for a specific purpose, such as a Wikimedia server to allow internal marketing teams to collaborate. But what if, as part of the architecture process, we need to design a VPC, a virtual private cloud? We shouldn't assume that its scope will be restricted just to that application. That being the case, we need to understand what else it will be used for. Well, at least, what are the compliance restrictions of applications that will be deployed into it in its current state? Designing an architecture that can support non-material data will require different levels of rigor to one that can support PCI DSS Level 1 compliant applications. The limitations of our architecture should be clearly documented in the case that it will form part of an organization's shared infrastructure. Compliance on the AWS platform is constantly evolving. Not only are new compliance assurance programs being included as influenced by customer adoption, but assurance programs are being updated to include new web services and regions as AWS expands its service catalog and regional footprint. This creates two challenges for architects. Firstly, we may initially pass over a particular service for inclusion in one or more of our designs because potentially the service was out of scope of the assurance program. Secondly, we may want to deploy our application in a new region that isn't currently covered under the scope of an assurance program. For example, when the Frankfurt region was launched, it was not covered under the PCI DSS Level 1 assurance program. We should therefore regularly check the compliance section of the AWS website for updates on both the scope of services and the regional coverage. Finally, security is a shared responsibility on the AWS platform. AWS maintains the security of the cloud, but the security in the cloud is our responsibility. The same goes for IT controls. We need to understand where the control boundaries lie when we consume AWS services in different AWS regions. In this video, we will be looking at network access control lists on the AWS platform. We will start off by looking at what network access control lists are and why we should use them, followed by a walkthrough of how to create and manage ACLs by the AWS Management Console. We will then look at the default network ACL that gets created whenever we create a new VPC, and we will finish up by looking at design considerations when using network ACLs. Network ACLs are a stateless network layer security feature for subnets in an Amazon VPC. While a network ACL can be associated with multiple subnets in a VPC, it cannot be associated with multiple VPCs. Each network ACL consists of a series of inbound and outbound rules. Inbound and outbound rule groups consist of a number of rules that are ordered by sequence number. This is important as rules can either allow particular network traffic or deny that traffic. As we will see shortly, the order of rules makes a big difference to whether traffic is allowed to pass through a network ACL. Network ACLs can be managed using the AWS Management Console, API, or SDK, or even one of the many command line tools such as the AWS CLI package for Python or the AWS tools for Windows PowerShell. For the purpose of this illustration, we will focus on the AWS Management Console. As we have seen a number of times, programmatic approach to managing resources provides significant benefits in the areas of operational efficiency, consistency, automation, and security. For this reason, it is generally the recommended approach. The screenshot shows the network ACL creation interface. In this example, we're going to create an ACL called Perimeter Network ACL and associate it with the default VPC. By default, we can see that the network ACL contains a single inbound rule of deny all traffic from everywhere. This default rule ensures that resources we place into a subnet associated with a network ACL will not be accessible from outside of the subnet. This is a sensible default posture, albeit a not particularly useful one yet. Let's create a rule that allows hosts residing in the network 10.10.10.0/27 to connect via TCP port 22. This network ACL rule is indicative of a rule associated with a subnet containing bastion hosts or jump hosts. By giving this rule the number 100, we can see that it comes before the current deny rule. Similar to inbound rules, by default we have a single outbound rule that denies all traffic. Once again, this is a sensible default position. As network ACLs are stateless, we need to specify an outbound rule. This is in contrast to security groups that are stateful and do not require a corresponding egress rule. As we cannot usually control the high port that a host will use when connecting to a host, we have to use a wide range of ports. In this case, 1024 to 65,535. This is to accommodate the variety of ports used by different operating systems or third-party services. If we can control this range, there is the opportunity to restrict this port range somewhat. But debugging network ACLs is almost always a result of outbound rules, ports, and destination CIDRs, so beware. As we would expect, by default, a network ACL isn't associated with a subnet. We can choose one or more subnets within a VPC to associate ours with. However, as with security groups, changes take effect immediately, so take great care, especially in production environments. Each VPC has a default network ACL. This is indicated by the field default, as shown in the summary section of the ACL. Unlike ACLs that we create, the default ACL cannot be deleted. As we can see, the default ACL allows all incoming traffic by default. This is indicated by the rule 100 coming before the last deny rule. Similarly, the default ACL rule allows all outgoing network traffic. While we cannot delete a default network ACL, we may wish to disable it by updating both the inbound and outbound rules to only contain a deny rule. This is useful to allow a potential situation where the network ACL is unintentionally associated with one or more subnets, and those subnets have no restriction on incoming or outgoing traffic. The first thing we need to consider when incorporating network ACLs into our designs is what resolution should they be at. For example, we can create a dedicated network ACL for each subnet in a VPC, but often this creates additional operational overheads with little or no security benefit. We can often reuse network ACLs for subnets that have similar network access requirements and use security groups for stateful granular access control. For example, we may choose to use a dedicated network ACL for perimeter security, but have common network ACLs for different application subnets. This is often a pragmatic balance of security and control versus operational efficiency. We also need to consider what access is required from other VPC subnets or on-premise infrastructure. Inbound and outbound ACLs should be the union of the required network traffic entering and leaving the subnets respectively. Take care when defining outbound rules, in particular ports, as the stateless nature of network access controls require that we specify all destination ports. Forgetting to add outbound rules is a common mistake that often results in extended debugging time. While the example in this video focused on managing network ACLs via the AWS Management Console, in practice they are managed as code and increasingly often using AWS CloudFormation. Given the far-reaching implications of configuration errors, changes should be thoroughly tested before updating existing CloudFormation stacks with associated SLAs. Furthermore, templates should be placed in version control and access restricted to network administrators only. Resource tags are available for network ACLs, so we should incorporate them into our designs. This makes auditing and reporting easier, not to mention it helps avoid mistakes resulting in modifying the wrong resource. While we cannot delete a default network ACL, we should take steps to ensure that we don't reduce our security posture by accidentally associating it with a network subnet. Update the inbound and outbound rules to remove all rules, thereby leaving only deny rules. In this video, we will be looking at the AWS Shared Responsibility Model. We will start by considering what is meant by a shared responsibility model. We will then look at internal shared responsibilities from the perspective of a consumer, deployment, operations, and security teams. We will then take a look at what AWS are responsible for from the perspective of infrastructure, and then by category of service. We will then look at the shared responsibility model for Amazon Elastic Beanstalk, and conclude by highlighting some of the key design considerations that we need to bear in mind as we architect for security. The shared responsibility model simply means that as consumers of an AWS web service, we are partly responsible for the security of resources that the service provides. For example, in the case of the Amazon Elastic Compute Service, EC2, we are responsible for the OS of a running instance. The degree to which we are responsible greatly depends on the web service in question, but broadly, it is related to the level of abstraction from the underlying infrastructure resources. Broadly speaking, as we move from infrastructure as a service to platform as a service and software as a service, AWS take on more of the shared responsibility. For example, deploying a relational database on EC2 requires that we take on more responsibility than if we were to consume the same database engine as part of the relational database service. This is because in the case of EC2, we are responsible for the OS and all services running on the host, whereas RDS provides a managed database in which we do not have access to the operating system. One area of shared responsibility that sometimes gets overlooked is within an organization. As an architect, we may fully appreciate the responsibility that our organization has when consuming an AWS web service, but unless the responsibility is clearly defined within internal groups without any responsibility gaps, then this can lead to a reduced overall security posture. As a minimum, the responsibility of security is shared between development, operations, and security teams, but this can often include a much larger number of groups depending on the size and the maturity of the organization. For example, it could easily be expanded to include storage, identity, and database teams, to name but a few. A discussion around shared responsibility would not be complete without at least mentioning AWS's infrastructure responsibility. Consider this as a high-level summary only and refer to the latest version of the AWS Security White Paper located within the Security section of the AWS website for a detailed explanation. AWS operates the cloud infrastructure that provides foundational infrastructure resources that their web services consume. AWS infrastructure includes the facilities, network, and hardware, as well as some operational software that supports the provisioning and use of these resources. AWS maintains a comprehensive list of compliance including SOC 1, 2, 3, SSAE 16, ISAE 3402, FISMA, PCI DSS Level 1 compliance, ISO 27001, ITAR, and FIPS 140-2. Compliance is an active area, so always refer to the compliance section of the security website for the latest assurance and compliance details. AWS is responsible for the physical and environmental security of their data centers. Amazon's responsible for the high availability of its infrastructure, and AWS has designed its systems to tolerate system or hardware failures with minimal impact to customers. Data center business continuity management at AWS is under the direction of the Amazon Infrastructure Group. The AWS network has been architected to permit us to select the level of security and resiliency appropriate for a given workload. This is facilitated by a world-class network infrastructure that is carefully monitored and managed by AWS. The boundary of shared responsibility varies by AWS service. That being said, as we have seen, AWS are responsible for the infrastructure that their web services are built upon. Broadly speaking, this is compute, storage, and networking at each of their physical locations in regions, availability zones, and edges. AWS then build upon each of these foundational infrastructure components to provide higher-level web services. While software as a service, platform as a service, and infrastructure as a service is a broad categorization of web service, it is helpful when thinking about what we are responsible for as consumers. As illustrated, in the event that we consume an infrastructure as a service-like service, such as EC2, our responsibility is greater. Not all web services sit neatly into one of these categories. Let's consider the Amazon Elastic Beanstalk service and see where our shared responsibility lies. Amazon Elastic Beanstalk is a service that allows us to deploy and scale out applications. We can think of it like an application platform service with increased flexibility at the application container level. It provides components of a platform as a service with the flexibility of an infrastructure as a service by allowing us to customize and manage the operating system and application server. AWS make it easy to deploy an application onto Beanstalk by providing a collection of ready-to-use Amazon machine images that we can use to base our application service platform on. These Amazon machine images are a secure starting point from which to launch our instance of Beanstalk. AWS regularly updates their collection of supported Amazon machine images and software repositories with the latest security errata. However, the responsibility is on us as consumers of the service to apply the security errata or update our environment to use the latest Amazon machine image. This is a simple task, but a task that we are responsible for nonetheless. AWS provides a large number of web services that span the continuum from infrastructure as a service, such as EC2, right through to fully managed software as a service, such as Amazon WorkDocs. As we move along the continuum, we need to appreciate not only what features the service provides, but equally importantly, where the lines of responsibility lie. AWS's current categorization of service such as compute or database will contain services with different security boundaries. As architects, we need to invest the time to understand where the boundaries of each are. After we understand what we need to be responsible for as an organization, the next stage is to consider how the responsibility will be shared amongst the internal teams. The responsibility can vary depending on the size of our teams, the maturity of the organization, regulatory requirements, and the dominant development methodology. While clearly it makes sense for the most suitable team to be responsible for a particular component of an architecture, what's equally if not more so important is that collectively between the various internal groups that all areas are covered. Network security is one area that can often be shared between development teams and network security teams. Take time to ensure that the lines of demarcation are documented and actively managed. AWS maintains compliance and certification with a large number of industry and government bodies. Always refer to the compliance section of the AWS website for the latest details. However, it's important to note that when consuming an AWS service, that we ensure that that particular service in question is covered under a particular compliance or assurance. In particular, if we refer to the PCI DSS Level 1 compliance, this is restricted to a subset of AWS services. While that subset of services is very large, it is a subset of services nonetheless. And finally, we should consider the entropy of security. As we have seen with services like the Amazon Elastic Beanstalk service, over time, if the individual operating system or application platform is not actively patched and managed by us as consumers, the overall security will decrease. It's therefore very important that we understand where the security boundaries are for services that combine elements of infrastructure as a service and platform as a service. In this video, we will be looking at security groups on the AWS platform. We will start by looking at what AWS security groups are and why they are useful. We will then look at the two main categories of security groups, EC2 Classic and EC2 VPC. Next, we will look at how we can manage security groups using the AWS Management Console, and then do the same using the AWS CLI tools. We will conclude by reviewing some key design considerations. Security groups are stateful firewall resources for EC2 instances. A security group's behavior, that is, its firewall rules, are controlled by security group rules. Rules are a collection of ports and protocols between a source and destination, similar to a traditional stateful firewall rule. Modifications to security group rules take effect immediately. Each EC2 instance associated with a security group will automatically be updated in near real time. Multiple security groups can be associated with a single instance. This is a powerful feature that allows us to efficiently manage and share common rule sets between groups of logically grouped instances. It should be noted that rules are additive. Security groups are only one component of a defense-in-depth approach to network access control. Their stateful nature makes them a great complement to using AWS Network Access Control Lists. Finally, there are two variations of EC2 security groups. First, we have the EC2 Classic variation, and then we have the EC2 VPC variation. The former is a predecessor to the latter, and while it's infrequently used today, for completeness, let's take a look at both of them in terms of their key features and their differences. EC2 Classic security groups were the first type of security group available. They were later usurped by EC2 VPC security groups, which we will look at shortly. Like most AWS services and resources, there are limitations that often evolve over time. One such example for EC2 Classic security groups is the number of groups per AWS region. This is currently 500. As always, refer to the AWS service documentation for the latest service limits. A real benefit of the first incarnation of security groups was their ability to refer to security groups belonging to another AWS root account. This significantly simplified restricting network access between EC2 instances between known, trusted AWS accounts. Two notable disadvantages of EC2 Classic security groups is that they only support ingress rules, and groups can only be associated with an instance at launch. While we can still modify rules associated with a running instance, not being able to detach or attach a security group can be an operational pain point. And the EC2 Classic variation of security group has only limited support for network protocols. This is restricted to TCP, UDP, and ICMP. Now let's take a look at EC2 VPC security groups, the successor to the Classic variation. As the name suggests, EC2 VPC security groups are associated with Amazon Virtual Private Cloud. Furthermore, each security group is associated with only a single VPC. As security groups are associated with a VPC, we can only make reference to other security groups in the same VPC. One of the great features of EC2 VPC security groups is their ability to be added or removed to an instance after it has been launched. Another highly valuable feature is being able to define security groups for both ingress and egress network traffic. Remember that the EC2 Classic variation only supports ingress rules, and EC2 VPC security groups provide support for all standard network protocols. If you are new to AWS, you may have noticed that each VPC contains a security group named default. The security group is created automatically when a VPC is created. By default, this security group denies all inbound traffic, but allows all outbound traffic. Therefore, any instance associated with a security group in the default state will be able to make outbound connections but not receive network traffic. This is a sensible, pragmatic default position. The default security group for each VPC cannot be removed. However, we are able to modify its rules. If we are particularly concerned about the possibility for a security group to be associated with an instance in error and potentially allow it greater access than it would otherwise be allowed, simply remove all egress rules. As we'd expect, we can modify security groups in a number of ways. The AWS Management Console allows for easy management and visual feedback on rules. Some particularly useful features include security group auto-completion, as shown in the screenshot. Here, we are creating an ingress rule to allow all hosts associated with a security group web server security group to access all hosts associated with security group application servers security group via the TCP port 8080. While our rules often refer to other security groups, sometimes we need to use CIDR ranges. For example, if we need to refer to resources residing in a different VPC or outside of AWS. And not forgetting, we also have the ability to define egress rules. As these are stateful, and the rule corresponds to the remote port which we will access and not the high unprivileged port the outbound connection will be initiated from. While using the AWS Management Console may be suitable for managing smaller environments, when we need to manage greater numbers of resources and need to protect against administrator error, we will typically use the command line tools and programming libraries to a much greater extent. For example, the screenshot shows how we can create a security group, tag it with a suitable name, and then associate an ingress rule with it. Another popular way to manage security groups is via AWS CloudFormation. This allows us to take full advantage of managing infrastructure as code, and even allows us to make updates to existing security groups via our CloudFormation stacks. Security groups are incredibly powerful, but their number should be clearly managed to avoid unnecessary operational overheads. Associate types of instances, such as a web server, with a given application with the same security group, and make reference to this security group in other tiers, for example, the application tier. Most architects start with ingress rules, but don't always define suitable egress rules. Leaving them as their default allows any. In the context of our application architecture, we need to consider whether an instance should be able to attempt to access arbitrary ports on other hosts, or should it be restricted. In most cases, we want to lock this down to 1 or 2 ports at most. Whenever possible, we should refer to other instances by their security groups instead of using CIDR blocks. This helps to keep our potential attack surface small and easy to manage. Sometimes this cannot be avoided, such as the case with allowing connections to or from on-premise resources or other VPCs, but this should be an exception rather than a rule. In particular, we should use a CIDR block of 0.0.0.0.0/0 very sparingly, typically restricting it to external ELBs or web services. Even then, we should lock the port and protocol down to what's appropriate. As shown in the AWS CLI example, we can manage security groups as code. The AWS Management Console makes changes easy for admins new to the platform, but as we mature in our usage, we should evolve to use programming languages, scripts, and deployment management tools such as CloudFormation to increase security through consistency. There are a small number of AWS limits that we need to be mindful of. One limit in particular is the maximum number of security groups per VPC. This is currently 100 and can have implications on our design. This limit can be increased, but only if no more than 100 groups make reference to a single security group. For example, imagine we place all Bastion hosts into a Bastion hosts security group, and then have a corresponding ingress rule on 100 other security groups. If we then want to increase our limit to say 150, this may not be granted by AWS Support. Understand the limitations and architect around them. Resource tags are supported on security groups and make ownership of resources much easier to track and report on. We should ensure that security groups are tagged according to whatever resource tagging pattern or policy makes sense for our environment. Finally, debugging security groups is usually quite straightforward due to their stateful nature. If we discover unexpected network restrictions or issues, then we should expand our investigation to include network access control lists and network routes. In this video, we will be looking at identity and access management on the AWS platform. We will start off by recapping on what identity and access management is, why it's valuable, and highlighting the scope of this video. We will then look at the AWS Identity and Access Management Service, IAM, and look how we can federate IAM with existing on-premise solutions that support SAML 2.0 assertions. We'll also take a close look at IAM roles and policies along with tools to help us develop and test them. We will conclude by reviewing some of the key design considerations. In a general sense, identity and access management concerns the authentication of users and the subsequent control over resources that they have access to, and the actions that they can perform on those resources. As we would expect, identity and access management is driven by one or more security controls required to maintain a security posture. In this video, we will focus on how to securely authenticate AWS users and restrict access of users, groups, and AWS resources to AWS services and their respective resources. Identity and access management on the AWS platform is provided by the AWS Service Identity and Access Management, IAM. The IAM service enables us to securely control access to AWS services and resources for our users. Using IAM, we can create and manage AWS users and groups and use permissions to allow and deny their access to AWS resources. We should restrict usage of the AWS root account to a small number of administrators for restricted, highly privileged actions such as setting up trust accounts or managing IAM admin groups. While multi-factor authentication or MFA is considered in detail in an accompanying video in this series, To recap, the IAM service provides support for MFA using either virtual multi-factor authentication devices or physical MFA devices. Furthermore, as of early 2014, the IAM service provided support for cross-AWS account MFA protected access. This is achieved by using an IAM role and specifying that the role requires MFA. This sets up a trust relationship and allows us to efficiently manage user access between AWS accounts. IAM provides support for federation with existing directory services that support SAML 2.0 assertions, such as Microsoft Active Directory Federated Services with Microsoft Active Directory. IAM provides support for policies, JSON formatted documents that specify the actions and resources a principal, such as a user or group, can perform. We can also use IAM to define roles that may be associated with EC2 instances to safely grant them access to AWS services and resources. Before roles existed, we needed to embed access credentials, an access key and a secret key, into each host, which complicated securing our environment. If an instance was compromised and the attacker gained access to the embedded credentials, then they could be copied off host and potentially used from anywhere on the internet. As we shall see, developing IAM policies can be a little tricky, so AWS has provided a number of tools to help make management and testing easier. IAM policies are first-class objects. That is, we can define a policy and centrally manage it. This allows us to efficiently share policies between resources and helps avoid forgetting to update one or multiple identical policies. As we would expect, IAM is accessible via the AWS Management Console and Service API. The IAM users we create can access the AWS console in a similar way to that of a root user. However, they will have to use a modified console URL as shown in the slide. That's a quick overview of the key features of the IAM service. Let's now take a closer look at IAM user management. For the purpose of this example, we'll consider that users are not federated with an external service. After logging into the AWS Management Console, we navigate to the IAM section and select Create User. In this example, we will create a user called AWS-Demo. The Amazon Resource Name, or ARN, uniquely identifies the newly created user or principal. The ARN consists of a service identifier, IAM, and an AWS account ID, blackened out on the screen, along with a unique username. The IAM user management interface allows us to attach a manage policy either defined by ourselves or a number of AWS provided templates, or an inline policy, a non-first class policy object that's just associated with the user. We can also associate the user with one or more groups. This is an efficient way to manage policies within an organization, and the same best practices and principles apply as we would adopt when managing a directory service such as Microsoft Active Directory. There's also the option to allow us to manage access credentials. Those are access and secret keys. Access and secret keys allow for authenticated and digitally signing access to AWS services, similar to what we have with the AWS root account. And finally, if our IAM user requires console access, then this can be granted along with MFA requirements and password management. IAM provides support for Security Assertion Markup Language, or SAML, an open standard used by many identity providers. This feature enables federated single sign-on, or SSO, which lets users log into the AWS Management Console or call the AWS APIs without having to create an IAM user for everyone in our organization. This simplifies the process of configuring federation with AWS, because we can use an existing identity provider service instead of writing custom identity proxy code. Therefore, provided our existing identity provider service supports SAML 2.0, we can manage users and groups in our existing identity service. For example, if our organization uses Microsoft Active Directory, then clients will communicate with an ADFS service. This will in turn request authentication from Active Directory and receive a SAML assertion if successful. We can create one or more IAM roles and policies, each of which maps to a group in the federated directory service. We will explain what roles and policies are in more detail in a moment. Users can then gain federated access via a web page provided by the ADFS service. This usually provides a selection of roles that we can assume. After selecting the desired role, we are redirected to the AWS Management Console and have the associated role policy associated with our session. We can also enable federated access on the console too. In this case, we can obtain a time-based session token after successfully authenticating against the domain for a given role. The AWS IAM team have created detailed instructions showing how to configure both Active Directory and ADFS, as well as Open LDAP and Shibboleth. We should therefore refer to the IAM Management Federation section of the AWS website to streamline the process of getting SSO up and running in our environment. An IAM role is essentially a set of permissions that grant access and actions to a given set of resources. These permissions are attached to the role, not to an IAM user or group. There are currently 3 categories of role: AWS service roles, cross-account access roles, and identity provider roles. AWS service roles are associated with AWS service resources, for example, an EC2 instance. They allow us to safely delegate access to one or more AWS resources from an EC2 instance. Before we had service roles, we had to embed access credentials such as access and secret keys inside of our instance in order to interact with the AWS service APIs. This caused a security challenge. Not only did it make updating credentials a necessary operational task, but if the instance was compromised, an attacker could then use the credentials from another location, assuming of course there was no source IP restrictions associated with the role and policy. We also have cross-account access roles. These allow us to delegate trust to users and groups in different AWS accounts. We look into these in more detail in the cross-account access video in the series. And finally, there are identity federation roles. This is where we can grant single sign-on access to resources for users authenticated via a number of OpenID providers or identity services that support SAML 2.0. A role gets its permissions or powers by having one or more policies associated with it. Let's take a closer look at role policies. An IAM policy allows us to grant a principal, either a user, group, or a role, access to one or more AWS resources. IAM policies are first-class objects, and they can be shared by multiple principals. This significantly simplifies management because it makes it operationally more efficient and secure. When a first-class policy is updated, all principals associated with a policy immediately benefit from the update. An IAM policy is a JSON formatted document that grants access to AWS resources. An IAM role policy looks very similar to that of an S3 bucket policy, as discussed in some detail in the S3 policy video in this series. Let's take a closer look at the structure of a simple policy to help our understanding. In this example, we're going to take a look at the first-class policy Amazon Glacier Full Access. As the name suggests, this allows the principal it is associated with full admin access to all Glacier resources owned by the account. Let's take a closer look at each of the attributes in a little more detail. The first attribute of the policy we will look at is its version. The version attribute specifies the version of the access policy language the policy is written in. At the time this video was created, the latest supported version is 2012-10-17. As the access policy language evolves, we should expect support for additional versions and supported features. Refer to the Identity and Access Management documentation for guidance on the latest supported versions. The statement section is the core of a policy. Each statement defines an access or a deny action for a given resource and collectively add together to form the overall policy. While statements are additive in nature, a deny statement will override an allow statement. Let's take a closer look at each section of the statement. Action attribute specifies which actions the statement will allow. Each AWS service has its own set of actions. Actions can either be a list of individual actions supported by the service, or in this case, we can use the wildcard character to represent all actions. It should be noted that as new actions are supported by a given service over time, the wildcard character will automatically grant access to them. This may not be our preferred behavior for some policies, so we should use wildcard characters sparingly. Next, we have the effect. This is either allow or deny, depending on what the desired result of the policy should be. In the case where we are granting access to a series of actions on resources, we set it to allow. Finally, we specify the resource that we want the allow action to act upon. As this is an admin policy, we are granting access to all resources, but we could easily limit this to specifying instances of Glacier if desired by replacing the wildcard character with the respective ARN of the Glacier vault. This rather simple example doesn't cover the full breadth of supported JSON attributes. Other key attributes include IDs for naming and conditional clauses to restrict application of the statement. Refer to the IAM documentation for a full description of the structure of an IAM policy. AWS provides a number of tools to help us manage and test IAM policies. These include the AWS Policy Generator, Policy Simulator, and JSON Document Editor. Let's take a closer look at each one of these. The AWS Policy Generator allows us to create a number of different policy types, not just IAM policies. It allows us to visually construct one or more statements by choosing from a list of service actions and AWS resources. We can even make statements conditional by specifying one or more conditional clauses. The resulting policy can then be downloaded, and we can then associate that with our AWS account. Being able to confirm that a policy does what we think it should be doing is very useful. Even a small typo in a policy could result in granting significantly greater privileges than we initially intended. The AWS Policy Simulator allows us to perform a dry run of what a user or group will be able to do when a given policy is associated with it. The Policy Generator is a highly useful tool to provide visual feedback on one or more of our policies. While the JSON schema is quite easy to read and not particularly complex, having real-time syntax highlighting is very useful. This is one of the more recent additions to IAM and has helped streamline development of IAM policies. One of the most important design decisions when using IAM is cross-account access and identity federation. We should therefore make our identity team part of the design process to maximize operational efficiency and security across both IAM and, say, Microsoft Active Directory as appropriate. Refer to the cross-account video in the series for design considerations specific to this area. We should carefully guard against access to our AWS root credentials and only allow a small number of trusted administrators to have access to them for specific operational tasks that cannot be performed by an IAM user. As with any other identity system, your users should not share accounts. Even in the case where you want a user to assume one or more roles, it's important that the user authenticates as a particular user and not a shared generic user. While policies can be associated with individual IAM users, it's not operationally efficient to do this. We should look for opportunities to manage users by group membership. The principle of least access holds with IAM as it does with any other access control process. For this reason, care should be taken when using wildcard characters to refer to resources or action elements within IAM policies. As users can have passwords and access credentials, we should rotate each in relation to our information security policy. If the policy doesn't explicitly relate to either, a quarterly rotation policy is the minimum recommended rotation period. Finally, we should monitor and generate alarms or events when changes are made to policies or trust relationships are altered. Using a combination of AWS services such as AWS CloudTrail and CloudWatch filters and potentially third-party products, we can gain greater visibility of changes to our environment and react in near real time to unexpected updates. In this video, we will be looking at Amazon S3 bucket policies from a security perspective. We will start off by looking at what Amazon S3 bucket policies are and why we may use them over AWS IAM policies. We will then take a look at the anatomy of a policy and work through a simple example. Next, we will look at some ways in which we can manage and test policies, and conclude by reviewing some of the key design considerations when restricting access to S3 resources. An Amazon S3 bucket policy allows us to control access to Amazon S3 resources. Unlike an IAM policy, which is associated with a user, group, or role, the S3 bucket policy is directly associated with an S3 bucket. Similar to other IAM policy types, an S3 bucket policy consists of JSON attribute value pairs. While bucket policies may look very similar to IAM policies, there are a few subtle differences. In particular, an IAM policy does not contain an attribute called principal, as in the case of a user, group, or role. The principal is implied by associating the policy, whereas in the case of S3, the principal is not the resource the policy is associated with. There are a few good reasons why we may want to choose to create an S3 bucket policy. The main reason is that we want to provide a third-party user or account with access to S3. For example, imagine we hosted web media on S3 and wanted to allow web browsers to download the content directly from S3. Or consider the case where we wanted to provide other AWS account holders with access to our S3 resources. While it's possible to set up a trust relationship between accounts, providing access to S3 resources to partners or customers is better achieved using S3 bucket policies instead of using cross-account trust and assume role. Another example of when it makes sense to use bucket policies is if we centralize our management of S3 buckets to get around the current limitation of 100 S3 buckets per AWS root account. Before it was possible to set up cross-account trust relationships, this was the only option for environments consuming large numbers of S3 bucket resources. However, today this is rarely required, and provided that we trust those accounts requiring access to S3 resources, as in they are part of our organization, then cross-account access is the preferred option. So now we know what an S3 bucket policy is and why we may use it. Let's take a closer look at what a policy actually looks like. As each S3 bucket policy is a JSON document, it consists of a series of attributes and values. Let's take a look at the structure with a simple example. We're going to define an S3 bucket policy that allows read requests from all users and accounts in the 47.41.37.24/29 network to the S3 bucket my AWS demo bucket. For brevity, we will omit the statement section from the S3 policy until a little later, so we can comfortably fit the policy snippets onto the screen. The first attribute of an S3 bucket policy we will look at is its version. The version attribute specifies the version of the access policy language the policy is written in. At the time this video was created, the default version was 2008-10-17, and the latest supported version is 2012-10-17. As the access policy language evolves, we should expect support for additional versions and supported features. Refer to the developer guide of the Amazon Simple Storage Service and the Identity and Access Management documentation for guidance on the latest supported versions. The next attribute is ID. This is an optional attribute as it allows us to associate a sensible, human-readable description with a policy. Now we consider the statement attribute. So let's remove the version and ID attributes from the slide and focus in on statement. The statement section is the core of an S3 policy. Each statement defines an allow or deny action on the S3 bucket that collectively add together to form an overall policy. While statements are additive, a deny statement will override an allow statement. Let's take a closer look at each section of the statement. Each statement consists of an optional statement identifier or SID. While not technically required, it makes it easier for us to understand what a statement is intended to do. This is increasingly important when multiple people are responsible for managing policies. We want to encourage reuse of policies and snippets of policies when at all possible. One way to increase the chance of this happening is to make them easier to understand. Next, we have the effect attribute. This specifies whether the statement should allow or deny a particular action. The default effect is deny, as we would expect. We then move on to the principal. Principal corresponds to the identity of the entity requesting access to the resource. This is an important design point, so let's take a closer look at principals. A policy principal refers to either a user, AWS account, or AWS service. For example, if we want to refer to the user Daniel from the AWS account with ID 1234567891012, then the principal would be that shown in the table. Using a similar format, if we want to refer to an AWS account, then instead of specifying a user, we will use the identifier root, as can be seen in the second example. And finally, if we want to refer to an AWS service or canonical user, then the format is a little different. Canonical users are commonly used to allow an Amazon CloudFront origin access to our S3 bucket. Now that we have a better understanding of what a principal is, let's get back to our example. As we want to provide all requesters with access to a bucket, we simply use the wildcard identifier. We now move on to the action or verb part of the policy. This defines what we are allowing the principal to do. A complete list of actions for the S3 service is available in the S3 developer guide. We should always refer to the guide to understand what actions are supported and what operations they correspond to. In our simple example, we are only granting access to get an object. Now that we have defined who is allowed to perform an action on a resource, we need to define the resource. Given that we will associate the policy with an S3 bucket, at first it may seem a little strange that we're specifying a resource. we could be mistaken for thinking that resources should be implied by the association of the policy with a bucket. However, we need to remember that policies don't just necessarily apply to buckets, they also apply to objects or pseudo directories in buckets. In our example, note that the resource uses the wildcard character to correspond to all objects in the bucket. The last part of the S3 bucket policy we will look at is one or more optional conditions. These allow us to restrict the statements based on a condition of some sort. IAM supports a wide collection of condition parameters that are too broad to cover in this brief video. However, for the purpose of illustration, we will use a condition source IP to restrict the statement to only requesters from a particular network range. Refer to the IAM documentation for a full list of supported conditions. While the structure of an S3 bucket is quite simple, they can be difficult to create and manage by simply reading the IAM documentation. I would therefore recommend using the AWS Policy Generator as well as a number of helpful examples contained within the IAM documentation when developing bucket policies. AWS provides a useful IAM policy simulator that we may already be using to test IAM users, groups, and role policies. This allows us to perform a dry run of whether a given action would be allowed by a user against a given resource. Unfortunately, today the IAM policy simulator does not currently support S3 bucket policies. As policies are little more than JSON documents, we can easily use version control to manage policies. If we programmatically associate policies with S3 resources, then it's easy to use the CLI tools, programming languages, and APIs to consistently and reliably control access permissions on S3 resources. Finally, AWS CloudFormation provides support for bucket policy resources, thereby making it easy to create and manage policies. Clearly, the most important design requirement is who or what needs to access our S3 resources, what actions they should be able to perform, and what restrictions, if any, should be placed upon them. Of these requirements, the who or what will either push us towards an S3 bucket policy or using IAM user, group, and role-based policies. When possible, we should use IAM policies and include bucket policies if we need to provide access to a principal outside of an AWS account that we trust. While we can create complex S3 bucket policies consisting of a number of statements, principals, and conditions, the current maximum size of an S3 bucket policy is 20 kilobytes, so we should design our policies to be efficient to avoid limit issues. This will also make them easier to manage. We need to ensure that our policies actually do what they are supposed to do. Creating policies, even with the assistance of tools such as the policy generator, can be difficult to get right. Furthermore, a subtle change to a policy can completely change access permissions. It's good practice to develop reusable policies or policy snippets and carefully control the review process and change management to policies. Furthermore, it may make sense to monitor API calls specifically relating to bucket policy management and investigate all changes performed outside of change control. Making good use of version control will simplify change management and make it easier to roll back. As part of testing, we may want to look at unit testing practices, similar to what we do when developing software. For example, if a policy should only allow a particular user read access to restricted objects in an S3 bucket, we can simulate this and validate behavior via a series of unit tests. In this video, we will be looking at multi-factor authentication for the AWS platform. We will start off with an introduction to multi-factor authentication and look at why it's a must-have component for our identity and access management architecture. We will then consider the different supported MFA form factors, and then look at how MFA relates to the identity and access management service. We will then conclude by looking at the key design considerations when integrating MFA into our AWS architecture. Multi-factor authentication provides a means of authenticating a user using two or more forms of identity check. The first check is typically a username and password, often referred to as something we know. The second component is a one-time access token, provided by a time-synchronized MFA device. This typically corresponds to something we have. Even if someone were to guess our password, they would also need our MFA device in order to access our resources. In addition to restricting access to AWS accounts, MFA can also be used to restrict access to sensitive API calls, such as terminating an EC2 instance or deleting a sensitive S3 object. Multi-factor authentication makes it much harder for someone to gain unlawful access to our AWS account and resources. AWS supports both physical and virtual MFA devices. Virtual MFA devices are available for most mobile platforms including Android, iPhone, BlackBerry, and Windows. The application just needs to support the time-based one-time password open standard. Virtual MFAs are generally considered suitable for non-AWS root accounts. The other form of MFA is a physical MFA device. These are often small key fob-sized or credit card-sized devices that display a one-time password on a small LCD display. At present, the only MFA device supported by the AWS platform are provided by Gemalto. Refer to the IAM section of the AWS website for further details along with how to purchase one of these devices. AWS state that physical devices provide greater levels of security than virtual devices, and for that reason, they are recommended for protecting AWS root accounts. AWS root accounts should be restricted to a small number of users and groups who will infrequently use the credentials. Regular access of AWS should be via the AWS Identity and Access Management IAM service users or federated access via an existing identity system. AWS MFA is designed to support IAM. When we think about MFA access, we often first think of two-factor authentication to be via a web portal. For example, to access an email account via a secure external website. Therefore, as we'd expect, MFA allows us to access the AWS Management Console to visually manage our resources. However, we can also use it to provide time-based programmatic access to resources. This is particularly useful for administrators who need to run scripts with a given set of access permissions. Furthermore, it's possible to integrate MFA together with Identity Federation, thereby allowing us to benefit not only from an existing directory service, such as Active Directory or LDAP. As of early 2014, the IAM service provided support for cross-account MFA-protected access. This is achieved by using an IAM role and specifying that the role requires MFA. This sets up a trust relationship and allows us to efficiently manage user access between AWS accounts, such as production, development, and staging. Given the potential impact to our business if our AWS account credentials are compromised, using MFA should be a default position for both root accounts and IAM users. When physical MFA devices are used, access should be restricted and logged. Placing them in a physical safe, but checking them on a regular basis to ensure that they are still operational is a good approach. Virtual MFAs will provide a significant step up in security with minimal implementation effort and little or no cost. While we can have multiple devices for a given AWS account, we can only use an MFA device with a single AWS root account. This is an important factor when considering the argument for virtual versus physical devices. Don't place MFA into production without a clear and tested procedure for revoking their access or replacing them with another device. Revoking MFAs associated with IAM users can be done without help from AWS Support. But if we need help with a root account, we'll need to contact AWS, currently via a purpose-designed MFA reset form located in the Forms section of their website. This is why we should regularly check physical devices to ensure delays in getting a new device associated with a root account are minimized. Have at least one spare physical device that's unused at all times to avoid delays. Identity Federation provides a number of operational benefits, but we need to ask ourselves, is it sufficient to just use single-factor authentication to protect our business's most valuable assets, namely our data? Enterprise organizations typically take the approach of MFA with Identity Federation to provide high levels of access control. We should consider protecting highly sensitive and destructive API service calls with MFA. For example, consider enabling MFA delete enabled on S3 buckets containing sensitive data. For example, on an S3 data bucket that contains AWS CloudTrail logs. Most organizations will need to manage multiple AWS root accounts to help enforce separation between different environments such as production, staging, and development. Cross-account access via trust relationships and IAM policies should require MFA to provide the greatest levels of authentication. In this video, we will be looking at cross-account access on the AWS platform. We will start off by looking at what cross-account access is, different ways to achieve it, and why it's valuable to be able to do so. We will then look at role-based delegation and see how we can set up trust relationships between AWS accounts. Building on this, we will then consider a simple example to illustrate how we can delegate trust between accounts and show how a trusted account can use an IAM policy to allow users and groups to assume a role in a trusting AWS account. Finally, we will conclude by reviewing some of the key design considerations. Cross-account access is the action of providing a user belonging to one AWS root account with the ability to assume the role of a user or gain access to resources in another AWS root account. For example, we may wish to grant administrative access to EC2 resources to an AWS account that doesn't own those resources. One of the most common uses of cross-account access is to provide access to resources across environments such as development, staging, and production. A common design approach for managing multiple environments is to create a dedicated AWS root account for each. While it's important for resources to be associated with distinct accounts for security reasons, if there's no mechanism for user A in account X to assume the role of user A in account Y, then it can result in quite a bit of operational overhead. Ideally, what we'd like to be able to do is provide a simple means of not only authenticating users against a single authentication platform, but that platform allowing users to assume a role or user associated with another account. As identity and access management is the main service we use to restrict access to services and resources within an AWS account, it should come as little surprise that it's also a key component when providing access across accounts. As a reminder, let's recap on what an IAM role is. There are a number of different types of IAM role, ranging from AWS service roles such as EC2, that is a role associated with an EC2 instance to allow it to access other AWS resources without having to embed AWS security credentials, an action that's clearly a bad idea from the perspective of security. We also have an identity provider role, which allows web single sign-on for SAML providers. And finally, we have a cross-account role. These typically allow access between accounts that you own or between third-party accounts. Providing access to users between accounts that you own works in the same way as providing access to third-party accounts. However, currently, it's not possible to switch between user accounts or assume the IAM role of a third-party account via the AWS Management Console. IAM role-based delegation is based on the concept of providing a trusted account with access to a trusting account. Let's take a closer look at this with a simple example. Let's imagine that we want to set up a trust relationship between a test environment account and a staging environment account. The trust relationship should provide full administrator access to all S3 buckets owned by staging, and we will control individual access to buckets and objects via group roles in the test account. In this case, the staging account is trusting the testing account, or put another way, the test account is seen to be trusted. Using the AWS Management Console, we can create a new IAM role, Test Environment Trust role, in the staging account. As this role will be used for cross-account access, we select cross-account access and select the radio button corresponding to accounts that we own. Next, we specify the AWS account ID of the test AWS account. This is a 12-digit number. For added security, we check the MFA checkbox requiring that users in the test AWS account must have authenticated via an MFA device. We then select the AWS Managed IAM policy providing full administrator access to the S3 buckets and resources and associate this with the role. This is the maximum privileges the test account will be able to delegate to users and groups. While we can and may choose to restrict this policy to a subset of S3 actions and resources, provided we trust the test account, we can trust the account admins to assign policies and users to groups as appropriate. Finally, we review and create the role. So far, all we've done is set up a trust relationship between two AWS root accounts. While this is useful, we generally don't want all users in the test AWS account to be able to control all S3 resources in the staging account. Access is therefore restricted by group membership and IAM policy. We do this by attaching a policy to one or more groups in the test account, granting them access to assume the role of the test environment trust role, highlighted in blue. Now that a trust relationship has been established and a suitable IAM policy associated with one or more groups in the trusted account, users belonging to those groups can assume the test environment trust role either via the AWS Management Console via the URL displayed when we set up the trust account or via command line tools or API SDK. The first thing we need to consider when considering our cross-account access is which accounts are in scope, and of these accounts, which accounts should trust which other accounts. This should be documented, and the number of admins who can create account roles should be restricted, carefully managed via IAM and monitored via CloudTrail and CloudWatch filters of third-party tools. AWS IAM allows us to provide very granular control over access to services and resources. When considering cross-account access control, it must be a balance between security and manageability when associating a policy with a role. Depending on the level of trust, we may choose to vary the restrictiveness of the IAM policy associated with the role, or place greater responsibility on the trusted account to restrict access to resources. Making the policy associated with the role too restrictive can result in operational inefficiencies and potentially policy debugging issues. We need to be particularly careful when providing access to third-party accounts that are not part of our organization. If there is a legitimate reason for providing a cross-account access to resources, investigate whether it's possible via AWS Service Resource-Based Access first of all. Some services such as S3 allow us to control access using bucket policies. Also, while strictly not a requirement of cross-account access, integration of identity federation for authentication to assume various roles is an incredibly useful and powerful operational and security approach. Cross-account access becomes a management headache unless we consider identity federation. A secure, manageable solution usually consists of a combination of cross-account trust relationships, identity federation, and multi-factor authentication. In this video, we will be looking at encryption. We will start by looking at the scope of encryption and why it's increasingly important when consuming services from a public cloud provider. We will then take a look at how encryption of data in transit is ensured when accessing resources by the AWS management interface. After that, we will take a look at some of the key data at rest and in transit features built into commonly used AWS services. We will then take a closer look at the AWS Key Management Service, KMS, and then compare and contrast considerations for client-side versus server-side encryption. We will conclude by looking at some of the key design considerations we need to bear in mind as we architect for the AWS platform. The focus of this video is the encryption of data at rest or in transit on the AWS platform. There will be a minimal discussion of crypto systems and their relative strengths. We will just focus on the application of industry standard encryption ciphers either provided as AWS service features or by third-party tools and software. For the purpose of this video, let us define data at rest to be data that is physically stored in a digital format that is not traversing a network, and data in transit to be data traversing a network. We will make no distinction between data at rest and data in memory on a host or service, although clearly it is noted this is a simplification. The primary reason for encrypting data at rest or in transit is to ensure that data can only be read by designated parties with a valid key to decrypt the data. Encryption of data is typically driven by a number of organizational and regulatory factors regarding the sensitivity of the data and the difficulty or cost of encrypting the data. Let's start by considering the AWS management interface. When AWS releases a new web service, there are typically three ways to interact with the service. The first is via the AWS Management Console, the second is via the Web Service API, either directly or using one of a number of programming languages or SDKs, and thirdly is via the command line tools such as the Python package, AWS CLI, or the AWS tools for PowerShell. While there is a growing ecosystem of third-party products and tools that allow us to manage our resources, they will be using one or more of the published programming libraries. Starting with the AWS Management Console, access is via HTTP inside of a secure socket layer SSL or transport layer security TLS, thereby providing a secure HTTPS connection. This protects all data in transit between your browser and the web service providing the AWS Management Console. Next, we have the API or libraries and SDKs. If there is an available SDK or library, it handles encryption and digitally signed content for us. If, however, we need to interact with a web service API or its RESTful interface, then we will have the option to either use HTTP or HTTPS. There's no additional AWS service cost for making a request over HTTPS, so always ensure requests are encapsulated by a secure TLS or SSL connection to ensure encryption of data and requests in transit. We will also need to ensure that requests are digitally signed to avoid requests being tampered with or replayed at a later date and time. Similar to the SDKs and libraries, the AWS command line tools automatically encrypt and digitally sign requests by default to ensure encryption of data in transit. Support for encryption of data at rest and in transit is extensive and continually evolving as AWS services evolve. We will cover a small select number of useful and commonly used encryption features, but we should always refer to the AWS service documentation for the latest supported features. The first service we will look at is the Amazon Simple Storage Service, S3. S3 provides options for both server-side and client-side encryption. If we select server-side encryption, then objects stored in S3 are encrypted on disk in Amazon data centers. Unless someone has both the server-side key and your encrypted object, the object will remain encrypted with advanced encryption standard EAS 256-bit encryption. There is no additional cost implications for using S3 provided server-side encryption, so it's a sensible minimum option. S3 also allows us to use the AWS Key Management Service, KMS, to manage our keys. More on that service shortly. The third variation for key management with S3 is client-managed keys. We can simply provide the keys when accessing an object, and S3 performs the encryption, decryption operation without any client-side code or additional client-side performance overhead. Similar to S3, Amazon Glacier allows us to encrypt our data server-side or client-side. Amazon Elastic Block Storage features server-side encryption. This was introduced after it was introduced into the S3 service. It provides support for 256-bit AES encryption, thereby encrypting data at rest and in transit between the storage tier and the EC2 instance that mounts each volume with the required key. It's important to note that not all EC2 instance types support encrypted volumes. Refer to the EC2 service documentation for the list of supported instance types. The Amazon Elastic Load Balancing service contains a number of features for encrypting data in transit. In brief, it allows us to terminate HTTPS sessions on the load balancer, thereby offloading the task from backend web or application servers, and optionally allows us to re-encrypt the backend connection if required. It provides support for a number of SSL security policies, including support for different versions of SSL, TLS, and an extensive collection of encryption ciphers. Refer to the ELB documentation for the latest supported features. And finally, the Amazon Relational Database Service, RDS, provides options for security of data in transit via a root SSL certificate, and a selection of database engines provides support for encryption of data at rest. Now let's take a look at two security-focused services. First of all, we have the AWS Key Management Service, KMS. KMS provides us with a way to centralize and fully manage our encryption keys, and as we have already seen, a number of AWS services are able to consume its service with little or no effort. Furthermore, it's integrated with AWS CloudTrail for auditing purposes, and it's fully managed, thereby allowing us to easily perform lifecycle management of keys, which is part of operational best practices. One other point of note is that keys that are managed by the KMS service will never go outside of the AWS region they are created in. This is valuable information when it comes to considering the potential implications of the Patriot Act. Finally, we have AWS Cloud HSM, a cloud-based hardware security module that supports a variety of use cases and applications. These include database encryption, digital rights management, public key infrastructure, authentication and authorization, document signing, and transaction processing. AWS Cloud HSM provides the greatest level of control over encryption keys. AWS administrators are only responsible for managing the HSM devices. We as consumers of the service have full control over the keys and crypto options. Encryption of data at rest and in transit should be driven by our information security policy. For large organizations, this document will exist and be regularly revised. For smaller organizations, the policy may be less formally managed or not defined at all. In the absence of a security policy, it's highly recommended that one be created that's at the right level for the maturity of your organization and the regulatory bodies that you are controlled or influenced by. At the very least, all data should be classified according to the number of different levels and guidance provided on the required encryption of data at rest and in transit for each one of those levels. The compliance targets we are architecting for will play a significant role in what needs to be encrypted. For example, PCI DSS Level 1 specifies strict requirements for encryption as described by its control objectives. As we have seen, AWS provide a number of security encryption features that come at little or no cost. There is little or no reason for us not to be making use of them, irrespective of what our enterprise security policy may require as a minimum. It's important that we monitor the configuration of resources for encryption best practices. AWS Trusted Advisor service continues to evolve and provide helpful guidance to improve our security posture. But in areas where there currently isn't any support or there are gaps, we need to ensure that operations actively monitors for resources that do not meet with encryption standards and close the loop. This could be achieved using a combination of AWS CloudTrail and querying one or more number of AWS APIs. Lifecycle management of keys is important to ensure we maintain a strong security posture. If a key is obtained by a third party and they have access to the encrypted data, then clearly they have access to the decrypted data. In the event that we manage our own keys, we must manage this service or function with great care and design for high availability. If keys are lost or the service is unavailable, we cannot access the data. Finally, be mindful of encryption service restrictions when architecting across regions. For example, as AWS KMS keys cannot leave a region, this means that we cannot use the asynchronous replication of some data services such as the relational database service for cross-region replication of encrypted data. While this may change in the future, we need to fully appreciate the implications of encryption decisions on other design requirements such as availability. In this video, we will be looking at perimeter security on the AWS platform. We will start off by looking at what perimeter security is and why it's important. We will then look at the components of perimeter security that we would commonly associate with an on-premise or non-cloud platform. This will lead us to review features of the Amazon VPC that allows us to control network access via stateful and stateless access controls. We will then go on to look at network and application level firewall design patterns, as well as recommendations for implementing intrusion prevention systems. Finally, we will conclude by reviewing some of the key design considerations when incorporating perimeter security into our architectures. Perimeter security is a broad term used to describe the physical or logical protection of resources at an external perimeter. The external perimeter actually is dependent on our point of view and what we are responsible for. As we are consuming virtual resources on the AWS platform, and AWS are responsible for the security of the cloud, then the boundary of the perimeter will not include physical security of the network devices, providing the boundary connection points, as we clearly do not have access to these. For the purpose of this video, we will define the perimeter to be the outmost tiers of our network architecture that are accessible from or provide access to non-AWS resources via the internet or private network connection. I say outmost tiers, as in some cases, we may need to extend the perimeter a little deeper than simply one level to provide a fault-tolerant and elastic edge. As an Amazon VPC is the default container for our AWS compute resources, we will consider what perimeter features it provides and use this as the outer edge of our perimeter boundary. This will include virtual gateways, internet gateways, but will not include VPC to VPC peering, as the traffic remains within the bounds of our perimeter. If we think about on-premise perimeter security, it typically consists of components from a number of areas. Solutions may be integrated as add-on modules for networking devices or by different providers. Either way, it will typically include or cover firewalls, web application firewalls for level 7 inspection, intrusion prevention, secure gateways, traffic management, and application acceleration. These modules are components that often reside in an online network device or are connected to a network port that has been mirrored to replay network traffic. Some of these features may have been regulatory requirements for our application. In other cases, they are optional, but provide increased performance, greater visibility of threats, and help us manage threats and reduce risk. Let's take a look at how the Amazon VPC allows us to incorporate a number of these components into our designs. Amazon VPC provides a number of perimeter security features that we can incorporate into our designs. An Internet Gateway is a horizontally scaled, redundant, and highly available VPC component that allows communication between instances in a VPC and the Internet. It's a fully managed virtual resource that provides a route from the Internet to our outer network perimeter. We have the ability to divide our network up into one or more subnets that are either directly publicly routable via an Internet Gateway or private and need to be routed via a NAT instance or proxy resource in order to access the Internet. For publicly routable subnets, we should develop network access controls that are the union of all the required access requirements of resources residing in the subnets that are associated with. As network access controls are stateless, the egress rules will be somewhat broader than the ingress rules, often with large port ranges due to the nature of connections initiated from unprivileged services on external hosts. Resources residing in a private subnet cannot access the Internet directly via an Internet Gateway. They will either need to be routed via a NAT instance, a proxy host, or via on-premise infrastructure in the case of a hybrid architecture. Proxy instances are generally considered the preferred means to provide access to Internet resources, as we can develop a more scalable, resilient architecture than we can with a NAT instance. For the next level of perimeter security, we use VPC security groups. These provide us with stateful access control and fill in the gaps left resulting from the broader, stateless control provided by the subnet NACLs. Collectively, subnet NACLs and VPC security groups provide a solid foundation for perimeter security. Collectively, these features allow us to design and configure a flexible network firewall for our AWS resources. However, they do not provide visibility of traffic that has been blocked as a result of the NACLs and security groups, and they cannot inspect application-level traffic and make context-based traffic decisions, such as preventing an SQL injection attack, or alert operations in the event of traffic that's characteristic of attackers. If we need visibility at that level, then we may need to augment the perimeter security features provided by AWS with those of third-party providers. Let's now take a look at some common design patterns for using third-party firewall and intrusion prevention systems on the AWS platform. Intrusion detection and prevention systems often consist of a combination of network and host-based devices and agents. The network component requires a network tap or port mirroring on one or more switches and combining that with host data captured with a host agent. We do not have access to mirror a switch port on the AWS platform. We must either direct all traffic via one or more network throttle points, or listen and replay all network traffic to and from an EC2 instance. Creating a network throttle point anywhere other than at the very most outer edges of our architecture is unworkable and will result in our architecture becoming brittle, difficult to scale, and operationally difficult to manage. We could place one or more network interfaces into promiscuous mode and relay the traffic to a centralized monitoring server. However, replaying network traffic in this way effectively reduces our network bandwidth by a factor of 2, as we only have a finite network bandwidth available on an EC2 instance. If we need to extend IDS and IPS detection into our architecture, as in into the cloud, away from the edge, host-based agents are generally considered best practice. It should, however, be noted that the host-based agents will only see the network traffic allowed by the combined effect of the subnet NACLs and security groups. Relaxing either of these for the purpose of greater visibility from an IDS/IPS perspective is not recommended. If the stateful and stateless firewalls provided by NACLs and security groups are not sufficient, there are a few designs which we may consider. Firstly, there's host-based firewalls. In many cases, host-based firewalls are used in addition to NACLs and security groups. But if our security groups are correctly configured, they provide little additional value above and beyond logging of network traffic. They can also cause operational overheads and sometimes result in extended debugging of suspected network configuration issues. Once again, a host-level firewall will only see the network traffic that NACLs and security groups allow to pass through. If we need greater visibility of traffic at the edge and integrated management with on-premise firewall rules and policies, then an inline solution is the most common approach. However, we will make the distinction between network firewalls and application-level firewalls. Network firewall solutions on the AWS platform typically run in an active standby configuration and will be restricted in throughput to the EC2 instance types we choose to run them on. Application level firewalls, however, are more flexible, and we can run them in an active cluster sandwiched between two tiers of load balancers. The AWS platform provides a number of features that help us provide a solid foundation for perimeter security. Collectively, subnet ACLs and security groups provide for stateful and stateless network access controls that integrate with a number of AWS services such as autoscaling. Before we deploy additional perimeter security, we should evaluate whether it's actually required and the benefits that it provides. This is an area where replicating on-premise into the cloud just because it's the way that we've always done it can result in unnecessary costs and operational burden. If we do require such a solution, what should be the scope? Does it need to accommodate all of our AWS resources, or should it be restricted to a subset? That being said, if we need greater visibility into network traffic, provide application-level firewall protection, or a unified enterprise firewall management system, then there may be good reason to augment the perimeter security features of the AWS platform with those of third parties. As discussed earlier in this video, the distributed nature of a cloud platform means it's not currently possible to gain access to a mirror port on a switch. Until higher-level services are able to provide access to this data, we may need to employ host-based solutions for inspecting or relaying traffic. While some approaches are technically possible, there is sometimes a trade-off either between security, manageability, scalability, and availability. While security should be top priority for organizations, as architects, we need to fully be aware of how our design decisions impact the operational availability of one or more services. In this video, we will be looking at monitoring and alerting of AWS resources from the perspective of security. We will start off with an introduction to monitoring and alerting on the AWS platform and highlight the scope of this video. We will then look at the AWS CloudWatch web service and see how we can use it to monitor and provide suitable alert notifications. Next, we will look at security monitoring and alerting features of the AWS Trusted Advisor service. Next, as part of the CloudWatch service, we will consider AWS CloudWatch alarms and see how we can use them together with the AWS CloudTrail service to provide near real-time alerting of security-related events. We will then conclude by summarizing some of the key design considerations we should bear in mind when architecting, monitoring, and alerting architectures on the AWS platform. The main focus of this video is monitoring and alerting of resources directly created by AWS Web Services or interacting with AWS Web Services using access credentials. For that reason, we will only briefly mention application or operating system level monitoring, which can be performed in a similar fashion to how we would do so on-premise today. As the American management consultant Peter Drucker once said, "What gets measured gets managed," and one important element of management is the security of resources. Without adequate monitoring and alerting tools and services, our security and operation team's ability to anticipate and respond to events is seriously restricted. Amazon CloudWatch is a monitoring service for AWS service resources and the applications you run on AWS. With CloudWatch, we're able to collect and to track resource metrics, store and monitor log files, as well as configure alarms. With CloudWatch, we can monitor not only point-in-time metrics of interest, but also statistical measures such as how a metric varies over a time period or across a group of resources. This is particularly valuable when using metric-based scaling for the AWS autoscaling service. For example, we could use CloudWatch to report on the average CPU utilization across an autoscaling group of web servers and use this together with a measure of duration to configure an alarm. CloudWatch provides monitoring support for a large number of AWS services as described in the AWS CloudWatch service documentation. For Amazon EC2, CloudWatch provides two levels of monitoring resolution: the default level, which is up to a 5-minute resolution, and a detailed 1-minute resolution. The default level of monitoring comes at no additional cost above and beyond the cost of the EC2 service. But if we need to increase the resolution up to 1 minute, that incurs an additional monthly charge. As AWS has a track record of reducing costs over time, we should refer to the latest pricing data before making any architectural design decisions based on cost. CloudWatch metrics are available for a period of 2 weeks. If we need to store metrics for a longer period of time, then the data will need to be extracted from the CloudWatch service and stored into a durable, low-cost storage service such as S3 or Glacier. We can archive this either using the getMetrics statistic API call or by one of a growing list of third-party tools. AWS CloudWatch is supported by the AWS Identity and Access Management Service, allowing us to control which users or groups have access to CloudWatch actions or resources. AWS CloudWatch has the ability to monitor and to record inbuilt metrics such as EC2 compute utilization, network I/O, database storage I/O, as well as custom metrics that we define. Custom metrics are used to monitor things such as actual memory used on a host or the number of threads an application may have. Basically, metrics which we don't have visibility to from the hypervisor. The first experience that people typically have when using AWS CloudWatch is via the AWS Management Console. In addition to accessing raw historical CloudWatch metrics or statistics from the last 2 weeks, we can also visualize data via a simple interactive graph. As data can be as little as 1 minute old, this is a great way to investigate issues in near real time and visually explore historical behavior. For example, the screenshot presents a CloudWatch graph for CPU utilization on a T2 micro instance during load testing. While we are only using CloudWatch monitoring with a 5-minute resolution in this example, we can clearly see variation in load against time. While a default level of resource monitoring is provided automatically, unless we actively generate alerts in a timely manner, then we cannot react to security-related events as they happen. Alerting is provided by the AWS CloudWatch Alarm. An AWS CloudWatch Alarm consists of a name, description, and alarm metrics such as CPU, a test condition of some sort such as greater than or equals to, and a period of time that the condition must be true before generating an alarm. The final element of an alarm is where to direct the alarm. This is configured using the Simple Notification Service, SNS, and is typically routed towards one or more recipient emails, a simple queue service queue, or a web service that's integrated with our operational management tools. CloudWatch is integrated with AWS Autoscaling. Collectively, they allow us to create a dynamic, responsive environment. As the scope of this video is security, we will not look into autoscaling in any great detail. However, it should be noted that as part of a denial of service strategy, our application architectures should be elastic, and therefore not only will autoscaling facilitate this, but high watermark alarms can alert us to suspicious high load behavior. Extending our earlier example, let's imagine that we want to generate an alarm when the average CPU of our instance exceeds 80% for 3 consecutive 5-minute periods. We can create such an alarm as shown in the screenshot. A valuable monitoring and alerting tool to assist in securing an AWS environment is the Trusted Advisor service. AWS Trusted Advisor inspects our AWS environment and provides helpful recommendations to improve our use of AWS in one of 4 different areas. Security is one of those areas and includes topics such as whether multi-factor authentication is activated on root accounts, whether we're using identity and access management, our security group configuration, and whether S3 bucket permissions are configured correctly, to name but a few. The service doesn't provide real-time alerting, but rather a weekly summary of notifications. These can then be acknowledged and subsequently removed from future notifications. In many cases, however, the alerts should be heeded and suitable remediation steps carried out. As Trusted Advisor isn't particularly context-aware in its recommendations, expect a number of false positives, but this is a small operational overhead and cost where security is concerned. It is also worth noting that the granularity of tests is determined by our current support level, with BASIC providing a small but still helpful subset of those tests provided to customers with business or enterprise support. AWS CloudWatch plays a significant role in helping us maintain a strong security posture when we combine it with AWS CloudTrail. AWS CloudTrail is a web service that records all API calls to an AWS account and stores those logs in S3 for analysis. Even for moderately sized AWS environments, CloudTrail can result in a large amount of log data that could contain valuable security data. We could analyze this data in batch using big data techniques, but for some events, they should be detected in near real time. That's where AWS CloudWatch comes in. We can configure one or more CloudWatch alarms using suitable CloudWatch filters. For example, let's imagine that we want to generate an alarm when an AWS policy is modified. We can do this with CloudWatch filters, as shown in the slide. In addition to using CloudWatch alarms, there is a growing ecosystem of third-party products and tools to help detect and alert based on security-related events or sequences of events. Refer to the AWS Partner Network section of the AWS website for further details. Monitoring and alerting should be driven by the classification and importance of the resource we are protecting. Our information security policy, along with the security runbooks, will be helpful to guide us here. For example, alerting based on deletion of objects in an S3 bucket containing public data in a testing environment should have a different level of alerting to that of production CloudTrail logs. Important notifications should not get lost in the noise of unimportant events. Another way to look at this is asking the questions: who needs to be alerted, of what do they need to be alerted, why, and in what time frame? Is there a good reason for detailed monitoring to be enabled on EC2 instances? Assess whether it makes sense to pay for detailed metrics. Detailed monitoring is often required primarily for operational scaling reasons, more so than from security. We need to look for gaps in our visibility. Consuming web services usually provides far more data than we previously would have had access to. However, as we have seen, CloudWatch does not have visibility to all metrics by default. If we need to inspect something that's not visible from the hypervisor, then we need to use custom metrics or use third-party application level monitoring tools. Monitoring and alerting is typically driven by security and operational requirements. The focus of each will be different. We should architect for the union of the two sets of requirements, but clearly allocate ownership of each to the respective internal teams. CloudWatch alerts and alarms are configurable CloudFormation resources. We should use CloudFormation templates to help enforce best practices and avoid potential operational errors. CloudFormation snippets should be reused when possible to ensure that multiple teams and applications benefit from the continual evolution of our security monitoring and alerting practices. A similar approach should be adopted if other lifecycle management tools are used. Monitoring and alerting should not be left to chance. It should be fully integrated into our operations. As previously mentioned, Trusted Advisor provides different levels of notification granularity depending on our service level. This should be an important factor when considering the level of support we subscribe to. Support level should not just be an SLA discussion. As CloudWatch only maintains historical metric data for a period of 2 weeks, this may be insufficient for our needs. For example, if we want to keep a record of all our IAM-related events as generated by CloudWatch filters, then we will need to extract summary statistics on a regular basis and store these in S3 or Glacier. In this video, we will be looking at infrastructure as code from the perspective of security. We will start off by explaining what we mean by infrastructure as code. We will then consider the benefits of taking a code-based approach to infrastructure management and look at two common approaches. Next, we will look at some of the tools and services provided by AWS to help us efficiently manage our resources as code, and conclude with a closer look at one of these tools, Amazon CloudFormation, with a specific focus on its security features. Let's start by considering what we mean by infrastructure as code. Infrastructure as code is a paradigm that allows us to model infrastructure resources such as networking or storage as if they were code. In doing so, we are able to abstract away from what may be a complex resource and think about them in terms of services that have well-defined interfaces. We can then manipulate these resources as we would with any other abstract programming resource. The origins of infrastructure as code emerged as a result of developments in utility computing and Web 2.0. However, the need to manage infrastructure as code was primarily driven by a desire to improve infrastructure operational efficiency. Treating infrastructure as code allows us to automate manual operational procedures that we may find in an operations runbook. Automation in turn allows us to increase operational efficiency, consistency of infrastructure management, and increase control, not to mention providing business agility. Unit and integration testing is a mature discipline that's used to great extent during application development. By treating infrastructure as code, we are able to use existing tools and methodologies to help improve the quality of our infrastructure deployments. An increase in consistency and control over deployments can have a significant impact on the security of our environment. There are two broad approaches to treating infrastructure as code. They are imperative and declarative. If we take an imperative approach, our code consists of a series of statements that change a virtual environment's state. On the positive side, we are able to use our programming language of choice, and in doing so, we can integrate our code into existing testing and development and delivery pipelines. However, as we need to manage state, the imperative approach is best suited for deployments from scratch, where we know the initial state. If we don't know the initial state, we need to somehow have a means to obtain it in our code. This can add significant additional complexity. Unless we take a compare and create approach in our code, it will not be idempotent. We could easily find that we have multiple copies of the same resources if we run our code multiple times. Therefore, the imperative approach can make updates difficult. If we take a declarative approach, our code defines the end state of a virtual environment, without explicitly defining the steps or commands that must be performed to achieve that state. On the positive side, by only being concerned about the end state, we avoid the heavy lifting of figuring out how to achieve it. Also, a declarative approach is by its very nature idempotent. However, there are some downsides. Firstly, declarative languages tend to be domain-specific, though that's not always the case. Ideally, a declarative language should be agnostic towards the underlying platform, thereby allowing resources to be reused between different providers. However, unless there are strong standards for resources and supported operations on those resources, then a declarative approach will have strong vendor-specific focus. By adopting a declarative language that's specific to a platform or service, it may increase the inertia to move away from a service or platform in the future. There are a number of ways to interact with AWS infrastructure resources as if they were code. One of the more common ways is to install the AWS command line tools, or CLI as it's more commonly known. Next, we have the AWS tools for Windows PowerShell. As you might expect, this is more popular with Microsoft system administrators. We can also interact with each of the services via their APIs or via one of a number of growing SDKs including Java, .NET, Python, Ruby, and JavaScript. And for those wishing to take a declarative approach to infrastructure, Amazon's CloudFormation service allows us to use a template-based approach to infrastructure. Let's take a closer look at some of these approaches. The AWS command line tools fall into the declarative category of management tools. They are available at the URL in the slide. The CLI tools are easy to install and readily available for Linux, OS X, and Microsoft Windows. For Linux and OS X, we can install them with a Python installer called pip. For Windows, we simply use the MSI installer, also available from the URL in the slide. Creating a new VPC using the CLI tools involves only a small amount of code. We just need to specify the action of create VPC and the CIDR block of the VPC. That's it. Also belonging to the declarative category are SDKs. Here we look at the Boto SDK for Python. If we wanted to create a VPC with the same properties as we did using the CLI tools, we could use something similar to the code extract presented in the slide. While this is not a simple one-liner, the main reason for the additional code is the import of a module and error checking. The real work is done with a single line of code outlined by the red box. The last approach we will look at to managing infrastructure as code is Amazon CloudFormation. CloudFormation is a declarative template-based service. We simply define what we want the end state to look like, and the CloudFormation service is responsible for achieving it. We specify what our infrastructure should look like by defining resources and their properties in the JSON format, and then make requests to Amazon CloudFormation to create or update a CloudFormation stack. Because CloudFormation uses a declarative template for input, we can be confident that the results will be consistent, no matter how many times we create a stack. If a creation or update process fails for any reason, we can specify that we want to roll back to the previous state. Let's look at what a minimal CloudFormation template may look like to define the VPC we created earlier. The most important section of this template is the VPC resource definition outlined by the red box. While a declarative approach may appear to be more verbose, most of the JSON we can see is necessary for scaffolding purposes only. As we add more resources, the scaffolding code will become less apparent. Once we have defined the state of our virtual infrastructure, we need to request CloudFormation to create a stack based on our template. There are a number of ways to do this. For example, we could use the command line tools as illustrated in the slide. There are a few CloudFormation security features worth mentioning here. Firstly, CloudFormation's ability to be used to update, not just create a CloudFormation stack, allows us to check templates into version control and manage changes to them as we would with any other code change. This allows us to easily link the state of our environment with version and change control. Being able to demonstrate strong environmental controls is an important part of operational security. CloudFormation also allows us to mark certain stack elements as immutable. Stack policies help protect critical stack resources from unintentional updates that could otherwise cause resources to be interrupted or even replaced. Another element of security is the ability to monitor and alert changes to our environment. While AWS currently does not provide a way to restrict resources initially created by CloudFormation to only be modified by CloudFormation, it does log all CloudFormation events against their respective stack. Furthermore, we have the ability to monitor all APIs against the CloudFormation service via AWS CloudTrail. In doing so, we can automate checking against our change control platform. Having clear visibility of resource ownership is helpful for security. CloudFormation allows us to associate meta tags with individual resources or automatically associate all resources with the stack with a given set of tags. Another useful security mechanism is the ability to mark certain resources to be retained in the event that the stack is deleted. This helps protect against the accidental or malicious destruction of resources. As we would expect, CloudFormation is well supported by the IAM service, thereby allowing us to restrict who has access to the CloudFormation APIs and of course the resources defined within the template. CloudFormation allows us to define a series of nested templates and takes care of any dependencies between them. While there are obvious operational efficiencies to be gained here, it also allows us to separate the management of resources by group. For example, a network group could be responsible for network perimeter resources such as VPCs, subnets, and network access control lists, whereas a DevOps group might be responsible for compute, storage, and security groups. As a final note on how CloudFormation can help us maintain a good security posture, templates allow us to define input parameters that can be restricted in value. This allows users of the templates to select from a list of pre-approved values such as security groups or networks. In this video, we will be looking at logging on the AWS platform. We will start off by looking at the different types of logging, factors that will influence our logging decisions, and the scope of this video. We will then look at AWS CloudTrail, AWS's API logging service. Next, we will look at the logging features of a few commonly used AWS services, along with how we can use AWS to store and potentially process third-party logs. We will conclude by reviewing some of the key design considerations. Let us start by considering different classifications of logs in order to set the scope of this video. When we think about logs on the AWS platform, there are three broad categories that come to mind. The first is logs of API calls to AWS services. For example, creating an S3 bucket or launching an EC2 instance. Logs of this type are collected by the AWS CloudTrail service. We will look at this service in more detail later. The next type of log category are logs created by AWS resources, such as access logs to objects in an S3 bucket or logs generated by Elastic Beanstalk containers. AWS provides extensive support for service-level logs, so we will highlight some of the most commonly used logging features that we should incorporate into our designs. And the third broad category of logs are logs created by third-party applications residing on the AWS platform or potentially on-premise. This is quite open-ended, so coverage of this will be restricted to using the Amazon S3 service and Amazon CloudWatch. We may collect log files for a number of purposes. Sometimes we need to keep them for regulatory reasons for a given period of time, but more often they're used to provide insight into our applications in areas such as performance, customer behavior, or security. As the focus of this video is security, we will only consider logging from the perspective of how it can help us meet or improve our security posture. AWS CloudTrail is a web service that records all API calls to our AWS account and stores them in S3 for analysis. Even for moderately sized AWS environments, CloudTrail can result in a large amount of log data that could contain valuable security information. We could analyze this data in batch using big data techniques, but some events should be detected in near real time. That's where AWS CloudWatch comes in. AWS CloudTrail is currently disabled by default. However, it's a simple operation to enable the service, and it's generally considered a sensible action for any organization wishing to increase visibility into API access to the resources. The service is configured on a region-by-region basis, with log data being stored in an S3 bucket after a delay of around 15 minutes. We can optionally configure notification when new log files are delivered, thereby allowing us to develop an event-driven processing architecture. AWS CloudTrail is integrated with the AWS CloudWatch service. By using suitably defined filters in CloudWatch, we are able to monitor AWS CloudTrail logs and alert to particular events in near real time. In addition to being able to configure the AWS CloudTrail service via the AWS Management Console, we can also use the console to view and filter interesting AWS activity. Let's take a closer look at this service by the AWS Management Console. The first step in using CloudTrail is to enable the service. If we have not previously enabled the service in a region, we will be presented with a screen similar to that shown in the slide. We click the Get Started button and proceed to the configuration section. When enabling the service, we need to choose an S3 bucket and log file prefix. The prefix is just the name of a sudo folder inside of S3 into which logs associated with the region will be placed. We can also configure CloudTrail for a given region to collate all API calls associated with global web services, such as IAM. A few minutes after being enabled, we will be able to see logs of API calls against our AWS account. For example, in the log, we can see that the user Daniel created a security group. Details of how AWS CloudWatch is used in combination with AWS CloudTrail is contained within the monitoring and alerting video in this series. Now let's take a look at the logging features of the AWS services themselves. Logging of usage and metric data has extensive coverage throughout AWS Web Services. We cannot possibly cover logging supported by each of the services. Rather, we will focus on a small selection of the more commonly used security-focused logging features. While the AWS CloudWatch service's role is to record resource metric data for other AWS services we consume, collecting metric data and storing it is a form of logging. Therefore, for completeness, we will briefly mention it here. One of the limitations of the service is the age of metrics accessible via the CloudWatch service. If we value metric data for longer than 2 weeks, we will need to copy summary data out of the service and place it into S3 for longer-term storage. As Amazon S3 is a durable, low-cost objects data storage service, it should come as no surprise that it is the storage location for AWS services. Before we look at the small selection of services that use S3 in this video, let's take a look at the logging features of S3 itself. S3 logging is enabled at the bucket level, thereby allowing us to selectively enable it only for buckets of interest. Logging is optional, and apart from the storage costs associated with the storing of log files, comes at no additional cost to us. When we configure logging for an S3 bucket, we need to choose the location, another bucket, and a prefix or folder into which we can place the access logs. While we can use the same bucket the logs are being generated for, from a security perspective, it makes sense to choose a secondary S3 bucket with strict access controls. Therefore, in the event that someone gains access to the source bucket, they cannot easily hide their tracks by modifying the access logs. An S3 bucket access log records details such as the bucket name, the access time, a source IP address, request URL, etc. S3 also supports custom access log information, URLs that contain query string parameters starting with x-. While these strings are ignored by S3, they do appear in the access logs. For more information about the contents of a log, refer to the Service Access Log format in the Amazon Simple Storage Service Developer Guide. While log files are automatically rotated up to several times an hour, old log files are not automatically deleted. S3 provides a useful feature allowing us to automate lifecycle management, either deleting the logs after a given period of time or archiving them into Amazon Glacier for long-term storage. Closely associated with Amazon S3 is Amazon CloudFront. CloudFront is AWS's content delivery network service and similar to S3, it allows us to store access logs in an S3 bucket. Assuming we are storing logs in an S3 bucket that our account owns, a suitable bucket policy will automatically be created and assigned to the bucket. If, however, we are logging to another AWS account, we need to provide access to the CloudFront origin, say using a bucket policy that references the canonical user of the CloudFront origin. Similar to S3, access logs generated by CloudFront will contain a number of fields including the date, time, edge location that served the request, the client IP address, etc. Full details are contained within the CloudFront Developer Guide. The last of the AWS Web Services we will look at is the Elastic Load Balancing Service, ELB. We can enable access logs on an ELB by ELB basis and choose the S3 bucket and prefix to store them in. Logging for an ELB is optional and disabled by default. It's very simple to enable, and we can do this via the Management Console. Access logs contain information such as the load balancer name, time a request was received, the client's IP address, latencies, request path, etc. As log files generated by S3, CloudFront, and ELB get rotated up to several times an hour, there are limitations to what we can do in real time. Furthermore, they can generate considerable sized logs that often require scalable data analytics methods to analyze them. For this reason, Amazon Elastic MapReduce or EMR and S3 are well integrated and make a good storage distributed compute platform for log data analytics. Now let us briefly consider logging of third-party applications. The first service to call out is AWS CloudWatch. In addition to providing a gateway to all our AWS resource metrics, it also provides support for third-party logs. For example, we can send existing log files to CloudWatch and monitor the logs in near real time. This is achieved by installing a CloudWatch-provided host agent, AWS Logs, on our EC2 instances. As part of the agent configuration, we can specify a log group and log stream, the former being a group identifier for one or more streams, and start the agent. This allows logs to be sent to CloudWatch and monitored with filters in near real time. Finally, S3 is commonly used to store logs for on-premise resources. When using third-party products and tools, we should always use IAM users with the minimum privileges required to perform the required task. We should never use our root credentials, and unless our tools or services need full access to S3, restrict its access policy to only the required subset of S3 actions and resources as required. We may choose to log for a number of reasons. It's therefore important to understand what the relative priority of each is. If we just need to collect logs for regulatory reasons, then we may defocus the need to get real-time access to logs. However, if logs for different components of our architecture are used for real-time performance but not for long-term storage, then the frequency of log rotation should be different. It's generally considered a good design principle to separate logs from the host or resource that created them. Think of a host sending its logs into a centralized log server. To protect against the scenario where the host is compromised and the attacker attempts to conceal his tracks by modifying logs. We should take a similar approach when configuring logs for S3. We should place logs in a separate bucket with a suitable access policy. This safeguards against a misconfigured policy on the source bucket or someone having gained elevated access. Some logs are clearly going to be more important than others. For example, CloudTrail logs will contain data that's more sensitive than access logs to an internal development Elastic Load Balancer. We should place greater controls around our sensitive logs, not only restricting who can access them, but also requiring additional steps to delete them. We can enable multi-factor authentication for API calls to delete sensitive data residing in S3 buckets. As all interactions with AWS Web Services are via an API call, the logging features provided by AWS CloudTrail are incredibly valuable. Ideally, logs should be used in near real time to alert us to potential security threats. However, even if they are only used as part of an investigation following a reported security event, they provide a detailed record of everything that's happened against our account. For this reason, we should enable CloudTrail for each region we allow our users to create resources in. Approaches to log rotation or archival is driven by a combination of policy, economics, and who within the organization needs access to logs, for how long, and for what purpose. We should have clearly defined aging and access policies for each different type of log, and enforce those policies via a combination of S3 to Glacier lifecycle policies. AWS provides native support for encryption of objects in S3 and Glacier. For sensitive log files and data, we should consider encrypting before storing on S3. The S3 service supports a number of means to encrypt and store data on the service, either using keys managed by AWS or keys that we manage as consumers of that service. In this video, we will be taking an introductory look at Amazon's deployment and management services. We're going to start with a brief summary of the current AWS services that belong to the product category deployment and management. We will then focus on the AWS CloudFormation service before wrapping up by looking at ways to streamline the design process. While the focus of this video series is architecting for the AWS cloud rather than DevOps for the AWS cloud, it wouldn't be complete unless we at least provided an introduction to the growing family of management and deployment focused tools. Every solution architect should be aware of how their design will be deployed and managed. The DevOps movement has meant that development and operations are now closer than ever before. The first service we will look at is the AWS Management Console. For most users of the AWS cloud, this will be their gateway to visually managing resources. The Management Console allows us to perform just about every operation that we could if we directly called the individual service APIs or used the command line tools. Next, we have the AWS Elastic Beanstalk. This is a semi-managed application container service designed to allow us to deploy and manage applications and services developed for Java, .NET, PHP, Node.js, Python, Ruby, Go, and Docker. This is a good option if we just want to focus on application development and have minimal infrastructure operational responsibilities. One area that's seen significant growth in the past few years is host and application management tools. It's commonplace for organizations to already be using tools such as Puppet, Chef, or Ansible, or similar tools to manage host configuration. AWS OpsWorks is AWS's application management service. Existing users of Chef will find it the easiest to adopt as it provides support for Chef recipes. Moving on, we come to the newest additions to the deployment and management services, namely Code Commit, Code Pipeline, and Code Deploy. Code Commit is AWS's source control service. We can think of it as AWS's equivalent to GitHub. Next, we have Code Pipeline. This is a continuous delivery and release service. We can use it to design our development workflows for checking in code, building the code, deploying our applications into staging, testing it, and releasing into production. The last of the Code family of services is Code Deploy. Code Deploy coordinates application deployments to EC2 instances or on-premise compute resources. It uses an application specification file and accompanying repository containing the application. The last service we will look at is AWS CloudFormation. This is not just a management tool, but also a powerful tool to explicitly represent our solution architecture designs when specified in a suitable format. Let's take a closer look at it. While Code Deploy focuses on the configuration of EC2 hosts and their applications, Amazon CloudFormation tends to focus more on the management of AWS service resources. We can use CloudFormation along with a host-level service called CFN init to configure host applications. However, Code Deploy has simplified the process. CloudFormation is a declarative template-based service. We simply define what we want the end state to look like, and the CloudFormation service is responsible for achieving it. We specify what our infrastructure should look like by defining resources and their properties in the JSON format, and then make requests to Amazon CloudFormation to create or update CloudFormation stacks. CloudFormation provides support for nested templates. This allows us to easily reuse other CloudFormation templates or snippets, and allows CloudFormation to schedule the creation or update of resources to accommodate any dependencies that we may specify. Because CloudFormation uses a declarative template for input, we can be confident that the results will be consistent, no matter how many times we create a stack. If a creation or update process fails for any reason, we can specify that we want to roll back to the previously known state. Let's take a look at the anatomy of a CloudFormation template. A CloudFormation template consists of 8 sections. Each of the sections is optional, except for the resources section. More on that in a moment. The first 2 sections are single-value template properties. The first specifies the version of the AWS template and identifies the capabilities of the CloudFormation template. This is not the same as the API or WSDL version of the CloudFormation service. The latest supported version at the time this video was created was 2010-09-09. While this is an optional parameter, it's good practice to specify a version to avoid potential incompatibility if AWS define a new version in the future. The description attribute is used to describe what the template actually does. Descriptions are limited in size to 1024 bytes. but that's usually sufficient to provide a brief summary or provide a URL to accompanying documentation. The next section of a CloudFormation template is the metadata section. This allows us to include arbitrary JSON objects that provide details about the template. In this example, we use it to specify the version of the template, when it was last modified, and by whom. Next, we have the parameter section. This is one of the most powerful ways to make our templates reusable when providing some control over how they can be used. For example, in this template snippet, we provide a parameter instance type parameter that will be used later in the template to specify the property of an EC2 resource. While the parameter is of type string, we restrict its value to two valid EC2 instance types of T2 micro and T2 small. The mapping section of a template is where we can define simple key to value lookups. Mappings are commonly used to make a template reusable across AWS regions or instance architecture types. For example, in this template snippet, we define a mapping for both 32 and 64-bit versions of the Amazon machine image in regions of US East 1 and US West 1. We can then use the function findInMap to determine the correct AMI for the given architecture type and region we created the CloudFormation stack in. Conditions are one of the newer additions to CloudFormation. They allow us to change the behavior of a template based on whether a given parameter is set. It is commonly used to alter a stack of resources depending on which environment it belongs to. For example, in production, we may want to deploy an Amazon RDS instance based on a database snapshot, whereas in a test environment, we may want to just initialize an empty database. The resources section of a CloudFormation template is where the real work happens. It is typically the largest section and is the only section of a CloudFormation template that is mandatory. It consists of one or more resources. Each resource has a similar format, but the supporting properties will of course vary greatly between service. There are a number of optional parameters omitted from the slide for brevity. These include metadata, depends on, and conditions. For example, the CloudFormation template snippet described in the slide corresponds to an EC2 route. Creation of the resource is dependent upon CloudFormation having attached an internet gateway to a VPC. The route becomes the table's default route and specifies the destination of Internet Gateway. Let's take a look at another example. This time we use the condition element we created earlier in the definition of an RDS instance. In this example, we want to create the database instance from a specified database snapshot if we are deploying into production, and create an empty database otherwise. The last section of a CloudFormation template is the output section. This allows us to extract information about one or more resources defined in the template. For example, if we had created an EC2 instance resource and configured it as a web server, then we might be interested in outputting the URL to the website. We could achieve this by using a snippet similar to that shown in the slide. The value of the output is created by concatenating together the string http:// with the value of the instance's public DNS name. A full list of available attributes is listed in the URL in the slide. In addition to developing solution architecture blueprints for common design patterns, there's real value in developing accompanying CloudFormation templates. We can think of these templates as living design documents. Depending on the size of an organization, a CloudFormation template containing nested templates may refer to templates owned and managed by different groups. For example, the networking team may manage all CloudFormation templates that contain a VPC, subnet, or other network-related resources, whereas the applications and development groups might manage templates that contain EC2 resources, storage, security groups, etc. By combining together CloudFormation templates or snippets of templates from a centrally managed, version-controlled source, it will simplify the design and operational process. CloudFormation templates can be a little verbose, as all resources need to be explicitly defined. For example, we can't use for loops or similar shorthand. For this reason, some users prefer to use an intermediate domain-specific language. In particular, DSLs based on Ruby are particularly common. While intermediate DSLs can reduce the size of the source template, it adds another step to the development process, and there's a natural lag to support new features and resources when added to CloudFormation. Just about every solution design will contain a diagram that visually represents the architecture. Whether the solution design is contained within a document or a group collaboration tool such as a wiki, the solution design will be a representation of what the environment should be rather than what it is. In almost all cases, the design isn't the completely accurate representation of reality. Having an accurate diagram of a system is incredibly valuable, in particular from an operational perspective. Given that we want to develop a solution architecture diagram, wouldn't it be helpful if we could use that diagram as the input to a tool to automatically create a CloudFormation template? A few companies are working on doing just this. One such company is Visual Ops. Their software as a service allows us to visually create our AWS resources and then either launch a stack or export a CloudFormation template that represents the architecture. Furthermore, they even allow us to import an existing CloudFormation template and visualize what it would look like. While I haven't used the tool to perform the full DevOps lifecycle process, I have used their tool to create and visually validate blueprints or reference architectures. In particular, I found it very useful for quickly and accurately designing and visualizing CloudFormation templates for core network resources, such as VPCs, subnets, routes, access control lists, etc. Used correctly, tools such as these can help streamline the design process. This course, Architecting for the Amazon Web Services Cloud, covered the essential design considerations when architecting for the AWS platform. The goal was to help you quickly and efficiently map from general architectural best practices and design requirements to the specifics of the AWS platform. This included essential educational resources, business considerations, cloud design patterns, cost optimization, as well as application platform durability, availability, scalability, performance, and security across a wide range of AWS products. The AWS platform is constantly evolving, with new products and features being introduced at an impressive rate of innovation. While we could not cover every AWS service in this video series, I hope that you now have a solid foundation for further learning. I love helping organizations understand and adopt the cloud efficiently and safely. I hope you have enjoyed this video series. Thank you for watching.